experiential learning. It is not there. After that, there is one full thing. Misconcept. I have a friend, you call him sometime, Mr. Narayan Murthy. He was an ex-RCI director. I'll be very satisfied. Then I know all of you have been taught, sir, moving subject. Have you understood? When a car moves from one place to another place, how the car is going, that is in the kinetics. And other one is the how much distance they have changed. Navigation. Okay? Sometimes they confuse with dynamics. Dynamics and statics. The same thing. It's a two different way of Americans sometimes they confuse. They write something and they tell something, but please read good books, they will explain. So this one is the first thing. Then, positive fabrication. I am working and made a model in 3D printing in my college. Have you made a 3D printing in your college? Answer. Hello, sir. Anybody has made 3D printing in your college? Have you made himself with the student 3D printing one machine? Printing they know, but have they developed? In a very small college I have done it. Oh, you have copied from somewhere. Said, please learn from Japanese. Copy it. Copying is not easy. And students learn to copying. I have learned missile through copying. I am telling you very clearly, but it was not easy. It was all valves, whereas ours is all computers. And initially we are all analog and digital. So that one was not easy, but it gave me the insight to the missile. I learned from the Russian missiles, which came, I was given the opportunity by get people like Bidinath Chaudhary and all to visit, and we opened missiles and learned from the Subedars and all, who at least told us, you open the missile, they will open and show. They know which is going where. So what is our first job? A Russian missile. When I entered from Siemens at the age of, like you, they told, make a breadboard model. Making a breadboard model with valve circuit, I don't know valve circuit. I know solid state. I had to learn, and I had an assistant. He just died last month. You learn from the foreman. He is a practical man. That is what is experiential learning. His experience I have inherited, and he has taught me valve circuits. Valve circuits, what is the advantage? Fantastic isolation. Why isolation? Like a transformer coupled. The input doesn't go to the output. But they are all high voltage and all. Why to do that? So I first of all made the breadboard model. Then finally, when my boss comes from England, unfortunately, I don't know to name them, there's no boss who knows. So we made our own group. All IIT pass people. Dr. Saraswat was also one of them. So propulsion group, ourselves. But Bidinath Chaudhary helped us. And there is one gentleman, AVM Narayan. He says, do anything, I'll support you. Chaps, we didn't get much people. We started interacting with Bandyopadhyay and all. I learned theory from him. He is excellent in the theories. I've seen very few people who knows things such deep. But I criticize him. I challenged him. You make it. He failed. He accepted that I can't have a closed form solution. Then he also started sending his students. Now we are together. We have grown up. And we are working sometimes and exchanging. Now next is wireless communication. That's very important, sir. Then your sensors. Sir, if the sensors are there, everything is there. So please let there be the journey, sensor group in our INA. You please focus on that. I cannot do signal processing without sensors. All your water problem, other things which I was observing, I find everywhere sensor is required. After sensor signal, do analog filtering and digital processing. That's it. My daughter is doing gene therapy. I want her to give us a signal. She has explained me what is inside. No sensor. She is working on that. She has got, what they call it, startup. Do you have a startup group, sir, here? Hello, Professor, sir. There is a startup group here. Anybody who is working on startup group, raise your hand. I am very clear. Where is a startup group? Anybody is working with startup, please raise your hand. Bandhopadhyay, somebody should raise. Good, at least one person. Which startup you are taking? Okay. Hello, madam. Dr. Saraswat has given 150 crores to both Osmania University and Central University. My deputy is the in charge of Osmania University. So I am also the mentor of the startup. And we have made a startup which got money from IEEE. There is maximum death in the Telangana in electrical shock. Do you know? They call it defeat program. So we give the proposal, they accepted and they are giving the money. My student only has pushed it. But I myself and Mr. Basha, who is a startup expert, is from Japan. He was my deputy. We always give lectures together. So next time I'll definitely bring him. I'll bring the student also. He will show what startup they have done. And in the meantime, you can come and exchange there. So there is a startup thing, practical. You will be surprised to see the facility. It's expanding, and I am the mentor for that. Now my daughter is in other one, Central University. She is funded by Americans, SOS. That is known as biofin. All biological subjects are there in one building. It is like California. It's an oval-shaped building. I want to tell you, during Corona, many things have happened. People didn't know because people had time inside whatever is possible they have done. And we are also able to somehow communicate by our good Zoom. That's also American, or Microsoft. And we are able to work in the hardware also, not the software alone. So those things have been built up. But again, Bahar mein, that our GHMC comes, again, lot of holes and all. But inside the campus, a building like Apple in both the places is there. I invite all of you to come and share your experience. One, I will do it. Another, my daughter can help you, your field. Okay? So this is...
Sir, I want to mention you that we have got a biogas program.
Achha, achha.
That is PBT. And we have got a scope for startups. We have a number of startups working there. Mostly, right now, our major focus has been on medical technologies.
Okay.
And we are
Sir, it is the right time you bring them once to the facility.
Sure.
So that she can show you
Yeah.
that bio. And if you bring the other group,
Yeah.
I can show you the other one.
Yeah, absolutely.
So-
We also request her to visit here
Yes.
so that they can be a good
That
experience.
you have to talk to her.
Yeah.
I'll tell her.
Yeah.
She will give a lecture also.
Yeah.
She is a PhD from London School. I mean that. What is it? Degree, biomedical. But she has gone to London School of Economics because she is more financial type.
Yeah. And we have started a very unique program
Yeah.
with the Hills Youth Tour because she is also working.
Sir, I have already given you offer. You have to visit once. I'll bring her as well as I'll bring the other group. These two combinations will help you. If you tell me in advance and if you can get the 2 hours flight, I don't want that 4 hours flight. वो दिल्ली में उतर के ऐसे नहीं आने सकता. The students can come by train.
Yeah.
I can tell them they'll come. You plan that, so that but you come once, so that you can feel. Bandhopadhyay can lead.
Yeah.
Bandhopadhyay has to come in field.
Yeah.
He has his knowledge. I want to translate that. Okay. Next is the. Hello. So where I am there. Sensors, actuators, softwares with reconfigurable ASIC. ASIC can be reconfigured. That is already there in Micron. What is it? The two big companies. Now, Now it can do many complex system. But madam, we are all forgetting verification and validation. V and V. V and V is very important. There is no body, what software you are writing, your boss doesn't know. Lot of accidents are happening because of that. That's why they are not allowing drone. Even in USA, lot of restrictions come. See, there is two things. One is code walkthrough. Code walkthrough is possible once I structure the design. Now, after code walkthrough, somebody has to, it is working like the control system I designed, it's working like that. For that, control system knowledge and embedded system knowledge, both are required. So that way, we combine. I also know control system. My PhD is on Conclave filter, but he knows better. I know less. His domain is much bigger, but I know embedded system more than him. So this is a combination. It works, and we all learn to that. Now next is, today the discipline of computer science, electrical, electronics, computer science, kya hai, Debjani? What is this? They are all same. All are having IoT, all are having AI. All grid stations and all, they are suffering because they are done by poor old people. They are required, but somebody has to computerize it. Grids have to be connected properly. Okay, next. The changes in operational environment. With the advent of concurrent engineering, is changing in the operational environment. Okay? Now, this is the main thing. This, first of all, is the foundation, then breadth, depth, leadership, which column has the maximum. Then design, you should know. Curiosity. There's one advertisement called Curiosity. Have you seen that? TV mein aata hai. That fellow is asking, what is curiosity? He thought it's a place where he can visit. Then somebody explained him. Then communication skills. Madam, you have to communicate. Unless I communicate, I can't reach you. Then, so English people are important. So then social skills. This is what social. I have come. I want to mix with all of you. This is not only technical, it's social also. I want to socialize with my friends. Okay? Then you should have the global view. Then last one, personal strength. Every day they will come to the office. They'll say, my daughter is sick, my son is sick, my father is sick. And you cope up with your problem. When I'm not able to come, I should have a friend who should represent me. So don't go alone. I was telling continuously, where is that lady, Disha? That you should have a group. So when you are not there, Dan should come. I saw yesterday they were there up to night 12 o'clock with me for making this proper. So that was what? If suppose he is not well, he will come. Is that okay, Debjani? We should have always a group. This selfishness you leave. If you know, Kalam told me, nobody will steal your work. You will grow further. By telling somebody, you know better. Okay, so personal strength. Then engineering education is a fundamental. Cultural change in muskil hai bhai. People are not changing culturally. What is cultural change? They were going in the same old fabrication way. But today you should at least semi-automate. Whole our India is lagging because of semi-automation. You cannot do full automation. I have seen in France what semi-automation can do. In this size of a room, 30 missiles are produced in 15 days. Whereas we are able to make 2 or 3 in a month, that too with a great effort. What are the things required? Conveyor and belt. You are teaching conveyor belt, please teach. You have servo control camera. Servo control, some photography should be there. Then there should be one SAP which will integrate the software. And there should be some testing facility. Your job is system integration by semi-automation. Then this size of room will produce 30 missiles in a month. 30 chota missile. Like now, we are able to produce only 3. So now I have got an order from Philippines, 3,000. I'm telling you, why you are bluffing? You can't give 3,000. I told sir, no, tum bhi jao, ab bhi jaake jhagda karo. Hamara position nahi hai bhai. I cannot fight much. If I tell too much, they will avoid me. Debjani will avoid me. I always argue with her that don't give me bhashan. Do something on semi-automation. Let us target it. that will make that cultural change. Let us introduce that three things I told: system, engineering, technology, and art. Now, my field is aerospace. It consists of so many missiles, then your aircraft, satellites, all these things. So now, what is the fundamental thing? System engineering. For my field, you can think in your field also in the same way. You have to highlight what are the system engineering needs. Like here, what I need feedback control system. First of all, Bandyopadhyay and I should agree, and Kadam. Then there are three parts. One is navigation, where you are. What is your XYZ? What is your theta phi psi? You need 6 things only: X, Y, Z, theta phi psi. Okay, maybe velocities, Vx, Vy, Vz, rotation, this thing. You need that. After that, you do guidance. Guidance means, suppose I am here, I want to go home, so I have to direct. I can go by jumping, but I'll have my physical limits, or I'll make accident. So I had to design a path which is purely software. In your bio also guidance is there. I've seen in my daughter's thing. You have to find that, within our body, there is one Israeli gentleman, Bandyopadhyay, he has got a Nobel Prize. We don't know all this. The doctors gave me. The pill goes like a missile. It's a said missile design. Inside, this is moving under guidance and goes to the place, it burns there. I will send you the paper. We are not working in this. If you don't work, who will work? They don't understand control. But after my shouting, and Vidyasagar tried to open that group, he told me, you also go. I am able to, Vidyasagar is a great man. So we are able to learn from the doctors and trying to change their attitude. Somehow in India, doctors, if any doctor is there, I'm afraid, they're more operation oriented, test oriented, because they get salary from the big people and they paid big money. I'm very clear. But there are some doctors, I do agree. And the pharmacists, they only write the papers. Pharmacists, they're only writing papers. My 2-3 friends, I have criticized them, they're changing. Because they have to know my daughter is doing that instruments you have to use, how to use it. So please change this medical, you take the lead, I'll be behind you. Okay? And finally control. I should not tumble. I should go in a Jal Sundaram, he says, Chaudhary, I do not want any tumbling. The first missile flight, I had to challenge who is from VSSC. VSSC, they have not flown onboard computer system before us. Debjan, you should know that. They have flown digital control system, but with software in 1988, we are the first fellow. You ask Suresh and all. First fellow and Dasgupta, we are the first fellow who done that. Because of Dr. Kalam's encouragement, he didn't allow us to work in one direction. And he gave me a freedom with 20 young fellows, and all others will work. Because I have some of the experience before, and in UK also, they never allowed me to come. With lot of effort, I came back. I was in trouble while coming back because I was more or less attached with them. So in that process, I learned. My wife was also working nicely within the campus. My chota santa, 3 years, I came back because of Dr. Kalam. Sam Pituda and all, they brought, I also was brought. I have not publicized all these things in the paper, I'm telling you personally. I came back and he told me afterwards, only 3 of you have come from the whole world. And you remained and you gave lead. I'll definitely take care of you. So he put me in RCI. No senior scientist, SERB should know, stays in RCI. They come, give lectures, go ahead. Because sons and daughters have to be taught in good schools. Kalam said, no, he convinced this lady, my wife, what is your problem? Education. Don't worry, Sundaram, give a car. And if Chaudhary is in charge of the chairman, school will improve. So we made some changes in the school, brought some teachers. See, in that school, driver's son also is there. So I find 50% failure is because of that. Because they are not taught in their home properly. So I brought some teachers. There are some things available in the country itself. They give coaching to these teachers. Teachers never liked it, but they finally liked it. And school, there's no failure after that. I should say this is because of Kalam's pushing me. And my own daughter was in the school. So if your own daughter is there, you will push automatically. So like that, things move, Then, what is that? You go to modeling and simulation. Sorry, MEMS. All MEMS. Microelectronic mechanical systems. Flight instrumentation, ground system, radars. Then you have to have some supporting features. Modeling and simulation. For this, sir, mathematics is important. Now, numerical systems are key to the thing. All of you, I was telling Disha also, should know how to solve a differential equation. What are the numerical techniques? That's a very important course for all engineers who are working with some movement, whether it is chemical, whether it is civil, whether it is electrical, mechanical. I am ready to teach 2-3 classes if you want. I know that subject. Then, including fundamentals of aerodynamics, maybe medical for her, aerodynamics for somebody else, like that you can do. Then hard real-time and embedded system. Madam, today your PC is there. PC cannot do everything. PC can load the system into an embedded system. Embedded system will be very small, but PC will take the information without wire and do the things through router and server in the Python frame to the people. Now Python is like English. I have taken training during Corona in Python. Bandhavata, please take. You'll understand with no time. Just spend some 6-7 days. Oh, jata. Then next is the hard real-time and embedded software engineering application, quality assurance, technology and project management. You have to do that. Now, various technologies. Here is the failure. Sir, technology. See, there is inertial radar and GPS. Kalam concentrated on this. He says, I am going to do this with you. But select also some gyros. How he has selected? In the gyro, what is gyro? It senses the rotational motion. First of all, you know Newton's third law of motion. No? So accelerator you understand. When you sit in bus, when it starts, you get it back. So some pendulum will be there, which will send the acceleration. And gyro is nothing but, suppose you think of 3 degree. 1 degree, you give the motion, it will rotate in the other one. One x-axis, you give high rotation. Y-axis, you give a torque. Then in Z-axis, physical movement will be there. Have you understood? Is it clear? So 2 physical senses are told. So these sensors, he said, go for inertial. Because that was known to us. Mr. Banerjee, who is my boss, he used to work on that. I also used to work, but he is more specialist. I make control class, he makes inertial class. Inertial class accuracy is much more. Control class is easier. But because we made it, we learned through experience. He struggled after us. Kalam said, no, they have made it. We'll try that. Chaudhary put a Kalman filter with that. I said, Kalman filter can improve 100 meter to 10 meter, but it cannot make 1 meter. You have to understand, Kalman filter cannot do everything. Kalman filter can make you 1 order better, not 10 order better. For that, some more tricks are there. You have to know that. So you have to continuously. Microprocessor, microcontrollers, SOC, FPGAs, DSPs, reconfigure ASIC. Then instrumentation, various transducers, positive fabrication, addition to modeling, simulation, system engineering, total system, technology and project management, state-of-the-art ERP environment. Sir, you have ERP here?
ERP is going to be implemented.
See, it's required.
Yes, it is going to be.
That-
They are in the process.
See, for engineering, I suggest you go for SAP. But SAP is slightly costly. You talk to both TCS and Wipro.
Yeah.
I think ERP is required. I have one expert in my lab, Mr. Gautam Mahapatra.
I know ERP was first established in Asia.
But I can come along with him.
Yeah.
But Gautam knows better than anybody in the whole. He is passionate about that.
Sorry, for the next 15 minutes.
ठीक है, I'll go ahead.
Yeah.
Now, what is this? This is nothing but an object. Any system is an object. So there is some input and there is some output. So it's a transformation. So if you write in an equation in Bandopada's way, U is transformed to X. Okay, Bandopadhyay? That equation, Bandopadhyay, is okay, no? X is U is get transformed to T to X. Now, what is there? The systems can be so many types. Now it can be single input, single output, static, dynamic, conversion, communication, open loop, closed loop, anything. Self-learning, there are so many kinds of systems. Now this is the main thing I want to tell. V and V process, I'm trying to give in a diagram. I can't help it. If I don't tell properly, sir, I can tell, but I thought it's tutorial. They should understand.
Basically for students to
So if they don't understand, I can take blah, 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 I can go on. Is that pace is okay? Hello, are you happy or you are getting bored? You tell me, I'll make it short if you want. But if I don't explain, you will not understand. But I'll go to the electrical electronics department in the afternoon, after Bandopada's lecture. So, you have to make a mathematical model. Okay? Now the actual system, you try to model it. Russians say they are able to make mathematical model of the seeker. After making the seeker, they found out so many mistakes in the mathematical model. R.N. Bhattacharya was fighting with them. He says, sir, please keep quiet. You are able to do it because Dr. Chaudhary is continuously giving you input. And he is also writing the equations. You cannot write the full equations until the thing is validated. What is validation? I'm coming. So you make a model, whatever you understand. Now, this mathematical model, whether it is right or wrong, you do a parable thing. The actual system, you do computer simulation from mathematical model. Now, you compare the real flight in the validation. That's what is experiential learning. From the flight trial, you are getting the data. I'll tell very simply. Flight trial, I have the telemetry data of all the rotations, other things. You have the inputs. Flight has failed. Debjani, flight has failed. So I give the same inputs, it's working. That means my model is not okay. So that was my main work, after which myself and Kadam got appreciated in DRDO. That is known as tail wag dog. Dog wags the tail, no? Tail should not move the dog. Have you understood? Our tail was moving the dog. That means the engine which you are using for up-down, when it is vibrating, some structural frequencies are coming and they are giving a 14 Hertz oscillation. But I am not able to capture it. Why? My telemetry friend was capturing the data without following Shannon theorem. What is Shannon theorem? Whatever is the fundamental frequency, you should have at least 2 times the frequency to capture the data. Suppose there is sine wave. You only will capture the peaks. So at least 2 times what? 10 times you should do it. He was not doing it. He is also a very good engineer. When I told, he was very upset. He only requested me, साहब ये बड़ा साहब को मत बोलो. हम नहीं बोलेगा, but हमारा flight fail हुआ, हमको question कर रहा है. Should I prove it? I had to prove for Dr. Kalam, it is failing in the lab also. We took the vibration from there, and myself and Kalam did that, and we gave a medicine. वो frequency निकाल दिया. हम ज़्यादा research नहीं किया, वो frequency निकाल दिया. That's all. We did that so that frequency doesn't come. So my propulsion friends are very unhappy. To prove it, I have broken 10 engines. They'll say, we will not give Chaudhary any more engine. Because I will break every engine, because Kalam is showing everybody. Dr. Ghoshal, Bandopadahyay, Kailath. See, what they are doing is correct. Vidyasagar. I was like a gel. So That is what is validation. So validation and verification, code walkthrough all of you can do. That needs a good structure and some good software well. So if this thing matches, that is what is validation. Next. So now my big friends are coming in software standards, software skills, system knowledge and experience. Now, don't get confused. It is nothing. I am not telling you to see all the data. You just make a plan. Your boss should be able to draw this. Simulation software. In my language, there is a plant and there is a controller. So plant is here, software is this, and support software is here. So all the data are mentioned. But I find it is impossible in bio. It is like a spider. So what my daughter has done, he has made video link. And he is telling group of things which is going. Because of my force. I said, no, you have to tell me. Then only I'll understand. I mean, we failed to draw a signal flow diagram, basically. Now ERP system will compile all the things. I'll not. So this is, now in a college, what we should do? I tried this with one college. Bandhavata knows it. Now there is a, say, EEE department. What is EEE? In JNTU, electrical and electronics engineering. Debjani, it's very important for you. So here, there is a system engineering and technology, there is a power system, there is a renewable energy. Okay? My focus is on system engineering and technology. I'll do the other things also. But you see, system engineering and technology needs control system and technology, embedded system and networks, power electronic application, because motors are there, it has to work. So with that, I can meet this basic theme of the conference or the workshop. Then you can have one more with the power system, with these three. Planning, reliability and qualify, smart grid, micro. Okay? Then you can go for renewable energy, solar energy, other things. Have you understood, sir? Now go to next. Sir, I'll take another 10 minutes. Go to the next one. Have you understood this? So when you do more workshop. Conference, sir, I'll take another 10 minutes. What is the time? No, 10. तुम जाओ भाई, तुमको दे दिया ना. The tabletop. मैडम tabletop में जाओ, तुमको कल दिखाया. No. It's not my laptop, it's your laptop. इसमें टाइम नहीं आया है. अब करो भाई. Now, whatever I have talked, that has to come on tabletop in a college. So that's why the name is Real World on Tabletop for inertial guidance and control. Okay? Now, you see, basically, there is a controller and a plant. I know the controller because I have designed it, or somebody has designed and given you. So you have implemented. You can check that. Now, you do not know the plant. Plant is not known properly. Like tail wag dog, it will happen. So plant is very difficult to design. So that's a question mark. But what is plant in terms of Bandhavata? X dot nonlinear is function of x and u. Okay? Output y algebraic equation g x u. Now what is my innovation? To reduce the model. My innovation or Bandhavata's innovation as a control system man, we should be able to reduce. But in your field, you have to do. You have to explain us. We will help you. Next is, see, the things are very difficult. Embedded, then real time, application process, V&V, verification, validation, ultimate validation in hardware in loop simulation. What is nothing but experiential facility or interface. Next. Okay, so I have already told you that there is guidance system engineering, control system, conclusion, and hands-on engineering. Okay, now I'll give one example. You see, there is a missile, okay? Don't worry, it can be a car also. So any car or a missile have to have some input. You can drive the car automatically through some control system, or a aircraft or a missile remotely. So it is the same thing. So I put that outside. What is my basic movement in the car? To move the wheels. In the missile, fin. Other things you are moving. So that's why the deflections are the command. You are giving the command deflections. You are giving the feedback at the body rates and acceleration. Understood? So if you do that, then this is known as inertial guidance and control system. I am talking of one system only, which is inertial. That means sensors, gyros and accelerators. So now you come to this IGCS. What is IGCS? Before that, you see the third one better. In that, there is some inertial sensors that give delta angular increment, delta velocity increment. Okay, that's from a sensors. It goes to the onboard computer. Onboard computer give the deflection command. That is your job. Now you come inside and launch command, they are giving some, before launching, some data. Now come to the last one. Inside this, there is navigation, guidance, and control. So this entire thing is software. Hardwares are here and here. Have you understood? Hello, Dan? Hardwares are here and here. The only hardware, which is onboard computer, that has these three components in software. So software has become very, very important. Now, so this is my job. Now you are flying the missile. You see all the parameters, you see all the outputs, okay? Now you see GPS has come. Initially when I flown, I had nearly, I'll tell you the exact values. The value was some 200 meters away. See, Jan Sundaram and Kalam make one island, Wheeler Island. I was under tension. In the Wheeler Island, they will capture the missile. But we saw it's giving 200 meters away in a 300 kilometers range. He forced me to put GPS. Within a year we did it. I kept the provision. So I know GPS is going to come, but Americans will not give you military GPS. So we did some techniques by using commercial GPS, which they cannot stop. I hope no Americans are there. So they are angry with me. I get problem with visa. Some 6-7 of us in trouble. Devjan, you know this? I took nearly 2 years to get a NASA invited visa. So they know that I am one of the designers. So finally, we designed it. That 200 meters, we made it within 10 meters. That is nothing by Kalman filtering. So you can make 200 meters to 10 meters, but not 0. Okay? My boss said, let us say, I said, sir, if you ask about sigma, I'll say 25 meters. I always believe in spread. You don't claim, sir. I request you.
Just 5 minutes, sir.
I'll do that, sir, but
5 minutes.
okay. So that one we did it. Now, how we have connected the state of the art in the hills. You see the same way the buses are there. Okay? The buses, MIL 1553 bus, interface. Then the simulation things, all these things we are seeing. ADC, DACs are there. Now you see one flight. You see there are some delta dot or flow rate. Hydraulic flow rate comes. You can't help it. So that flow rate we have expanded and we know that this much is allowed. Otherwise hydraulic motor will not work. Okay? This is called experiential learning. Through flight, through simulation, I am able to do it. Now, it was no time to make an anti-tank missile design. Now, we got the best thing in the world. We made the target of AD. Target also we had to make. Abroad, they give the target. Devjani, there is a target laboratory abroad. But here, the RDL RCI has to pick the target. So we converted one Prithvi as a target, hit by the AD missile, that is Dr. Saraswat's program. And I was one of the designer. We are able to hit and show that. These are all the hardware connected. We went to BrahMos. BrahMos is a collaboration because what we thought, we cannot do everything ourselves. So let us share the technology. This is Dr. Pillai. He forced me in that. So I was also there, but I had little time because I was busy with other things. But there we gave the inertial guidance system is ours. Other things are theirs. Then as a control system designer, you do all frequency response tests. Sir, frequency response test is a failure. You should do it. But for bigger commands, it doesn't work. So you have to do simulation. Or very big nonlinear analysis. I gave you that problem. You said better to do I am doing. And you supported that. So like that, aim for the design is gain margin. See, we teach in the college, 6 dB gain margin. I have seen in actual flight up to 4 dB it works. When it doesn't work, when the velocity is low. So plant is changing online. Plant is changing online. So if I can cross the 4 dB thing quickly, which is there in the low velocity zone, then it becomes stable. It's very fast crossing. So it is not able to fail because the plant is changing. So with that, and we all know we need 45 dB. Not required, sir. Phase margin 30 and 25, myself and Kadam are flying. We have proved it. Then your rigorous short period simulation, all these things we have done. Now, this is a model. It's at maximum 5 minutes, please. This is a knowledge gathering system. There is a decision process. There is an action process. Airframe, kinematics. What is kinematics? I told you, vehicle trajectory. X, Y, Z. See this matrix, Vx, Vy, Vz, theta, phi, psi. And they are target trajectory. All are inside. Because time is not there. These are typical block diagram of the same thing. Now we do the structuring of that. Then I write the equations. Then the process. Then it is a lecture for him. These are the courses is required. For navigation, I'll concentrate. Quaternion algebra. How many people know quaternion algebra? Please raise your hand. Anybody knows? Please raise. What is the fundamental advantage? One line answer is there. What is the fundamental advantage we have got?
It allows us to write the equation in a more compact form. So, and like when we apply it to spinner systems,
For them. But what is the basic advantage?
it allows us to capture rotation in 3D.
What is the problem in 3D? Tan 90 degree is infinity.
Yeah.
It avoids tan 90 degree. It converts it to 4 scalar quantities. Q0, Q1, Q2, Q3. So the scaling also is better, as he is telling. Scaling is within 1. Tan 90 degree will not happen. It will tell whether it is 90 degree or 91 degree. This is invention by Israelis. I think everybody should know it. It's required in computer graphics also.
Yes.
Okay. So please have a course. I am ready to give one introductory course. Devjan, you can organize also. So this is one thing which I find people are not knowing. Quaternion algebra, matrix algebra, integration technique. Then this is another thing. Solid geometry with geodetic, geocentric and 3D representation. If anybody knows it better after me, that is Satish Reddy. Satish Reddy knows this very well because I used to continuously fight with him on that. He is also knowledgeable in that area. The geodetic, geocentric, other things. Now, Bandopad is studying there, so I am not able to control myself. Sorry, sir. I will say control system. Control system, see, Laplace transform, Z transform, state space methods, optimization design, robust design. These are must. Like guidance, estimation theory. You see, I have told everything like that, each one. When time is there, I'll talk because Bandopad is getting angry on me. So now these are the hardware, critical technology, sensors, actuators. We concentrate on sensors and actuators and embedded systems. You can see there is a laser gyro. First of all, I explained you mechanical. Then we made in RCI, laser zero. They are flying. Okay? Our country optics is very poor. Devjani, to note down, optics is very poor. We don't know how to polish a good mirror. Only Bardwan University and somewhere in Pondicherry, there are two groups they are working. This is one of the area which Russians help me. Actuators. Then this facility, who will build? You have to build yourself. Americans are not giving. There are two men in the world. One is Mr. Maxer and one is John Carter in USA. They are 10 years older than me. They're still alive. They talk to me, but they like me. They said, I am the only man who have understood them. And I made a collaboration with a Swiss fellow, because Americans, there are problems. So he made half the thing, we made half the thing. Collaboratively, we did the complete this thing. Irrespective of the target motion, it will always point towards the missile. Bandhavadeh notes, it is fundamentally a servo control, but auto servo control, so that the seeker always see to the target. That was my biggest achievement in DRDO. These things we have made ourselves. You know, all the mechanical things are made in that HMD. HMD was lying idle. We can go do so many things in that. I had to stay 1 month for Bangalore. I'm not a mechanical engineer. But just to show Mr. Mark sir that it gives the same accuracy, I'm finishing, sir. So finally, this is the way, with number of years, number of guided flight trials has come down. See, foreign, they have taken nearly 1950 to 1980 to come to the level. We have started in 64. We planned 64 flight, but within 14 flights in 1988, we are able to come near them. So what I'm telling, India is not bad. We have our talent. The technology is basic. We have to go ahead, do some way. Now, for the students, the hands-on engineering, design of embedded system, set up a computer. You are having NI system, I heard. This is a system. Sir, it is nothing but there is a pendulum. It is available with them. There is a motor that when I give rotation, it should not fall down. You write the software on this. You write in any language and you try it. Then only you learn. Are you having this? You must be having. Sir, what is this? NI system is having. Please buy it. Then data acquisition system. Every day data are there. Please do it. Oh yeah. Robots, you develop, but buy something. So with the robots, you can put your software. Here your software is moving. Have you understood? So, can you read it? How to make it bright? Oh, conclusions, bioelectric, MEMS, all this positive aviation. Then these are the case study, this thing. Thank you. Okay. I will stop here. Sir, 1 5 minutes video, can I show? 1 5 minutes video, just, you'll end that. 1 5 minutes video. Then you put it. It will be nice. 5 minutes video. Bandhavadeh. That's interesting for you also. Yes, okay. Sir, I can't help it. I have taken how much time?
We should see video because it is going to be very interesting.
Any question you can ask. After Bandhavadeh's lecture, because Bandhavadeh is looking very badly towards me.
Directorate of Precision Guidance Technologies and Control Guidance and Software Integration are primarily working in the areas of hardware in loop simulation, popularly known as HILS. They are also responsible for mission software design and development of guidance, control, and navigation systems. present challenges and requirement for new type of missiles with different seekers, with their complexity for different target scenarios, have led to the development of Advanced Simulation Center. It is our privilege to have our beloved President, former Director of RCI, His Excellency Dr. APJ Abdul Kalam, for inaugurating Advanced Simulation Center. The missile, which consists of various subsystems like onboard computers, actuators, sensors and seekers, is expensive and is not reusable after a test launch. Hence, rigorous simulation is essential. Simulation is an analytical tool to convert a paper design into flight hardware and software. Conceptually, any closed-loop system can be represented by controller and plant. It is transformed into an engineering block diagram representing the flight configuration. Finally, this block diagram is converted into hill setup, implementing required electrical and communication links. Mathematical model of actuators, sensors, and simulated onboard computers are replaced with respective flight hardware in stepwise manner during hills. INS GPS, RF IR seekers, and various actuation systems, including pump motor, batteries performance, are checked and evaluated in hills. Under rapid proto environment, computer models are used as subsystems and finally replaced by actual flight hardware. DRDO's present challenging missions have led to the development of Advanced Simulation Center. It consists of Hills Lab, Advanced Hill Center, Remote Simulation Lab, Mission Software Center, Guidance Systems Engineering Center, and Visual Simulation Center. All the missiles of IGMDP are simulated in Hills Lab. At present, the renovated Hills Lab has the capability to simulate missiles with RF, MMW, and IR seekers. Advanced Hill Center is equipped with state-of-the-art gimbaled large travel span dual target motion simulator have been conceptualized, designed and developed jointly by India and Switzerland. The 5-axis flight motion simulator has higher dynamic range and continuous rolling capability. The dynamic scene generation for IR and RF targets with background is under progress to include in this center. Remote Simulation Laboratory, having state-of-the-art 3-axis flight motion simulator, high-end real-time simulation computer in a MIL standard 1553-based communication environment, connects missile integration building and control actuation division through fiber optic based shared common reflective memory network for remote flight vehicle in loop simulation. The primary activity of Mission Software Center is to design and develop the real-time in-flight mission software and checkout software for various missiles. Center is involved in the design and development of indigenous real-time operating systems for missile applications. Standard CMM software engineering practices and independent verification and validation techniques are strictly adhered. Guidance Systems Engineering Center has extensive data fusion techniques for development of closed-loop guidance for anti-ballistic missiles with state-of-the-art seekers, strap-down navigation system, and multi-function radars. Currently, this center is actively involved in the development of guidance schemes for missile-launched force multiplier, precision-guided munitions for multi-target neutralization with sub-meter accuracy and without collateral damage. Visual Simulation Center is equipped with advanced high-end workstations for graphical modeling, rendering, and visualization. Virtual walkthrough inside 3D models of missiles is developed. The aim of this center is to integrate visual simulation with the real-time hills to create synthetic flight scenario, Evolution of advanced simulation, along with high-speed processors and data fusion schemes, is resulting in reduction in the number of expensive guided missile flight trials. Joint development of DTMS has proved indigenous capability.
Let Bandyopadhyay speak. If there is one or two questions, I'll answer. Others, I'll ask afterwards. One or two questions. If you don't ask any question, then I'll think you have not understood me. At least two questions.
Yeah.
Sir, yesterday you said that I am in the AI department. So you said you will, in your talk, you will talk about what is AI. You'll tell me about that.
I didn't get the time to go to that course.
Okay.
Now you have to interact with me during the other time.
Sure.
But one short I'll tell you. See, any system is having an output you can monitor. All systems can be modeled. That also will be having output. If the mathematical model and the system is same, exact, then the difference will be zero. In Kalman filter, we call that one as innovation sequence. So if the model is bad or the hardware is wrong, noise, the output will not match. So this is the fundamental principle of Kalman filter. So Kalman has done AI much long before. We are now giving some names and jargons. So I am trying to introduce that in my simulation model. So this is one of the techniques how your intelligence can be used by AI. You can have learning models also. Okay, I'll talk further. Next question, second.
Sir, this isn't a question. I just want to tell you that you show a slide of Quansar, this inverted pendulum.
Yeah.
So we are having that in our controls lab.
Okay.
So I am a PhD student from electrical department.
You have made that yourself?
No, sir. Like I have simulated few algorithms on that, but it is there for like
With
BTech
hardware?
lab. Yes, sir.
Good, I want to see that.
Sure, sir.
But I suggest you, he's there. Sir, one table, I'm not a company man.
Yes.
If you buy from them, you can compare your things. It's not that costly. I can help you also.
Sure, sir.
So that you see what is the difference. Definitely, I congratulate you what you've done.
Thank you.
Excellent. Bye. Others, I'll answer afterwards.
Thank you, sir. Thank you so much. Thank you.
And I give one copy to the judge. That is the main thing which you can read. Have you understood? Total avionics system is there. Okay?
course, a good afternoon because it has crossed 12. Yeah. Thank you at the outset. Okay. Done? Okay, it's okay. This is on? Yeah. Okay. Okay, okay, okay. Okay. At the outset, I thank Professor Sampad for this introduction, which was not needed to tell so elaborately. I also thank, this is an occasion to Professor Chowdhury, Shantanu Chowdhury, Director, to invite me to be here after spending 35 years at IIT Bombay. I joined in 87, I was there until 2021 December, and then I came here. Actually, I will be talking here today. Of course, it's very highly specialized topic. I am not sure of how much it will be appreciated or will be accepted by the students. It is very specialized topic. And at Professor Dr. Chowdhury talked a lot of things, but in control, as I am working on control system for a long time, I cannot get rid of mathematics. In control system, mathematics is there, and that I cannot avoid in this talk also. But still, I will try to touch some of the practical aspects of this technique. Before starting the lecture, I just give a brief introduction. The sliding mode control, those who are not in control field, that what is it? What is so much spoken? The sliding mode control, that is first invented in the then Soviet Union in 1950s, around, before 1950s, you can say little. The first time the concept was given by Utkin and Emelianov. They first gave the concept that stabilization of a system by discontinuous control. Nobody could think in that time, how a system can be stabilized, because system is continuous. All continuous, all plants, engineering plants, nuclear, power system, missile system, fighter aircraft, all are continuous system. So why deliberately you introduced a discontinuous? That is the thinking. First came in 1950s. Utkin and Emelianov, both are the originators. Those who are in control, they know Utkin is heard more. He is known more because he shifted from Russia, the then Soviet Union, to United States, and Emelianov, he stayed back in Soviet Union. And both the discontinuous control by applying, why the question can come, why did you apply, why do you want to apply the discontinuous control? Because discontinuous control has a marvelous property, that which has a robustness, which I am coming there, that one of the main themes of this talk, the robust property. It can reject the disturbance completely. No other controller can reject completely the disturbance. If the disturbance is entering through the input channel to the system, it completely rejected by the controller. That is a marvelous property. First conceived the idea. They both are very famous. Utkin got the Lenin Prize of the Russia, of the then Soviet Union, the highest scientific award. And Emelianov, he got the academician title, which is known as a cabinet minister rank in Soviet Union that time. So both are very famous. Last 2 years ago, Emelianov has expired, but Utkin is still there. He is more than 80, still he is working on sliding mode control. So sliding mode control started from Soviet Union, and then it was confined there for a long time. It did not come to the Western world or South or Asia or anywhere, until a paper came in 1977 in Control Transaction, that what is sliding mode control. And once that survey paper came, then the people wanted to understand what is it in English literature, because it was confined in the Russian literature. So first it came in English literature, and then the people tried to understand what is sliding mode control, what is so marvelous, what is this property, the robustness property, which is not spoken earlier in any control, optimal control, robust control, LQR control, state feedback control, pole placement control, that it is not spoken, such a robustness property. Then people try to understand, and it has become so important, and it has become so important, this subject, then it sparked off research all over the world. Like it went to USA, to Europe, Italy, Germany, all UK, and also Southeast Asia, the India, China, Japan, and all these things. A few years back, I was visiting one university, Central University in Japan, Chiba National University, and I saw one professor. He, of course, the Japanese, they believe on practice. He has made the heaviest robot in the world and the lightest aircraft, 10-gram microaerial vehicle, Professor Nonami. And I found that he has written a book on sliding mode in Japanese. He presented me that book, and I was very thrilled that sliding mode control has gone. And the subject is so important that IEEE Control System Society, it recognized. And within IEEE Control System Society, they made the subject is so important, a technical committee on variable structured system and sliding mode control. I happen to be from India in that committee, and that committee is responsible to hold a biennial international conference, you can tell. They call workshop, but it is a conference, once in a 2 years. And actually today it has ended. I was supposed to go to Rio, and none of my students and myself could go because due to the corona. I heard the Brazil is highly affected by corona. So today it has ended. It happens once in a 2 years. So 2022, it just concluded yesterday, the IEEE workshop on variable structure system and sliding mode control. And I'm also very glad to tell that India, the first time, it was conducted in IIT Bombay in 2012. And 100 people came from, it's not a very big community, but all over the world, around 100 people are working on this topic. Many of my students, they have done PhD, and they are on the IIT faculty, different IIT faculties, and they are working, and they have done also very good research in the last few years. So this is the background. Here I will be talking on continuous integral sliding mode control. Why such another adjective has come, continuous integral? That is the thing that, and these two topics, continuous integral sliding and implementation of sliding mode control. The second order sliding mode, it has some name that the super twisting, which I am not going in details here, second order sliding mode control. Now, to understand the sliding mode, let's say this is a system, simply, as Dr. Chaudhary was telling, the plant state equation. The first order plant with disturbance, and disturbance is bounded. Then those who are working on control system, no other control can stabilize the system at x is 0, except a discontinuous control. No other control. Whatever control you have learned, those who are working on control system, it cannot stabilize the system unless there is a discontinuous control. This pointer, we have put the dongle, no? Pointer. No? It is not working? Yeah, I have another. It is not working. No, pointer. You see? This, yeah. Why? It is.
And slide changing from.
Now that I know, the pointer. Where? It's coming?
Yes, sir.
Where?
Laser right.
Huh? It is there?
Yes, sir. Just putting.
Okay. Anyway, I just. This controller that the X is, that this is the plant and this controller, the X is 0, it is stabilized by applying some discontinuous control, which is this control, KSGNX. By applying this control, it can stabilize the system. But the greatest drawback that it was going on for 30, 40, 50 years, you can say, that the sliding mode control, that discontinuous control, it works in practice very nice. There is no issue. I'm sorry. It works very good in theory. I mean, exactly it cancels the disturbance and exactly it slides. There is a sliding mode, which I'll be talking later, that it exactly slides, and when it slides, it is inert. It doesn't care about what is the system parameters in the plant, uncertainty, disturbance, nothing. It is governed by its own dynamics, the sliding mode dynamics. So in theory, it works very nice. But what has happened, I mean, in mathematics, it works, it slides by using the switching control. But in practice, then after the invention, and it was going on several years, and then the aerospace engineers, the mechanical engineers, they jumped at, and they tell that this works in practice, but it doesn't work it works in theory, but it doesn't work in practice, because no actuator can act with infinite frequency. No computer can compute the control with 0 time. So there is a little delay in the computation. There is a little delay. For example, you want to apply the control in an elevator, in a fighter aircraft, or a pin in missile, or in a nuclear reactor, in a valve. So there are mechanical devices. So discontinuous control, when it is applied, then it gives a property, it gives a result called the chattering, which is very dangerous. So this is the limitation. It was going on last several years that it cannot work in practice. Although there are certain stopgap, certain manageable results are obtained using this sliding mode control, and then the discontinuous control has been implemented in practice. But what has happened, fortunately, after the Utkin and the Emiliano, in the 80s, I think, late 80s, and the first paper came in early 90s, there is a researcher, very seminal result he has brought, and he has shown that by retaining all the property of the first order sliding, you can make the control continuous. And that is known as the second order sliding mode, which I will be touching here today. And that has become a very hot research topic. And the last 20 years, you can say 10,000 papers have come on this topic only. Differentiator, Levant, his name is Levant. He was in Soviet Union, his name was Levansky. Then he shifted to Israel, and his name is his father's land, and they call it the Levant. So Levant differentiator, Levant second order sliding mode, Levant observer, they are very famous. Research is very going on, and there are very successful implementation. I will just mention here, why did I bring that topic here? I will show there are certain wrong concepts which was propagated since last years, which we have corrected. And what is that? That I will be introducing. And also the discontinuous control, that U equals to this control, the discontinuous control, what is the problem in practice? So this is a discontinuous control, and if you apply here, then it rejects the disturbance, and X is 0 in finite time. And similarly, the second order sliding mode, that the control is a continuous. This is the difference. This is the control is discontinuous, here the control is continuous control. And continuous control, it also rejects the disturbance. So when you close the loop, then it becomes like this, and then it becomes further this, and then it is shown that X and Z go to 0 in finite time while rejecting the disturbance. And the advantage is that both are rejecting the disturbance. Here the advantage is that this control is a continuous control. This is the famous result, which is around, you can see the 10,000 papers have come. Second order sliding mode, that this control is applied to the system. It rejects the disturbance, and it is a continuous control, unlike in the traditional sliding mode, which is a discontinuous control. So this is the thing. So here I will show, because this is the way the disturbance is, disturbance observer, it is called sometimes. So the disturbance D is minus V and V is this. Now, let us consider the chain of integrators. You are familiar. The double integrator, triple integrator, chain of integrators, which x1 dot is x2, x2 dot is x3, xn minus dot is xn, and the last state, I'll also show the more general case, the last state is affected by driven by the input. And then there is a very famous result, and what's the drawback of this result, and how to take care of this result using this our new theory. This control, this plant, if it is, this is the control if it is applied. It is a continuous control. It is very famous, the Mott and Bernstein control. This is known as. So this control, if it is applied to that chain of integrators, then x1, x2, xn, all the states go to 0 in finite time. That is the advantage. Again, this is a very highly cited paper in Science Journal, Mott and Bernstein. So this continuous control, if it is applied, but the problem is that this control, for example, I wanted to show with the second order, double perturbed double integrator which is affected by some disturbance, then this control if you apply with this integrator, then what is happening? This is the control for second order, and then this control, the nominal control, then if there is no disturbance, then it is stabilized in finite time. And the control is also continuous, no issue. But the thing is that if there is a disturbance, if you consider, then it doesn't get stabilized. That the second order integrator, similarly third order integrator, fourth order or higher order integrator, if this continuous control is applied and if there is a disturbance in the system, then it doesn't get stabilized. This is the problem. Then what has been done, that there is a concept came again given by the Utkin, and which will show the modified version of that, which is that's what the title reflects, the continuous integral sliding mode control. The integral sliding mode control is actually there is a two control. There is a nominal control and there is a discontinuous, which is integral sliding, which is proposed by Utkin. And idea is that a sliding mode starts from the initial point, and when there is a disturbance acting on the system, the second component of the controller, it rejects the disturbance, and the closed loop system is governed by the nominal controller. So you can design a very nice controller, linear, quadratic, optimal, whatever you call. But this controller, if you apply alone, then if there is a disturbance in the system, it doesn't get stabilized. But with that, if you add a discontinuous part, which is termed as the integral sliding, because the surface is I will show that surface, which is sliding surface, is not a linear, it is an integral of the difference between the actual state, disturbed state, minus nominal state, projected along a matrix G, so that the sliding mode starts at initial time. And whenever there is a disturbance, the second component works and it rejects the disturbance, and it exactly slides, and it is governed by the nominal control and by the nominal system, and you get the exact behavior which you are designing by applying a nominal control. So this is the thing. So if the discontinuous control, that's why integral has two components. The nominal control is designed for the system without disturbance to have a desired trajectory. The design U nominal and U discontinuous are completely independent. It may be noted that equivalent value of the discontinuous control is the negative of the disturbance. And that's why when there is a disturbance and you apply the second component, it completely rejected the disturbance. So this is that U discontinuous is this, and then this is the surface, So when the system is on the sliding surface, the equivalent value of the control is calculated by substituting the derivative of the sliding surface. So U discontinuous becomes minus D. That is the property. The discontinuous control, its value is the negative of the disturbance. And that's why whenever some disturbance is acting on the system, it rejects the disturbance, the discontinuous part. And when there is no disturbance, then it exactly slides. And that time, the system is governed by the nominal control, and you get a robust and optimal behavior. That is the idea which is again proposed by Utkin. But then I will show what is the drawback. Again, in practice, the discontinuous control can introduce the chattering. I have certain videos also which is implemented this control and the proposed one, and then I will show what is the difference that will be more appreciated than the simulation. So this is the, now with discontinuous control, the S dot, so this is, it cancel, that's why when the system is on the sliding surface, the value of the disturbance and it's cancelled out, but it can clearly be observed the original control which is applied to the plan also contains a discontinuous control. So when the system is on the sliding surface, then the control is calculated by substituting this. So what is happening, that this is the problem. I'm mathematics part, always you can understand from our papers, and several books are there. The dozens of books are written, thousands of papers are on this topic, so there is no issue. But the problem, this is the situation, that when you have uncertainty in the system, and then you apply the nominal plus a discontinuous, then the states are stabilized in finite time, but the control is a discontinuous control. So which is again inviting that kind of issue, the chattering issue, and the aerospace engineers, mechanical engineers, when there is an actuator, a mechanical device, then it is a problem due to this discontinuity, and this is the control. So what we have shown here, that the second component, if it is replaced by continuous SMC, which is termed as the STC, that is super twisting. Why the name has come, that's a different, the trajectory is twisted. So the second order sliding, the Levant has given two names, a twisting control and a super twisting. Twisting, once twisting takes the derivative x and x dot, and super twisting, it doesn't take the derivative. That's why that adjective, another adjective has come. Anyway, these are all second order sliding mode. So this is that control. STC is this control, and this control if you apply with this, again you consider the same system, and then with this control if you write the closed loop system, then it becomes this, you see. The states are stabilized and the control is a continuous control. Because in the second component is not discontinuous. This is the second component. This is the second component. You see, this part is continuous. Not Lipschitz that S is 0, but this is a continuous signal. So this continuous signal, it is stabilized and states are stabilized and the control is a continuous control. So this is the thing. So this, again the chain of integrators, you take the second order and this is the surface, then this is, it is more general state space model which has been implemented. This idea, consider this system in a state space, D is the uncertainty, nth order system, A, B, C are the matrices, and the control, there is a nominal control which you can nicely design using linear quadratic control or any other PID control. As last month some professor came, he talked on the PID. The industrial controllers are all PIDs, 80% controllers. So any controller you design which has a nominal, U nominal control, and U STC, which is the second component, which is a continuous control. So these two control, when you apply to the system, then it gives the optimal behavior, and at the same time the disturbance is rejected by the second component, which I have explained. Now this is the, because that this system, because the which I have told, and this is the surface, that xt, and this is the second part within integration, that is the nominal trajectory. So the error between these two trajectory projected along the matrix G, the advantage of so choosing the sliding surface, that sliding mode starts from the initial time, unlike the traditional sliding mode. And then it is shown that S dot, if you write all these things, then the U S dot equivalent value can be obtained by setting S dot is 0. So what is shown here, USTC is minus T. So it rejects the disturbance. So this idea, I have certain videos which I will show that this is implemented on a emulated system. It has a drive disk and a load disk, and it emulates the behavior of the drive disk to the load disk. So it is first is the rigid plant, rigidly they are tightened by rigid belt. So whatever is the dynamics, whatever way the drive disk rotates, in the same manner the load disk rotates. So there it is implemented, and then there is some flexibility is introduced. Like with a pulley, there is a flexible belt which is connected, not directly, the drive disk and the load disk with a flexibility, some flexible belt, and then complexification has been done for the system because the vibratory modes are created in the system. There are infinite modes, but I have taken just one mode. And then I will show the application of continuous only linear quadratic control. What is the applications of continuous integral sliding, the proposed one, and also the discontinuous control proposed by Utkin. What is the difference in practice? So these three, so these are the different designs, not very important. These are the simulation results, but it will be interesting that if I show the, before going to the next topic, if I show certain video, that will be better. That first is the rigid thing, in that that only linear quadratic control is applied. This is the drive disk and the load disk, you see. So what is the meaning of this? That this only linear quadratic control, and some uncertainty is introduced in the system entering through the input channel, which is known as the matched uncertainty. And this uncertainty, you see, the disk is not, the load disk is not settled in that particular degree. It is rotating. That is the meaning. I repeat again. That means it is not getting stabilized. So that only linear quadratic, if you apply, then it does not get stabilized. Now let's say the discontinuous control, the second one. You see, this is not much visualized, but it will be more prominent when there is a flexibility is introduced in the system. But there is a chattering. That is that practical phenomena. It chatters, but it's tried to settle in that, in this 60 degree that that is designed for this, but discontinuous. The nominal control plus a discontinuous control is experimental results. So there is a chattering, but it rejects the disturbance, but there is a chattering in practical system, in a practical case. So it is shown. Now the proposed one, that second component is a continuous control. Then you see the difference. The drive disk, load disk, you see, it almost rejects the disturbance. This is. There are certain talks are going on in the sliding mode community that second order, although the control is continuous, but within the control there is a discontinuous term, that which I have shown the second equation. So there are frequency domain analysis and all this thing, it has been shown, still there can be some chattering. It's a very recent discussion. So that's why initially we are all telling that chattering is completely alleviated, but it is not completely. There is a less chattering, but chattering will be there because within the controller there is a discontinuous term. So that is, I am not going in much details, but this is better than the conventional. Now, it will be more prominent if there is a flexibility is introduced. And then I will show that the flexible, you check again the linear, only linear quadratic. This is the flexible, they are connected with a pulley and some flexible belt. So it introduces complex eigenvalues to the system. So you see as there is no second component, so the disk is not settled at that particular set point. But if you apply the discontinuous control to this system, then what is happening? It will be more prominent because there are complex eigenvalues. So this is the challenge. It's tried to settle at that set point, but due to this second component is the discontinuous control, it does not. This is a challenge. It's a practical phenomenon. Theoreticians, they did not consider first 30, 40 years. Because in mathematics, there is no issue. It doesn't give this kind of, it's an equation, an exact Filipov solutions that is called. There's a differential equation which is different in sliding mode and what you understand in physics and general control system. There's a differential equation, right hand side is continuous. So by ordinary differential equations theory, you can solve this system. But in the sliding mode, there is a dynamics and the right hand side is discontinuous. So another new theory was proposed that there is a solution for that equation, continuous solution. That is known as the Filipov solutions. So solutions in the sense of Filipov. Filipov has given a method, is a complete book is there. Discontinuous differential equation. If there is a differential equation and there is a right hand side is a discontinuous, then there is a continuous solution. That is called the Filipov solutions. So that solution doesn't have any chattering. Theoretically, there is no issue. It exactly slides and there is no. But in practice, so chattering, people should understand that the chattering, those who are working in control or in sliding mode, the chattering is a phenomena, is a practical phenomena. It does not exist in mathematics or in theory. But when you apply a discontinuous control, it gives this kind of phenomena. And then what I have shown here, that if you apply the second component, if you replace by this second order sliding mode control, that is the contribution, then you see everything is the same. The linear quadratic, the nominal control is the linear quadratic control, and the second component is the there is no chattering. That is, I will show again. So the second component is that when you apply that the second order sliding mode, this, it settles at the set point. In practice it happens. So first component is the linear quadratic control, and the second component is the continuous control, sliding mode, which is proposed by that, second order sliding mode or super twisting control, what you call. So the disk is settled without any chattering. So there are successful implementation. I met one researcher who is working in Bosch company. He says that in piston control system, this has been implemented and which may be marketed. I'm not sure of whether it has come in product. Because sliding mode, that was a lacuna for a long time. Because they are discontinuous, like in Professor Dr. Chaudhary was telling. There are missiles, although one of my students in DRDO, scientist Pune, he has done everything, sliding mode in missile, but as he may be knowing, there is an old mindset. He doesn't have that mindset. He is very open. Any controller he admits, he tests on hills, but there is a mindset that classical control is working, let it work. That gain margin, phase margin concept, gain scheduling concept, it is working in practice, let it work. 30, 40 years, if I'm not very wrong, Dr. Chaudhary knows the missile control system, entire thing is based on classical control. But if you convince them, I'm telling they are better. There are scientists and academicians who should not be blamed. They should not be blamed. Academician should not be blamed. They should come close together, as I have tried to come close together. One of the students, Dr. Parkhi, he is a scientist, high-level scientist in DRDO. He completely worked on sliding mode in missiles. But of course, I am not sure of whether it has gone to the end, the final point, whether it is implemented in practice. Because, as I told you, that all those who are designer, they are working on this PID or gain scheduling, and the missile is working. But one has to convince them that this is better than that, better robustness property, better control, better rejection of the uncertainty, better performance. One has to convince, and then I am sure, because Israelis, they are doing, they implemented the sliding mode in practice. So this is the first part. Then second part, also very interesting, which I will discuss another new results, that is the implementation issues, a wrong concept which was going on for a long time, which is corrected in these ideas, in this paper. After this, or okay, you can ask. Okay. Just.
One is, when you are switching from one controller to another controller, there is a delay. Will that delay not cause problem?
Yeah, I'll tell you. You have correctly told, but that's the issue. That is the correct issue. That in practice, that when you switch, there is a delay because your control is not ready. I'll just show it is happening like this.
I hope students, your understanding is
No, I understood. I'll tell you. What you are telling. Oh my, just a minute. I'll show you, as you have asked a very important question, so I'll try to answer a little elaborately. What is happening? Let me just check.
I hope, Chairman, I'm not disturbing. I thought it's important.
No, it's okay. Just, I don't know what has happened. Just a minute. You can close this thing. Close. I'll just open with the Zodo. Okay. Close. Why it is not closing? It's okay. Close it. No, let me check. You close it. Whole thing. I will close. I'll open again.
Just a moment.
Close completely. Close it. Close this file. This file you close.
Yeah.
Completely. Close it. Yeah. Let me check. Yeah. What you are telling, that is the most important question that, I'll just show that this is, let's say, this is the sliding surface. This is the sliding surface. and when the trajectory hits here, then it measures the S and then it changes the control. And the moment it is about to go to the other side, then the control forces the trajectory to go this side. And then when it crosses, then the control changes. That's why the switching control and sends the trajectory in this side. So this is the, but in practice, in theory, in the Philipov solution, we do the infinite switching, infinite time, which cannot, a practical actuator cannot do. So that's why it exactly slides, it exactly slides in this particular way. I'm sorry, it is not horizontal, this way. It goes along this line. Exactly. But if there is in practice there is a delay, then it crosses it. And then by the time you compute the control and the actuator acts, the trajectory crosses this sliding surface. And then it delays and it comes here. So this comes here. That's why this is all about 30 years going on, the chattering. This is chattering. So chattering occurs in practice. But mathematicians, control theoreticians, sliding mode theoreticians, they will not, they didn't go by that. It's okay. It exactly slides, and that is that Philipov solutions. A differential equation, right hand side is discontinuous, and it slides along this, that exactly slides this in this line. I mean, this is not curved, it is exactly along the line. But in practice, there is a delay, and that is chattering, and that's why all these question issues came, the second order sliding. So this is the what is important.
Thank you, sir. You can carry on your thing.
Yeah.
I'll ask other things afterwards.
Yeah. So I'm coming to the second aspect, second part of my talk, which is implementation of the second order. So there is a wrong notion which was going on, which I'll show why that is wrong and how that is corrected. Consider again a perturbed double integrator. And you want to control this system. x1 dot is x2, x2 is u. And if there is a double integrator ideal, there is no uncertainty. If there is a perturbed, then uncertainty u plus rho 1 is bounded. And the output is a generic mechanical system. The output is the position, because you do not get the velocity, you do not measure. So the position, if you want to control the second order system, then you cannot do, because the relative degree of the system is 2. So you cannot apply that so-called that super twisting sliding mode, which is valid for relative degree 1. So it's a relative degree 2 system, so one has to design a sliding surface, which is done here. This is the, so first construct the other state, and for that you need a observer, and this is that, the sliding mode second order that can act as a controller, that can act as an observer, that can act as a differentiator, which is the remarkable result. That earlier there was a notion, there was a concept, differentiator is not encouraged in control system because it magnifies the noise. But after the invention of the Levant differentiator, it has been shown that is the closest, it respects the Kolmogorov bound of the differentiator. So this differentiator has been used in practice. It doesn't have that noise problem. So the same algorithm is used in all the three purposes. So first of all, an observer, second order observer is proposed, and then the x2 is observe, and then again it is shown this observer error, this is the error, and if the uncertainty is bounded, then the error, these are universal formula, the k1 and k2 is the uncertainty, and the error goes to 0 in finite time. So x2 hat, which you are observing, the velocity, which estimates the x2 exactly after finite time. And then what is important here, I wanted to tell here, that this relative degree 2 system, so therefore one cannot apply that STC directly, so one has to design a sliding surface, that S hat, which is C1 x1 plus x2 hat, because x2 hat you are not measuring. It is coming from the observer. That's why x2 hat. And the moment you do this thing, and then this S hat dot and x1 and S hat dot, if you write this system, this equation, then what is shown here? This equation, the observer and controller together, then x1 dot and S hat dot is this, and this is the controller, then this is the closed loop system. Then this is the observer part, this part is the observer which goes to 0 in finite time, this part is the observer, and then when this error goes to 0, then this first equation, the plant equation, in the coordinate of x1 and S hat, that becomes, I will show, that becomes this equation. This is discussed that the observer error goes to 0 in finite time, and then finally what is happening, that this is the system. So here is the catch. At least the Mohit will be able to tell, who are working on sliding mode, that this is the problem which was first observed in 2014, I think, at IIT Bombay, that there is something wrong here. I want, if somebody can tell, at least control researchers, what is the problem here. The super twisting or second order sliding mode is not enforced here. There is a mathematical incorrectness which is pointed out. Also a paper you can check, it is in last 4 years more than 350 times cited, all by others, most of them, 95%. So this is the work. So this breaks down. What I will boil down, I did not discuss much on mathematics, that there is a double integrator and you have to control, so relative degree 2, because y is the output, the position. And the relative degree 2 system, if you have to control, then you have to design a sliding surface. And sliding surface, you need the x2 hat. And x2 hat, when you design from a second order observer, and then if you plug to the plant and the controller together, then the closed loop system becomes this. x1 dot is this, S hat this is this, and L is this. And then this is the point, this is the result where it shows that the second order never begins in this system. Why? This is the reason. Then how to mitigate, how to resolve this issue. That if you have a second order controller, second order observer, and a second order plant, then what is happening? That last two equation, which is that actually those who know, others cannot much tell, those who know the sliding mode, the second last two equations, that is the closed loop system for the, by application of second order sliding mode control. Here sliding mode is not enforced. Why? Why? The reason is that the S hat dot term contains a non-differentiable term. That's why it cannot be shown S hat and L go to 0 in finite time. It cannot go. That is the problem. That's why the conclusion is that a second order plant, perturbed plant, if you control using a second order observer and a second order controller, then it doesn't, mathematically it is incorrect. But people are doing this thing, where before this work, people were doing this kind of, because in discrete, what you do, discrete implementation. So even in a discontinuous term, if you discretize it, sampling time, it will give some values, and that you can, use it. So what is done here, which I will quickly, that it is clear the mathematical transformation by selecting STO, so that is observer, to estimate the state of the second order uncertain system, and then second order, then this following standard way of STC application, sliding manifold, the second order sliding mode never starts. That is the conclusion. So how to take care of this thing? That is I am discussing. Because that what I told, the S hat dot contains the non-differentiable term this, which prevents the possibility of lower 2 subsystem to act as a super twisting. Whenever it starts, a second order sliding. So what has been shown here? This is the block diagram of that. This is the plant. This is the observer. This is the surface, and this is the controller. It's a block diagram representation. Then is to design U such that the second order sliding motion occurs in finite time. So one of the remedies that you propose the controller like this equation 40. The C1 x2 hat minus K2 this minus this. And then if you apply this control to this system, then it has been again shown that this is the 0 in finite time. So this second, last two equation again, a second order sliding mode takes place, S hat and nu go to 0 in finite time, and when x1 is minus C1 x1, so x1 is asymptotically stable, and x1 and x2 are algebraic, so x2 is also asymptotically stable. But what is the problem then? The very purpose is defeated. Why? You look at the control. This way, if you propose the control in this particular way, this control, then it can be done, it can be solved to some extent. But the very purpose is defeated. Why? Mohit can tell. If you propose this control, I am again repeating because little bit better to explain, that this control, that if you have a system, double integrator, x2 you are estimating, S hat, it is an estimated S hat, and then this control if you apply, and this control if you apply to this system, then this closed loop, it becomes, this is the system. And here there is no issue. In this part, there is no issue here. They go to 0 in finite time, and then the x1 stabilized. But the very purpose is defeated. Why? Anybody can tell, at least control researchers. Why? In this control. What is the problem in this control? This control is that again a discontinuous term is introduced. Then the very purpose of second order sliding mode, that the continuous control you are looking for, that is compromised. So really it doesn't serve the purpose. That means if you apply the discontinuous control again, that K2 is Gn E1, which is discontinuous. So control is discontinuous. So which I try to avoid. The whole proposal of second order sliding mode is that. So it really doesn't serve the purpose. So what is the invention here? That one has to, so stabilization of this x1 and x2, which is done here. So this is the discontinuous control, this part. That is second order plant, second order observer, surface, control, but it has a discontinuous term here. So it breaks down. So what is that? Similarly, the output feedback control, that is the way, if states are available, then you do construct in this way, and then, this is the control, and you just simply S you replace by S hat, and then you do. But thing is that in output feedback control, you are assuming the states are available, which is not the situation. So what is the remedy here? That this is that if we use STO to estimate x2 hat and using it in control by replacing x2 with its estimated value, then control input becomes 47. So U is this, but then the control is applied, it is not possible to SO, which you have discussed. That this way, that if you x1 and x2, if you take and if you constitute the control, and x2 hat if you estimate, then we have seen mathematically it is incorrect. So now what is the solution is, this is. Now what I am trying to show in the last part, that if we use this method for practical implementation, it may work. Why? Because most of the time, controller implemented digitally through computer. It means that controller is implemented at some fixed sampling time, so the value of the discontinuous will be constant, actually, in implementation. That's why you get some value, and that you implement, and you get some results, and one is excited, oh, it is working. But there is a shortfall. It is not correct mathematically, that I have discussed. Now, what has been done here, that for a second order, that is the observation here, which I was talking about the paper in IEEE transactions, that this one has to resort to a 1 more degree higher observer. Like if you have to control a double integrator, you have to go for a third order observer. If you have to control a triple integrator, you have to go for a fourth order observer. You have to control an nth order integrator, then you have to go for n plus 1th order observer, finite time observer, again proposed by the Levin. So that's what it has been shown. If you consider a third order observer for the second order plant, and that problem will not come. That means that non-differentiable term in the controller expression will not come. So which is shown here. So this is that observer goes to 0. Again, then this is the controller, this is the nth order observer, third order observer, this is the error, this is the third order observer. Third order observer, and if K3 is greater than derivative of the disturbance, then all error go to 0 in finite time. So this is the third order. Similarly, fourth order observer, fifth order observer, all higher order observers can be proposed. So in this case, when you are talking about a second order plant, then one has to resort to third order observer. And which is this? So controller and observer together, that if you write, these are the error, and this is the, again x2 hat, you are taking from the observer, then this is the x1 dot plant s hat, and this is the controller. Now see, this control is continuous control, and this, if it is implemented, then what you get here, that this is the control system, and this is the observer system. They go to 0 in finite time, and then if they go to 0, then this goes to 0, and then you get this kind of equation, that this is the plant, and then E1, E2. So this is the lower two subsystem again, that there is no such problem which we have encountered when you consider a second order plant and second order observer. Second order plant, third order observer, this is the closed loop system. So S hat and V go to 0 in finite time, and then X1 and X2 are stabilized. So this is the result in these ideas. So this is the block diagram representation. This is the plant, this is the plant, this is the observer, this is the surface, and this is the control. So this control is a continuous control. So this is so what is the conclusion is that above observation, that sound mathematical analysis reduces the two gain condition with respect to disturbance by simply one gain condition. In this implementation using a third order observer, only you need a gain condition here, that this gain should be more than the derivative of the disturbance. But in controller, no such explicit gain condition is needed. You see here. Any lambda 1, lambda 2 greater than 0, it is not related to disturbance. If you implement a double integrator, a third order observer to a double integrator, no gain condition. So even if you implement, wrongly, then there are two gain conditions are needed. One is dependent on the derivative of the disturbance, another is dependent on the disturbance bound. But here it is not. Only the observer gain is dependent on the derivative of the disturbance. So this is then certain simulations are discussed. So yeah. This is another is the precision. One is the mathematical correctness. Second is the gain condition, it reduces. Another is the precision. Precision is here better. Why? Because when you are using a third order observer, then the precisions in the sliding surface, sliding variable is one level higher than only the second order thing. So what it means, due to the increase in the precision, states are also much affected. So if you talk about the stabilization, in other words, if we talk about stabilization problem, then states are much closer to the origin in case of higher order SMO based STC than STO based STC. Because here is a third order observer, so x1, x2 in a discrete manner, the precision is order of tau cube, tau square and tau. So the precision in the S hat is in the order of tau square, and which is more than STO based STC. So this is another advantage. So these ideas is implemented, and it has been shown in the zoomed version also that this is the output, ordinary way, and this is the higher order observer based controller. Here in the scale, this precision is high. This is the position, simulation results, this is the experimental results. Similarly, the estimate x2 and the experimental results. Similarly, all these the error in the estimates. So I think this is all about my talk. I'll be happy to get a few questions. I wanted to know who are working on control system. Can you raise so that I can get an idea of the audience? MTech or PhD? You two, of course. This Gaurav is 3, and so I'm sorry that the topic is such that it might not have gone to the others, because others are not control system students.
But I think it's very important that, whether you have understood or not, but that control is something which is very, very crucial. Whenever you talk of any system, control is one of the most important requirements, and if you are able to control the things precisely, that's where he was talking about precision.
Yeah.
So precision in control is again very, very important. So I don't know how much you have understood or how much I have understood, but at the same time, this control aspect, whenever you talk of any equipment, any system, any machines, and particularly when you are talking of missiles, Dr. Chaudhary spoke in the morning. So that's what is very important. So maybe theoretically, yes, it is difficult to get on, but practically, control is one of the most important aspects. So thank you very much, sir, for your,
Thank you.
yeah.
Yeah, tell, please.
Student community. Hello, sorry for interruption. He's my friend, and I have learned a lot of things from him. We
Tell, please.
listen each other. Now, one point he commented, we are not using only classical control. You're wrong, sir. All the Kalman filters are there. Kalman filter is part of the.
No, I'm telling the closed loop control part in missile.
Hold on.
I am not telling the estimation part. You applied Kalman filter. I
See,
agree.
Kalman
I admit. I am
filter-
telling that feedback system. What I have learned, I don't know the confidential thing of the defense.
But one thing I want to comment. If I
No,
can,
I'll be happy to know if there is a robust control is applied in missile. I
no.
understand there is a gain scheduling, there is a 3-loop structure,
Sir,
and you change the controller,
I'll answer this.
and it follows the trajectory.
Sir,
This is my perception. I may be wrong.
No. One more thing. So we are using.
And I am not blaming to scientists.
I'm just.
There are
I'm
300
just telling-
scientists in each
See,
lab.
we
They are
found-
good, all knowledgeable.
No,
But what I am trying to tell,
this debate-
even I will give you an example that I was supposed
No,
to
you
talk.
give
No,
me-
just 1 minute. There is a nuclear, other day Professor Chidambaram, they talked on the nuclear plant. Again, last 20 years, we have done the modeling and control of 2 reactors. And that is what he was telling, the pressurized heavy water reactor. And first time, with my PhD students, Dr. A.P. Tiwari, we have made a model of that system 70th order. And then it's a stiff system, singularly perturbed system. All investigations have been done. composite control, sliding mode control, output feedback control, and he is now associate director. He implemented this control in a test bed reactor. Reactor is a computer and all the hardware is the control. I mean, control is the hardware. But then when it goes to the practice at Tarapur, which is producing 540 megawatt, there are safety commission, this commission, that commission. There again they return to PID control. They did not dare to implement this model. I'm not blaming them, nor my student Tiwari. So this is the scenario what Professor Bhattacharya was telling last month, that it is their mindset. And I'm not blaming nuclear scientists or missile scientists, that you have
he was given the platform.
The academicians are to be blamed.
Implementable control.
Because he always admits. Anybody I have sent to students,
give me 2 minutes.
He shows the hills in the hills hardware in loop simulation, and it works there. But it doesn't
just
go to
give me
practice.
2 minutes time.
Yes.
Please complete your comments.
Just I'll answer. DRDO don't think is not using modern control, but they are not solving the equations online. We solve it offline, and the gain schedule is based on that. The reason for this, which Bhattacharya could have mentioned, the plant changes depending on the velocity. So the plant is changing. That's mean each controller after a particular height is different. The first missile fell down because of height. There is a difference of 10 kilometers. So the gain schedule didn't work. Myself and Kadam has worked on that. So after I gave him proper height with estimation, then the control system is working. So gain schedule is based on offline research. So gain schedule is nothing but we are using the computer system to make the gain accordingly. So what he is telling, as I understood, we are estimating not position alone. He told that x dot is estimating. If we know the velocity and the acceleration and the jerk, any physical system, you please teach me, sir, anybody, that any position can have a velocity, can have an acceleration or a jerk. More than that, I don't know. So these three are there everywhere. And today with the navigation sensors, when you go to control, I have seen in NASA I was called to solve that problem. My friend, I'll bring him sometime, Menon. Menon is a good theorist and very good engineer. He worked in NASA, he took me. He showed that all their controls in NASA with those GPS and all, whatever is available, or the INS available of the cell, are giving that jerk problem. So first thing I told him, remove by analog thing. Because analog is online. He was able to remove and he thanked me. I just told him, you see, it will not affect. Like he was showing small jerks. So that can be attempted. But that can be found out by your analytical method. What I say, sir, please explain the students, because you are a teacher.
Yeah.
I'll help you. Sir, solve that problem offline, but give the gain online. That's what is my point, nothing else. I thought then we can work better.
Okay.
But we have to keep in touch.
Yeah, thank
Have
you.
I given the message?
Thank you for your comments.
Thank you, Dr.
Thank you.
Kadri. Yeah. Any questions from audience? Anything? Okay. If no questions, I have pleasure to present moment to. Yeah, absolutely. That's what you told is one of the most important things, and we are also focusing at IIT Jodhpur on the experiential learning. So we are more having lab component, hands-on components. In the hands-on component also, group of 2 to 3 or 4 students, they will think of not that research problem, but they will think of something making new by using theory, whatever theory they have had. So many times we read the theory, but then how to use the theory, and when you go to the practical aspects, you will discover many things. So that is where the experiential learning will help a lot. So that's very important. Experiential learning you taught in the morning, so I didn't want to go more detail into it. But definitely, as he explained from, that how kid learns the things, so how we grow and we learn the things, and more importantly, our observations are very important. One is we observe the thing, and two is we analyze the things. So not only that we observe, we see the things, but then we need to analyze the things. If we observe and analyze, then we'll try, many things we can discover. So something X person sees and Y person cannot see, the bigger difference is that only that somebody observes, sees the things, but another person sees deeply and analyzes it. So that analytical part is very, very important. Yes, sir. Absolutely. I fully agree, and I think this is a good lesson for all the young students, that observation and analysis, these are two parts. Not that simply you observe it, but you analyze it, and once you analyze, then try to understand the kind of problems you have.
Because you have
Because
a
problems can result into challenges and then opportunities and all those things.
yeah, Bandhavata
So very
continues with
important
you.
is observation and analysis.
Yes.
And everywhere, whatever you see, whatever, wherever you are, you can do, in whatever work you are doing. So that's very, we had really, really very, excellent talks by very, very, I would say, renowned people, luminaries in the subject. And I have pleasure to, present memento to Professor Bandhavata. With this, we come to the end of this very special session uh, on control part, on software part. And thank you for being with us. And please try to remain similar way in other sessions also. And you will be having lots of, I think next session is related to quantum technology. Two talks will be there. One will be from IBM and another will be TCS. So, they will be going to be again very interesting talks. So please participate and try to make use of this opportunity as much as possible. 2 o'clock. So we break for lunch and then we will be coming back here at 2 o'clock. Thank you. Thank you.
Thank you. Thank you all.
Students, stay back. Stay back. Students, there's something for you. We have to give it to you. You please stay back. The guests will leave the room. The coordinators will give you something, so please stay back.
Yes. Thank you. Yeah. No. It's that brain tree of IIT Jodhpur, isn't it? Yes. Very nice, that tree I have seen. Always I.
Made by
Made on this camel bone.
Oh, camel bone. Nice.
artisans of
Yeah.
IIT Jodhpur.
Yeah, they are a part of Jodhpur City Knowledge and Innovation
Oh, very good.
when I saw their,
Actual camel bone.
yeah, when I saw the things on exhibition, then
Yes.
when I saw their things, why don't you make this?
for carbon dioxide conversion into hydrocarbons, so making these process engineering more efficient, making better financial models, more stable and more real-time financial models. Or, with COVID, something got very, very relevant to us, that building an antibiotic or building an injection, a dosage of this vaccination that you guys got. Normally, a vaccine would take some 28 years to get delivered, right? Why is that so? Because a chemist has to sit in a wet lab, do all those experiments one by one, understand, what works best with the particular virus or bacteria in question, and then come up with that particular pharmaceutical, compound. Versus if we have supercomputers, and this is what we did with Summit, which is one of the supercomputers at IBM, and we were able to shortlist the number of chemical compounds to some 64 within 8 days. Now, 8 days is also a lot. Can we do even better? Now, the world's largest supercomputer is still taking 8 days, is not a great sign for, computer scientists, and the progress that we have been able to make. So why quantum? So in the center you see a white ellipse, which is problems that we can adequately answer today, right? So problems like sending emails, doing a class on, online, or doing, streaming a video and so on. We can do them seamlessly, classically, and we really don't need any further resources to do that. Then you see the sky blue area, the larger ellipse, that is problems which we cannot adequately answer today. For example, in some of them you need large amount of data, or in some you need huge amount of computation time. And most cases you need both, right? You are ingesting large amount of data, you're training it for days or hours together, and typically machine learning is one of the biggest thing in this sky blue area. Okay, wherein deep learning consumes huge amount of data and takes in a lot of energy also for all of these GPUs to continuously function. But the interesting part is this dark blue part, right? So there we are seeing, so it's not like quantum is that big a hammer which we can nail any problem, no. But there are certain problems that we could do much more efficiently with quantum. And it opens up an extra space. So if you see this black space and black and dark blue overlap, yeah. So that space is a new space that comes up now, which has problems like high energy particle physics or discovering new molecules that we were earlier just not being able to scratch the surface. You can't even think about doing it classically. But those kind of problems now you can do with the advent of quantum computing. So just to give an example, right? So all of you probably, or most of you probably would be having coffee, and it's a simple molecule that is on your screens right now, right? Now, if the best classical computers are so powerful, then we should be able to simulate molecules like this, at least conveniently. We should be able to do them quite well. But, and this has a large number of applications, okay? So this would accelerate discovery of new compounds, and these are very important for healthcare, pharmaceutical guys, right? But caffeine takes typically 10 to the power 48 bits to represent the energy configuration of a single caffeine molecule. Okay? At a single instant, if you want to have the entire understanding of caffeine, right? Now, 10 to the power 48 bits is almost close to 10% of the total number of atoms in this world. So if I invest everything that this world has into caffeine, what will we do with the other problems, right? But with quantum, you can actually do it with a much smaller number of qubits. Now, a fundamental unit of information in classical computing is a bit, which can hold two states. It can either be 0 or be 1. Versus in quantum, it can be, it's called a qubit, which can either hold 0, or it can hold 1, or it can be in the linear combination of 0 and 1. So it can be in several combinations. Thereby, your state space is much larger. It's now 2 to the power n that you're being able to do with just one qubit. And with just 160 logical qubits, you could have represented what you needed 10 to the power 48 classical bits. So that's the power of compute that you get. This is just an example, and there are, even bigger examples or more utilizable examples. Now, what have we done? So, coming from IBM, which has pioneered in several of the things in quantum technology. So, what have we done? So, we of course we build quantum hardware. We do a lot of things in quantum software. The first quantum hardware that we were able to successfully put on cloud, which is openly accessible to anyone, was in 2016. And from there onwards, we have been putting a lot of IBM hardware, a lot of IBM quantum computers on cloud. There are a lot of IBM quantum computers, and I'll just share a QR code in the end, which you can just scan and go to the page and see for yourself what are the different hardwares present and what all can you do there. But till now we have, and this is actually a slightly dated slide, but you have more than 400,000 registered users who are actually accessing our quantum computers and working on them. There's over 1.4 trillion circuits that people have been running on these quantum hardwares. And the more interesting part to probably you guys is the number of scientific research papers. And 1400 is still a conservative number, but we are seeing a huge number of research papers that are running on these quantum hardware. We also try to build this quantum network. So it's important because we can't do everything alone. We want to have partners. We want to get these people who are actually developing quantum algorithms or working on quantum hardware or in the theory and the software, and partner with all of them to get those problem statements which are really interesting and we should work on. And for now, we have around 127 members here. One of the recent members and the first member in India is IIT Madras, that has joined us in this network as well. So these are typically, the strategic partnership that we have, and we have close to 30 plus systems that have been deployed. At any point in time, you will see 20 to 22 systems that are available on cloud, and some of the systems will be pulled down for maintenance and all. And these are the other systems that we have been able to strategically position. So while most of the systems are in Poughkeepsie, US, there are some systems that we have been able to ship. So, for example, in Fraunhofer, Germany, in Japan, in University of Tokyo, in Cleveland Clinic, we have been putting one. In Yonsei University, which is South Korea, we have. And we are trying to bring one to India very soon. Now, just to give you an idea of how fast is the research in quantum and why you should invest now or why should you learn now. So some of my colleagues in Zurich, they published a paper on an algorithm called amplitude estimation in 2019 January. Okay, and Keio University, which is one of our partners, they present it to them, and Keio University picks it up. They advance it. They work on amplitude estimation without phase estimation. They make some modification on the existing algorithm. They go ahead. They work with their partners. One of them is Mitsubishi Finance Group, and the other was Mizuho Bank. They work with real data, and they publish another paper. And they are then, in the same year, they are now presenting their work in another, picked-up conference, right? In a quantum conference. And JP Morgan and Chase is like one of you in the audience, and JP Morgan and Chase gets interested, and they feel that, okay, this is a work that I can typically use in my applications. If this is helping other two banks, then why am I leaving behind? So now they start working, and they publish without any IBM authors. So they do everything on their own. So they had enough material to do everything on their own, and they publish. And all of this is happening within a year. And then when we realize that there's so much of potential and so much of interest that people really want to take it up and work it, we open source the entire codes. They're all available on Qiskit. So all of this happened in a year. So 3-4 research papers coming up in a single year, each presenting at different places, and more people coming up. So that's a super fast pace of research that is happening in quantum. And why I'm mentioning this is, a lot of people feel that, okay, quantum computing, maybe it's something about the future. It will come in the next 5 years, 10 years or so. But if we don't start building algorithms, if we don't start building our quantum hardware now, then, who else will do it, right? Being in IIT, I think that's something that you all guys must think about. Now, coming to applications, okay, so broadly we tend to say that there are 3 major areas of applications. For example, the first one is into simulation, where you want to simulate quantum systems, and they have a large number of use cases in quantum chemistry, in material science, like discovering new materials, and for polymers, and a lot of people work on, what is I want to ban plastic, but then what else do I use? So there's a lot of interesting problems in material science. There's a lot of problems in high energy particle physics. CERN has been working very closely with us, and we have been publishing a lot of papers on high energy particle physics. The second bucket that is there is artificial intelligence. And in artificial intelligence, of course, many of you might, because I heard that machine learning is one course that all of you might have taken. So there are a number of problems that we can try to, improvise or see what better we can do with quantum machine learning. And the third one is again in the optimization bucket. So, for example, Monte Carlo, Markov chain Monte Carlo, that's an optimization algorithm, and amplitude estimation, the paper that I was mentioning in the previous slide, that's a faster way to do Monte Carlo. So it's a faster way to do Markov chain Monte Carlo. And that has multiple use cases. For example, in finance, you have typically use cases like portfolio optimization, risk analysis, loan credit scoring, and several others. So I've just listed a bunch of applications. Of course, this is not an exhaustive list. It's just a bunch of applications just to show you guys that, if something strikes a chord with either one of you, some of you might be working on some problems versus some of you might be interested in some others. So I'm just trying to show you that these are some of the areas where people have been publishing, people are getting some initial results, or some are getting some kind of better results using quantum technologies. Now, coming to some particular use cases that we really like to flash. So Daimler, the parent company of Mercedes-Benz, we have been working very closely with them for a couple of problems, and one of the problems that I'm showing here is in material discovery. So in UK, government announced in 2020 that by 2030 we'll have all electric cars on the road. Now, if you want to have that, you have to, of course, do a lot of regulations and, charging points and all of those problems that you guys are well aware. But you need to be able to build better batteries that can hold charge for way longer, which you can't do with the current chemical compounds that exist. Right? So you need to be able to discover those compounds with which you can do better battery material design. So Daimler was one of those companies which had the vision, and they wanted to start up quite early, and we have been working with them, and there are a lot of papers that are getting published, and one of those compounds is lithium sulfur that they are currently testing in their electric cars. And all of this simulation has been possible. It would take them months to do in a classical computer, which they are now being able to do. The second example is ExxonMobil. So with ExxonMobil, there are again a couple of interesting problems. There are problems in wherein we are trying to do these chemical thermodynamic calculations, which we are able to do much faster. Then there's another problem, which is, typically you can think of that as a traveling salesman problem, because that's something that all of you know, right? So just to be able to relate. So this is a large fleet of LNG ships that carry goods to different parts of the globe. Right? Now, there could be severe conditions, right? Now, one country goes bankrupt, and you are sending ships to me, but I can't even take your ships. I can't take them into my port because I have no money to give you. So I want to send them away. Or there is some weather changes in some part, right? So the port authorities need to know how to do a better fleet management, so that some countries have suddenly a high increase in demand, some have low increase, or there are transverse amount of conditions or parameters that you wish to optimize. So this is it's an NP-hard problem. It's a very hard problem to do in the optimization space. And again, here we are trying to do something in quantum, and we are trying to reduce that and do better optimizations. And feel free to stop me if you want more details. I'm not going into too much of technical details. There are published papers which I can point you for each of these. The third one is an interesting application which I picked from finance, and JP Morgan and Chase, and we have been doing a lot of work in portfolio optimization. So you see this circuit, this is actually a options pricing circuit. It's a smaller version of the full-blown circuit that we created for options pricing. It's, I think, a call options or a put options, I don't exactly remember. Wherein what we are trying to do is we are using the same algorithm that I mentioned, amplitude estimation and some variants of amplitude estimation. It's a Monte Carlo-like sampling algorithm, and we were doing options pricing, portfolio optimization, and several other problems which are of key interest to investment banks. And they need real-time analysis. They have a lot of data coming in. They want it, like, if you can't tell me the price of this commodity right now, then it's of no use. So those are the kind of problems where you need to be able to be highly precise, and you can't take a lot of time in training and testing, unlike the current deep learning algorithms. Now, we spoke about different applications. Now, you guys know about classical computers, and Gordon Moore in 1964 said that, the number of transistors that you pack in an integrated circuit is going to double every year. right? And typically that statement of Gordon Moore is considered as Moore's law. The entire semiconductor industry runs on it. And we are now seeing an end of that because you are now reaching the 3 nanometer scale ICs. If your ICs go even further down, they're going to start seeing these subatomic experiences, right? So now they're going to start seeing what we call quantum effects. So we need to be able to go there, understand where classical physics is going to fail. We have to do something better than that, right? But that's one thing that we say that, okay, why we need quantum. Now, if we have quantum computers, how do we measure them? How do we say that, okay, this is a good metric to measure the performance of quantum computers? So we say that there are 3 parameters to actually measure. So one thing is scale. So you definitely want to have more number of qubits, right? Like the way we said, we want to have more number of ICs or more number of transistors packed into an integrated circuit. You definitely want to have quantum computers which have a large number of qubits. But the second thing is the quality. So these qubits, if they are noisy, then they are of no good use. If they are not being able to stay in that quantum state, so if folks are not aware of that, so if you have a coin spinning, right, when it's spinning, it's not either in head or in tail, it's some combination of head and tail, right? So if this qubit is in that some combination state, and if till that point, that qubit is useful. Beyond that, the qubit is useless to me because it has flashed to either a 0 or a 1, which is effectively a bit, right? It's effectively a classical bit. So till it is useful, that's the time when I feel that, I want to use it. So there should be some metric to test the quality of the quantum computer. And in 2018, there was a Nature paper by IBM where we published a metric called quantum volume, wherein it's a classical metric, it's easy to identify and calculate, where we can say that, okay, this particular quantum computer has these many qubits. It also has, the error correction up to this limit. You can run a circuit of equal width and equal depth to this level reliably, right? Reliably is very important here. So that's typically the quantum volume, and we have been able to achieve from a quantum volume of 4, we have been now able to achieve a quantum volume of 512. Right? So we have constantly been doing a lot of things, both in the hardware, the software, the circuit optimization, error correction, just to bring up the quantum volume and build more reliable systems. And the third one is, of course, speed, because as soon as we say quantum, a lot of people feel that it's just a different paradigm or a just different hardware that will be able to do much faster computation, which is not true, but it has to be fast, right? So speed is definitely a third, angle, and we use CLOPS. So, FLOPS, which is the classical metrics, and here we say circuit layer operations per second. That's the metric to measure speed of quantum computers. So we'll just. I alluded to what is scale and, with high coherence, high reliability, and, how far are we able to build our quantum system. So 2016, we had a 4-qubit machine which was available on cloud. We now have a 127 qubit which is available on cloud, and by the end of this year, it's already out. It's not out yet, but I think it's tested. It's a 433 qubit quantum computer that's going to be released in December 2022. In terms of quality, as I mentioned, we have been able to significantly pump up the quantum volume of the current devices, current hardware architectures, as well as we are working towards the newer hardware architectures. And in speed, if I just show you, then, okay, this is quantum volume. So if this blue line is Moore's law, that are we doubling quantum volume every year? So we have been able to do better than double quantum volume. So, of course, speed is very essential. So if we measure reasonable QPU speed, that is going to allow users to incorporate quantum computing as a part of their workflow. This is very important. And in order to have that speed, one other thing that we have been working on is called Qiskit runtime. So right now, you are accessing your quantum computers which are sitting on cloud. So you're sending some codes from your laptop to the quantum computer which is sitting on cloud. You're doing some quantum processing, and you're also doing some classical processing, be it on your laptop or on some other classical hardware. So there's a lot of latency that is happening. So overall time taking is increasing sufficiently. If you could have a classical computer or some supercomputer which is co-located with the hardware, then you can significantly reduce that latency. Now, saying that is very easy, but building all of that in a Dockerized container, wherein your code creates a separate container, everything works within that container. You run all your jobs, get back all your results, and then exit the pipeline. It's quite a difficult thing, but that's something that the Qiskit runtime team has been able to do. And we are trying to decrease two domains of latency. One is the real-time domain, and one is the near-time domain. And this is more going into the structure of a typical workload. And I don't know how many computer science guys are here, but real workloads are not purely quantum, right? So they require these interactions between quantum and classical compute resources. For example, the optimizations, or in quantum machine learning, there are different algorithms. For example, quantum support vector machines, or quantum neural networks, or quantum variational classifiers. So you do some part of your compute in the quantum hardware, but you do these gradient-based optimizations in some classical resource. So they're all in the state of hybrid. So, a definite claim that is not true is nothing is going to replace classical computers, right? Not quantum computers for sure. Quantum computers will be working with these classical, and they're going to work hand in hand to be able to, and we want to solve those hard problems for classical computing in quantum computers, and something which is hard for quantum might be easier in classical. So there's always this thing, right? So this is what we are trying to achieve with Qiskit runtime, and I'll maybe just forward these. So there was this demonstration of Qiskit runtime, which I'll just spend a few seconds here. So initially what we expected is that all this latency improvement and other improvements in the circuit, what kind of an improvement is it giving? And our aim was, can we make it 100 times faster? We were able to actually make it 120 times faster. Right, and this was done on a chemistry simulation problem, because those are the problems which classical computers really struggle on. And a lithium hydride compound that we were trying to understand the energy of lithium hydride, and these are huge number of circuits that were run on this. And if you look at this, the blue histogram on this part is actually the traditional runtime, and what you see in green is Qiskit runtime. So that much speed up was what we could achieve. And of course, it is not just with one thing. So algorithm-wise, we had a 1.8 times speed up. Qiskit runtime gave us 4 times speed up, and so on. And I've given the breakdown here, and this was a Nature paper again. Okay, so CLOPS, I think we briefly mentioned, it's a measure of how many parallel and parameterized quantum operations a quantum processor unit can run per unit of time, whatever is your unit of time. And there are several papers, and I'll not go into the detail of that, but if whoever is interested can go through and read more. Now, this is the development roadmap. So what have researchers before you done, and what is more for you? But this is an IBM perspective, and we have our development roadmap, up there. We have given the picture of what can we do in the next 5 years as well. So in 2019, we had a system which we call the Falcon. It's the processor's name. All our processors are named on birds. Don't ask why. They're just named with names of birds, and all our quantum hardware is actually names of cities where IBM holds an office. It's not that the physical system is there. Most of the physical systems are in US, but they are named like that: IBM Washington and IBM Perth, and there are IBM Mumbai, Kolkata, and all of that is also there. So in 2019, we had a system which had 27 qubit. In 2020, we actually built on top of it. We have a lot of circuit libraries that are open sourced, and we came up with our Hummingbird processor, which is a 65 qubit processor. And then we, of course, did a lot of algorithm work for the algorithm developers. So we have a quantum algorithm application module, and these are all open source. So these are all up. Machine learning, and we call this natural sciences or nature, wherein you have all the physics and the chemistry applications. And of course, you have a ton of optimization codes and everything which is online. In 2021, we announced the 127 qubit Eagle processor. So a 127 qubit quantum computer is already there, and by the end of this year, we'll have the Osprey machine as well. By the next year, say by 2023, what we are trying to do is, so in order to scale these machines to have, millions and millions of qubits, and that's what we will ultimately need, right? The same as far as supercomputers. So we can't just keep having more qubits in the same arrangement. So there are a lot of arrangement related things that you see in 2023 that we have planned. One is the Condor processor, which is already in development development and currently under test, which requires huge dilution refrigerators. So all of these quantum computers need these large, so golden chandeliers, if you have seen the images, so they look like golden chandeliers. They're actually large dilution refrigerators. From the top, which is at room temperature, to the bottom where the qubit actually resides, it's at 15 millikelvin. So it's made out of gold, because gold is an excellent metal to bring down the temperature and minimize the noise, right, because of its inertness properties. But so for Condor, we have created something called Golden Eye. It's a 6 feet wide and a 10-foot long kind of dilution refrigerator with these Condor processors, and multiple of these Condor processors can be stacked and kept in one way. And we are doing several types of connections. So within each of these processors, we can have classical connections, we can have some quantum connections, and so on. So you see classical connections in the processor Heron, but you will see quantum connections when we move on to Flamingo and so on. So this is more or less the pipeline or the roadmap that we are trying to work on, and these are the things that we are bringing from our side in terms of hardware, software, kernel developments, and the most interesting part is you don't need to actually learn about the hardware or know all the quantum physics to be able to start working on quantum. Okay, so if you are someone who is an algorithmic developer, you can start working at algorithm level without even knowing how that works in our real hardware. So I'm not a hardware person, by the way, myself, and I don't probably understand a lot of hardware myself, but I can still build algorithms. I'm still building a lot of applications in the domain of finance, chemistry, pharmaceuticals, and so on. So we saw about quantum volume, and if you actually go into look at any of these quantum devices, you'll see quantum volume, and that's why I put a slide on quantum volume wherein we can see that quantum volume just not depends on the number of qubits that you can create in this hardware, but it also depends on a large number of things. For example, calibration error, circuit optimization, coherence, gate fidelity. So gate fidelity means that you're applying some gates on each of these qubits, or some operators you're applying. Now you want to change it from a 0 to 1, but it is doing something else there. So there's some amount of fidelity that is involved there, right? And there are several other things. There's a coupling map. There's a layout of the hardware, right? So you have certain number of qubits laid out in a particular topology, and that's also very useful. That limits you for using some kind of gates that bring some different kinds of challenges and so on, right? So all of these are important points to that quantum volume tries to take care. And I've highlighted this circuit optimization thing in green because that's something that my team works on. And just with adding a lot of circuit optimization, we have been able to significantly pump up the quantum volume, right? So without doing anything in the actual hardware also, we were able to increase the quantum volume. So just because this is a largely student audience, I've put in a lot of these self-learning resources. So all of this is openly available and free. The Qiskit textbook is free. So Qiskit textbook is an interactive textbook. It has the concept, and it has the codes right there in Jupyter Notebook. So you can directly, you don't have to install anything, you don't have to do anything. You can directly run codes from a Qiskit textbook, and you can learn each concepts while running things and have a feel for yourself and how things work. Of course, there's a Qiskit YouTube channel where a lot of these academicians and industry experts from all over the world come and give their seminars, which are everything is free for anyone to attend, and there are these recordings where you can go back and hear at any time. And of course, we build these two software platforms. One is a graphical user interface, which we call Quantum Composer, wherein people who are not very familiar with coding, they can still do some of their applications, right? They can drag and drop gates. It's graphical user interface. It's very, very easy to use, and they can create something of their own. Versus there's a second one, which is a Python-based one. So you don't have to, if you know Python, you don't have to know a new language to be able to do quantum computing. Right? It's completely on Python. It's called Qiskit, and Qiskit again is open source and free, and you can quickly get started there, right? So yeah, so this is just something about Qiskit. It's agnostic to the underlying hardware architecture, although IBM works on superconducting qubits, but there are several other companies which are building quantum hardware on different other technologies, and they have their own pros and cons, and Qiskit can be useful for all of them, and coding on all of them. And Qiskit hosts a wide range of calibration metrics and a lot of error mitigation techniques. So that's something that is very useful for any kind of quantum computers, because these are not logical qubits that we have. The physical physical qubits that we have are error prone. So after a certain number of computation, you'll have to do some kind of error mitigation to get a better results. And error mitigation typically will improve your results. So Qiskit has that as well. And again, this is some of the, research papers. I mean, the pride part that we have is whenever we show these research papers, there's a large number of research papers which don't have IBM authors, right? That's where we feel very proud of that people have been able to use Qiskit or use IBM hardware and build things by themselves, right? They didn't have to have an IBM author in there. So large number of areas: chemistry, optimization, finance, machine learning, and these are there. So I just put up this, so this will take you directly to quantum-computing.ibm.com, and you can have you can take screenshots or whatever you want, and this will directly take you there. If you have any kind of email ID, right, Google, Gmail, LinkedIn, Facebook, Twitter, whatever email IDs, you can log into that, and you will be able to see all the quantum computers that I've been mentioning or I've been showing in the roadmap. They are out there. Anyone, some of them are free to access, some of them require a premier access to, but you can at least look up the hardware, read about it, see how it functions, and get all details about the hardware. Qiskit is up there, the Quantum Composer, the graphical user interface is up there, so you can access everything. All your codes will be there. You can share your codes between your peers and create reports, everything you can do just from this one link. So feel free to try it out. And thank you. Yes, please. Can you give him a mic? Can you give him a mic?
So thank you, Dr. Ray. Now the floor is open for question and answer session. Yep.
I joined it late, but I know this subject was very discussed some 10 years back, but I didn't see much progress. What I understand, computing has become faster, but communication has not become that fast. So I think the basic problem in any system, quantum design, is an optical interface. Not our standard or the protocol-based other things. So optics also, they are giving some protocol and all. So how to use that one in a private network, that is better. I don't think you can use it in a big outside internet environment. And finally, the purpose of quantum is to myself, I'm a control system man. We want to control something. So what you are trying, I feel certain noises at all, which we can capture at this quantum rate, then that is better. I want to understand the purpose. What for IBM is using. Are they discussing colleges and this thing only for quantum or quantum for some purpose?
Yeah, so
Sorry for the comments.
no, that's that. Thank you for the comments. So this gives me an opportunity to describe way more things that I naturally wanted to skip because it's a majorly student audience. But I would, yes, of course, they should. There's a large amount of things that we are doing. So, and what you are pointing to is a small sect of what we are doing. So, this slide is a bit too verbose. Oh, it's not even legible. So if you look at the academic, the last column, that many names are academic universities around the globe that we are working with. So it's showing 52 academic partners, but this is a slightly dated slide. So I'm sure the numbers have grown, but let's go with 52. It's 52 universities. And each university, there are multiple profs that we are working, different areas, not just quantum communication or quantum. There are several product areas, so see for yourself. I think this is legible. So we work on a lot of problems in quantum communication. We work on a lot of problems in quantum control theory. We work on a lot of problems in quantum chemistry. For example, these ones that we were mentioning, improved battery materials. I think I'm audible. I'll point you to maybe the researchers who are working on quantum communication and quantum theory. That would be best for you. Yes, sure. I'd be more than happy to do. Thank you for the question. Anyone else? Any other query? It could be any question, just feel free. Yeah, please.
Hello, ma'am. Being a student of MSc Physics, how can we go into this field? Because I'm particularly interested in quantum physics and quantum technology.
Being a student of MSc Physics, you have all the background to pick up this much.
So, what's the roadmap?
Computer scientists like we have. Apart from Qiskit, if you are familiar with Python.
I have learned it already.
That's excellent. So wherever you are more interested, you could be interested in the hardware. There's a lot of people working, even in India, there are a lot of people who are developing quantum hardware. TIFR has a 1-qubit machine, IISc has a 4-qubit machine now. SERB Pune has a, so if you're interested in hardware, I'm just giving you pointers to wherever you're interested. If you're working or in the algorithmic space, then there's of course a large number of people. I know TCS, my next speaker is here, so they are working on applications. Capgemini is working on applications. There are a large number of people who are working on algorithms and applications across IBM. IBM works on the entire stack from hardware to software, everything. And then you have, if you want to work on control, there are a lot of people who are working on control. There are a lot of people working on hybrid cloud. So these quantum computers, they are hosted on cloud. It's not an easy task. There are a large number of people who are accessing those quantum computers. They are running their processes and getting it back, right? So, one fundamental reason why we have been able to put it out on cloud and other companies have not, because IBM had a huge history of working into hybrid cloud, right? So that gave them an edge over maybe others, and we have like 30 plus quantum computers. So hybrid cloud is definitely one area. The hybrid cloud quantum computing, that's another area. So there, even you can work at a device level or a kernel level. So there are different levels, and maybe add one slide wherein I show all the stack. So whichever stack interests you the more. If you are more of an experimental physicist who wants to work on hardware, there are a lot of things to be done. I mean, one of the major things is, for example, there are different technologies that can build, right? There is ion trap, there is cold atoms, there is superconducting. So there are different ways of constructing a quantum computer, right? IBM does superconducting because there's some pros and cons. Ion trap is also there. So there are, and each of them have their own advantages and disadvantages. So you may wish to explore. I would say, as a student, you have all the liberty to explore within your research and within your PhD and find out what is that thing that you want to really work on. There's a lot of.
Good afternoon, ma'am. I want to ask, what are the advantages quantum will have in option pricing, derivative pricing in finance sector, and how much accurate it will be compared to traditional methods?
So compared to classical Monte Carlo, so Markov chain Monte Carlo, we are seeing a quadratic advantage. Okay, so there's a quadratic speed up that you are seeing. But okay, can you hear me now?
Yes, ma'am.
It's way too loud. Okay. So in terms of Monte Carlo, so wherever there was Monte Carlo, Markov chain Monte Carlo kind of algorithms being used in these processes, which are most of them like portfolio optimization or options pricing, most of them use these kind of classical algorithms. There we see a quadratic speed up. Okay, but then there are other applications also or other algorithms wherein we really don't see a quantum advantage as of now. So we are seeing that these quantum algorithms are being able to do sometimes at par, sometimes not as good. Now you have to also understand something. For example, in machine learning, a lot of people ask this, that can quantum machine learning beat classical machine learning? Now classical machine learning has their growth years over some 40 years or so, right? So suddenly quantum machine learning is not even like 5-year-old. So it cannot really beat that. It has its own advantage, disadvantage. So if you compare it in this way, that you make them an apples to apples comparison. So you bring down the classical algorithms, machine learning algorithms have this advantage that they can take in large volumes of data. For example, the deep learning algorithms, right? They can take in large volumes of data. These quantum algorithms are currently struggling. Not because there is an algorithmic burden there, but because the hardware is not being able to run so many circuits at one go, or it is taking a significant long time for you to run so many circuits, right? So that's the reason we are trying to, we are sort of restricted. So to some, for example, I have been running these in the order of thousands, right? So I've been able to go till 20,000, 25,000, and then I feel there's a restriction. I'm not being able to do better than that. For example, in classical machine learning or in deep learning, I was doing millions of data. Right? Now, if you bring down, so you take your same deep learning algorithm, make it work on some 20,000, have a quantum ML and then algorithm and work on 20,000, then you see that, okay, quantum algorithm is slightly better. But then you can always argue that classical can go much better if it gets more data, right? So that is there, and it will be there for some time, I believe. So we'll have to, that's the reason we are here, right? So we are trying to improve these algorithms better and better. So yeah.
Thank you, ma'am.
Sure. Yes, please.
Thank you, ma'am. So I had two questions, if you don't mind. So firstly, as a computer scientist, can you just give us your opinion on the different hardware techniques that are there in quantum computing, like superconducting or photonic?
Yeah, so superconducting, so the advantage is, it will go, disadvantages will go unstable very quickly. Okay, but the advantage is you can run a lot of things and run a lot faster. So if you look at speed, which is something that people typically aim, or people hope that quantum computers will make things very fast, that's something that superconducting can do. That's the reason why a lot of companies like IBM, Google, they are relying on superconducting. Now, if you look at ion trap, the qubit stays, the coherence time is typically longer, right? So the qubit stays stable for much long, but it's slower. So you can run a lot of circuits. So the problem that I was just mentioning, right? The number of circuits that I'm being able to run is getting limited here in superconducting. Maybe you would be able to run a lot more circuits, but then it is way more slower. So each of the hardwares have their own, so cold atoms are there, each of the hardwares have their own pros and cons. Then there are some advantages, for example, fabrication. Right? So IBM has their own fabrication, and they found it easier to fabricate with superconducting, right? But there are, different people have their own hunches and go with their own materials for quantum computers.
And the second question was, let's say, what's the major issue? Can you discuss the major issue that is stopping us from having, let's say, 1 million qubits or something more than that?
Noise. It's just a one-word answer. That makes quantum error correction the fundamental or the biggest research area in quantum computing. So these qubits are highly noisy. Okay, so noise could be several things. Noise can come from the environment where a quantum computer resides. So I was mentioning this huge dilution refrigerator, right? And you have to decrease the temperature. So if the temperature is slightly above, so if there's a minimal amount of heat, it's not like visible heat, but then there is some amount of noise, any kind of heat, your qubit will collapse to either state. So your qubit will lose its coherence. So those are properties, and those are issues that, and there could be several types of noise, right? So it's very hard to handle that kind of a noise. So we are far away from having logical qubits. Logical qubits is like an ideal qubit that has no noise. So the qubits that we are showing you, they're all physical qubits. They're all physical chips that you can see by your hand, right? They are still a visible size, and they are experiencing all these noise effects.
Thank you.
Yeah, please.
Yeah, so I do have like two questions particularly. So first question is that with improvements in the design of the quantum computers, year by year, so we are expecting more qubits to be allocated within the constrained resources. So if we are constraining the resources alongside accounting the fact that we are using dropping noises and
Constraining what resources?
Resources, I mean to say that we have to allocate qubits within a certain space or within certain hardware constraints. So how we are allocating more qubits within the constrained space if we are improving the quantum computers and their designs?
Okay, so space constraint is not the fundamental problem. The fundamental problem is you want to have qubits in an arrangement where you can do different types of circuits processed. Okay, And what happens is, if you have these arrangements, often you see that, okay, you did some operation on qubit 1, but qubit 1 is not connected to some other qubit. So you have certain topologies. It could be a linear topology, it could be some hexagonal, some topology. And then you need a large number of gates. So you need, okay, I'm doing one swap operation from this to this qubit because these are connected, then another, and then finally you connect to that particular qubit which was not connected, and that was your intended thing. So you are using a large number of gates. The more gates you use, the more noise you bring. Okay, so that is a challenge. The other thing is, if one of the qubit is staying idle, that is also a problem. So if the qubit stays idle for a significant time, that's also a problem. So it's the fabrication wise, that is not a challenge. The challenge is that we are just not being able to pack in. So okay, so Keio University did this kind of an experiment. They said that, okay, let's just pack in more number of, similar to what we do in transistors, right? Let's pack in more qubits. Does that increase the quantum volume? Versus, if you have the same number of qubits and you are being able to do an error reduction by 10%, you have an increase of 500 times quantum volume. So error reduction by 10% matters that much. So error and noise is a very big problem. If we can get that in control, we can go much faster. So,
Yes, like accounting of physics constraints as well, like while we are
absolutely, absolutely.
And my second question is that, while using these quantum computers, can we also go with the application of like mimicking a consciousness? Because while we want to study about the human consciousness, so we account the fact that we use multiple neurons and etc. So can we also go towards that direction as well?
So typically quantum neural networks, that idea is completely borrowed from classical neural networks, which is of course brain inspired. Quantum computers itself are differentiable. Now, that's a very good property. So differential programming is a bridge that brings in machine learning and quantum computing closer. Okay, you can do differential programming in both, linear algebra in both. So that's the reason why people are saying that, quantum machine learning will probably see the sunrise first, right? I mean, quantum advantage first, I should say. So I am not very sure about if people have been able to do neuromorphic or brain-inspired applications as of now with quantum computing, but we are trying to tackle those problems which were not being able to be done using classical computers, which you were already being able to do with classical computers very well. You don't really need a big hammer like quantum computing. It comes with a large cost as well, right? It comes with a lot of things. So you don't really, so for example, you want to factor two numbers, you can do it easily in quantum computer, right? But you want to do a different object, which is a different thing that is hard for or easy for a classical computer, you'll find it very hard for a quantum. So you don't want to apply to everything, right? So I'm not sure if people have been doing brain designing, but yeah, there are a lot of interesting applications where people are doing in image recognition, image processing and so on. So you might just see in a few days that you have fMRI images and people are actually trying to do that. So that there could be people moving to brain-computer interface, so yeah.
Yes, maybe a sample design.
Yeah, but yeah, you guys are the future, so you guys should think about such applications and start building something like that. So that would be best. Anyone else, any other questions? Yeah, please. Just ask.
Can quantum computing be used for Bitcoin mining?
So I have been working on Ethereum, which is a crypto network. Yes. Ethereum, because Ethereum is open source. It is one of those cryptocurrency network which has the largest amount of blockchain technologies built on it. So I have personally been working on Ethereum and we can do that. So, but yes, I am of course not working on that problem. I am working on Ethereum for doing phishing detection better. So with crypto, the problem is that you don't have audit regulations. You don't. It's a decentralized network, right? And everyone has that kind of a principle. So its auditing is hard. A lot of things are decentralized and makes it much harder. So there can we do phishing detection better, and that makes for the life of hackers and phishers, it's easier, right? Anyone can send you an email or something like that and say that, okay, you have to invest in this and this is doing better. And most of those activities are phishing activities. A large amount of money is trapped there. So we are doing, so in short, the answer is yes, and it is doable, but yeah, use it wisely.
So if I use quantum computing in place of classical means computing, so will my efficiency increase in Bitcoin mining?
I have not done mining, but yes, for these kind of detection problems, we are being able to see some improvements.
But the mining cost will not decrease.
So there are a lot of people that are doing data mining, and there's no such advantage that we have seen over classical yet.
Okay.
But maybe eventually. But yes, you can do it. With the current algorithms that are available, you can definitely do it.
Okay. Thank you.
Okay, let us thank the speaker, Professor Anupama Ray. We are concluding the first part of the session. I request Professor Kiran Kumar to present the memento to the speaker.
All right, so after this wonderful talk, now we have a second speaker, Mr. Godfrey Matthijs. Mr. Godfrey Matthijs is Quantum Computing Solution Consultant, R&I Incubation at TCS, and is responsible for working with accounts and businesses with identifying big bet opportunities in quantum computing. Mr. Matthijs holds Bachelor in Engineering, Computer Engineering degree from Mumbai University. He started out as a multiple stack mobile developer with an extensive experience in designing and developing Android SDKs. He has over 15 years of experience in the areas of cognitive solutions like data extraction, chatbots, as well as IoT solutions. Over last 2 years, Mr. Matthijs has been working with various customers and TCS accounts to identify next big bet solutions in the area of quantum computing. He has been actively involved in various domains, which includes quantum machine learning and optimization. He is also a part of team that is working with South Australian government to evangelize quantum computing in their geography. He is actively participating in academic collaboration, standards, and ideation for research labs. So, Mr. Matthijs, we are eager to hear your views on QIC. Please, Bill.
Hello, good afternoon, everyone. Give me a few seconds. I'll just set this up. There. I hope the screen is clear. So before we start, COVID has taught us something. Like, we have been working from home, and every time we do a presentation, when we begin a presentation, like we share our screen, the first question we usually ask is, am I audible? I hope I'm audible to the end, the last row. Good. And the second question we ask is my screen visible? And well, I don't need to clarify that because I can see it myself. That's a good thing. So without any further ado, I'll start with my presentation. The topic is quantum computing and applications. My messaging would be similar to what Dr. Anupama gave, but a slightly different perspective. There was more on algorithmic side, the hardware side. I'll give you more from what we, that is the service industry, perceives this. At different domains, how do you look at those use cases? And what do we usually tell our customers? Because we deal with a lot of customers from different domains. What do we tell them, considering the situation of quantum computing today, right? So before we start anything, a small introduction about my company that I work for. It's Tata Consultancy Services, and I believe everybody knows about it. It's one of the biggest company in India, the most reputed IT services company. We have a strength of around 6 lakh employees worldwide. We are present in 46 countries, not just in India, but in most of the countries. Like last week I was in Australia, and there also we have a strength of around a couple of thousand employees there. Locals, not the ones going from here over there on-site, no. As far as our strengths are concerned, we do have our research groups, the team that I'm part of. We have around 2,100 granted patents, approximately 6,000 patents on the way. Not just quantum, but everything. I'll come to the quantum bit a little later. So as I was talking about the TCS research group, we call it the RNI. RNI stands for Research and Innovation. And the subgroup that I belong to, that is called the incubation team, which is part of the RNI group, but it is a step after research. So while research takes in all the new technologies, works on different algorithms, a lot of new things, we in incubation, we pick up those ideas and we work on delivering the next big bet solutions to the businesses. Okay? So in other words, we are a startup within TCS. So every 2 or 3 years, we pick up a new technology, we try to create some high value applications out of it, give it to different accounts within TCS. Now when I say accounts are those groups within TCS who service different customers in different domains. So we, that is the incubation, we are a horizontal within the entire organization, and every account is a vertical. So we service everyone within TCS. Right? So it's kind of a startup. We try to come up with, with high value solutions. We pitch them to our customers through the accounts, and then we hand it over to the accounts so that they can take it further. So if you see towards the last row, we have all the solutions or all the technologies mentioned. So our group was set up in 2008. And from that time till now, every 2 or 3 years, we've been working on something new. We started out with connected markets. Then we went on to IoT. In between, we had cognitive. That was something that I have been working on before I came into quantum. And in the last 1.5 years, that is towards the beginning of 2021, we embraced quantum computing. Now, when I say we, I'm again talking in terms of incubation team that I'm part of. In fact, our research group that is there, they have been working on quantum for the last 5 years. And we came into this in the last 1.5 years. So that's about TCS in general and my group in general. Now we come to the main part of the talk today. And the agenda of this talk will be quantum computing short introduction, which a major part of it was already covered by Dr. Anupama. What kind of problems can be solved by quantum? A perspective on the quantum problems from our side, that is the service industry side. Then I'll talk about TCS's work, investment and work in the area of quantum. What are the different use cases that we have done, and in a nutshell, where do we stand? And finally, what do we propose to our customers? So I'll not go a lot deep into the quantum computing introduction. That topic has been very well and thoroughly covered till now, and you guys already know a lot about it. But when we talk of quantum computing, we talk in terms of quantum bits. And the way it is different from classical bits is, classical bits are sequential in nature. Of course, they take the value of either 0 or 1, but then when you do a processing, it has to be sequential. It is sequential. You can have multiple codes and make it parallel, but that's how you do it. In case of quantum, parallelism is inherently available to you. Why? Because qubits can take multiple values ranging from 0 to 1 and everything in between. That's a combination of zeros and 1. So, couple of features that something called a superposition, you have entanglement, you have interference, all of this coupled together, and by using this, you can really create some very useful applications. Today, you are at a stage where you can create POCs, which can demonstrate some quantum benefits. I'll not use the word advantage, because when we use the word advantage, a lot of bells start ringing. So I don't want to bell the cat right now. I'll use the term quantum benefits. Now this is something that I wanted to show you guys. Probably this might be bounces for you, but then I'll make it simple for you to understand. The theme of this slide is to say, why is it the right time for you to start working on quantum today? And when I say you, it's not just you, but for the industry as well. If you look at the red boxes, sorry, the pink boxes here, that tells you about the status of quantum today. And if you look at the gray boxes, that tells you what is it projected to be in the coming years. So in the year 2020, quantum patents ranked number 5, right? So you can make out that has been the kind of work that has been going on into the area of quantum. The top countries like the US, Canada, China, Russia, everyone has individually pledged close to $1 billion into this area. And even in India, we have NMQTA, through which the government of India has also pledged close to around 8,000 crore rupees. And so that's also a big investment coming in. In different areas, different geographies and different domains, you see a lot of consortiums coming up which are working specifically on quantum. You have Q-Farm, which is in the pharma industry. You have Q-Star, which is specific to Japan, a group of 25 Japanese companies coming together. You have NMQTA in India, where even we are part of. And you have QTAC, again, I think it is Europe. So these are the different consortiums, organizations that have come up, a collaboration that is coming up. So you see, quantum computing is not an individual's game. Not one organization can do it. You need to be a group, right? And that's why even we, as TCS, we collaborate with universities. We have started doing that in India. In fact, even with your organization here, we work with the top players like IBM. We also, now being in a service industry, we cannot just stick with one provider, so sorry IBM, but then we also have to work on other things like using AWS Bracket. We have to use Microsoft's solvers, the quantum inspired solvers. We work with niche players like D-Wave as well. And we try to work on all of these things. We try to run our applications, execute our applications on all of these hardwares, all of these simulators, and use their technology as well. But primarily it has been IBM to begin with. Now, if you look at the gray boxes, the left-hand side box, that gives you a survey which was conducted by IDC in 2021. And they say that by the end of 2027, the quantum market is going to grow up to $8.6 billion. That's a huge increase from what it is today. Now hold your breath for the next one, that is 2035. This is a report by BCG, and they predict that by 2035, this market is going to touch $900 billion. Wow. So that is what is going to drive this market, and hence, not just we, many players in this, even IBM would say, the time to begin is now in quantum. In fact, it's already a little late, but if you haven't yet done it, now is the time to start. So I'll go to the next topic now, what kind of problems can be solved. When we talk about problems and use cases, we get into the area of complexities. We talk about P, NP, NP hard, NP complete, all of these problems, right? Now, classically, it's easier to solve the problems which fall into the category of P. You can also tackle some of the NP problems, but when it comes to NP hard and NP complete, that is, there are some problems which classical just cannot solve, and there are some problems which classical can solve but can take a very long time. The timing, the time that it takes would really not be acceptable to you. And these two categories of problems are the ones that we feel quantum could play a big role. So it's not just quantum everything, but along with classical, quantum will play a supporting role, and maybe that supporting role will keep on increasing as the time progresses. A few examples of use cases here with numbers that I have put in. A typical traveling salesman's problem, right? You all know about this particular use case. You have a few number of cities, you have a salesman traveling through it, and your goal is to make him travel through all of the cities in such a way that the final distance he travels is the minimum, right? Now, In this particular use case, there could be many variants to it. I'll take a very simple case. One salesman have to travel through all of these cities at least once. Now, when we talk of this, as and when you increase the number of cities, the problem grows exponentially. Like in this case, you have to travel through 10 cities, which means there is a 9 factorial combination of routes available that you need to process. That is around 3,62,000 possible routes, right? And this figure is quite difficult for a classical machine to handle today. You increase that value by 1, that is, increase the number of cities to 11, and you're talking in terms of some 3.6 million possible routes, which is close to impossible for classical to solve, right? So any number of city that you increase, the problem grows exponentially, and that is where quantum could come in handy. You take any typical use case, which maybe a rail network that needs to be designed, a road network that needs to be designed, something in the retail domain, right? You have to transport goods from different places, bring them to somewhere. You increase the number of your storage depots, your distribution centers, and you're talking of a very big number here. The second use case is, the second example rather, is the weather forecasting. Today, we do not have a very good system that can predict earthquakes, right, in real time. Not just earthquake, anything like, you can say, very heavy rainfall in a short span of time. That's quite difficult to do because there are so many parameters to be considered, and for a classical model, that becomes really difficult. So we believe using quantum, even a problem like this could also be handled. Then we have caffeine molecule simulation in the area of chemistry. There is an illustration given here which says that for a caffeine molecule, to simulate a caffeine molecule or to model a single caffeine molecule, you would need 10 to the power 48 bits. And what we have today is 10 to the power 16. Right? So there's a big disparity of what you really need and what you have. In case of quantum, if you want to solve the same problem, you would need 160 qubits. But today what we have is 127, which is still some way to go, but we do expect, and IBM is soon to come out with a machine which is having 433 qubits. Now, of course, not all 433 will be useful because a lot of it goes into error correction as well. So we'll have to wait some more time. But what we believe is when you have a sufficiently good quantum computer available, this problem could also be tackled. Now, from the industry use case perspective, I tried to divide some of these use cases based on the domain that they come from. We did a few market study, we referred to some studies done by the others, and we came out with a list here. Like in the first case, you have the BFSI, that is the banking domain. You have use cases like portfolio optimization, options pricing, asset price prediction, etc. In retail and transportation, you have capacitated vehicle routing. That's one of the problems that we are tackling. You have scheduling, fleet management. And if you go through the other list, we have listed some more use cases there as well. I'll not go through each of those, but this is for your reference. You can have a good look at it. One thing that is missing here is cybersecurity. I'll not talk anything more about this. I'll come to this later. Here. So the way I like to talk about quantum, the cybersecurity is as the flip side of quantum. I begin that as a flip side of quantum. Why? Because one statement, once you have really strong quantum computers available, your current encryption will become obsolete, is the statement given by many organizations, and there are some theoretical studies that also point to that. In essence, there are 3 threats that we look at: data harvesting, man-in-the-middle attack, and pseudo-randomness. When we talk of data harvesting, consider the shelf life of any data. Like your personal information being stored by any bank. There is always a shelf life to the data that is being stored. It could be 10 years, 20 years, 5 years, whatever. Now, what hackers are doing is they can get access to the data today, but they cannot break it. Why? Because it is encrypted. It's quite secure. In today's standard terms, it's quite secure. But they are storing it at their end. Why? With the sole objective that once you have a good quantum computer available, and if the shelf life of the data is quite huge, they'll be able to break this data easily and access everything. right? So that is what is happening today, that is storing the data, or you can say stealing the data. Second is man in the middle, where you have data transmissions happening and somebody eavesdrop. How do you identify that? Today it is being done, but it's a difficult affair to do. In case of quantum, there is a feature wherein, when a qubit is in the state of superposition, and the moment you measure it or you try to read it, it loses its feature of superposition and it takes just one value, right? And this particular feature can be made use to identify if your data was interrupted or if there was some kind of an eavesdropping. I mean, it could not be just that thing, but this is one of the things that can be used. And finally, you have pseudo-randomness. Most of your encryption algorithms today depend on random keys, and your encryption usually is only as strong as the randomness of your key. Today, the kind of random keys that are being used are generated using software which are pseudo-random. Like, they do depend on some seed value. And if somebody knows about that, it's easier for them to break that key. With quantum, you could look at something called as quantum random number generations, which is already available by some players. And through that, what they say is they use the physical property to generate a random key, which is not predictable, and hence it makes it stronger. Right? So that is where it is now. Do you have a question? Okay. So I'll just jump to this one slide over here since we are on the cybersecurity area. This talks about what should organizations do in the area of cybersecurity today. So the first thing that they can do is look at quantum random number generation. If you are already working or using random number generation but the pseudo ones, now is the time where you can migrate to quantum random number generation. The second is quantum key distribution. This is where it's still maybe a couple of years more in the works. You do not have it readily available today, but there is a lot of research going in. This mainly deals with transmission of data between two places, 2 points, and how do you do it securely using quantum techniques. The third is post-quantum cryptography. This is something that can be done even today. In fact, NIST, that is the American organization, is already working on identifying few algorithms, few standards that could fall into the category of post-quantum cryptography. Now, what is this? These are actually not really quantum techniques, but classical, which are believed to stand or withstand the quantum attacks as well. So NIST started with around 7 or 8 such techniques. They started evaluating that, and finally they came down to 4 techniques which they thought would be really strong against quantum. And very recently there was a news that one of those was also broken. So now essentially you have only 3. Now, having said that, many organizations are also working on creating new standards, creating new encryptions, which can fall into this category as well. But this is where organizations can start building up today itself, right? Because it's not purely quantum, it's a lot classical as well. The main purpose or the main thing that needs to be done is being crypto agile. Now, when we say crypto agile, it means you build up your encryption in such a way, your encryption platform in such a way that switching between techniques becomes easy. Right? Today you have something. Tomorrow that might not withstand those different attacks that we're talking about. You might have to bring in something new. So make your system in such a way that migration of those techniques to your system would become easier, and it won't be a time-consuming or a costly affair later. So here we conclude the part where I'm giving you some general knowledge about the use cases in quantum in a general sense. Now I'll be talking about what we as TCS have been doing in the area of quantum, our investments and works in the area of quantum computing. So this gives you a nutshell view about TCS's work in this area. So as I had already mentioned, the research groups within TCS started working in the area of quantum. They started working 5 years back into this area. My group, that is the incubation team, we got into it 1.5 years back. And along with the research teams, we have published close to 18 papers and 3 patents as well. We have a dedicated team of incubation enthusiasts that counts to around 30, and these 30 people are dedicatedly working on quantum use cases today, which is a big number considering many other companies in India at least who have a dedicated workforce working on quantum use cases specifically. In addition to that, we also undertake trainings within our organization, and we train the other folks also. Now, those other folks are not really part of the quantum team, but they service the other accounts. So the whole idea is, as and when we are growing, we are talking to different customers, we are talking to different accounts, and when something comes up for one of the customers, we can engage these 200 people as well. In addition to that, we are also building a few solution accelerators. Now, this is something that we are bringing in from our classical domain as well. So before quantum, we were working on the cognitive side of things, where we used to do a lot of modeling, a lot of machine learning. And for that, we had seen that, creating models, running experiments, sequentially takes a lot of time. So we came up with a platform which allows you parallel experimentation and basically reducing your time of experimentation and getting the results out. So that is a concept that we are trying to bring into quantum as well. In fact, half of it is already done, where we are helping users with developing pipelines and based on workflows, and experimentations can be done in parallel. Additionally, as I said, we come with a very strong background in the area of machine learning, in optimization, and we are trying to bring most of the use cases that we see over there. We try to create POCs on those on quantum as well now. We are also aligning with a lot of universities in India, one of them IIT Jodhpur as well, and trying to see if there are some use cases that we can take up with you guys. And of course, we'll look out for internship folks also. If you are interested to do your internship with us, you're most welcome. So most of our focus till now has been primarily on QML and optimization, but recently we have also started working on simulations as well as security, in the area of security. We have a dedicated cybersecurity team with us, and a part of it is also working on the quantum cybersecurity as well. So here what you see is a few of the use case POCs that we have already developed till now. They belong to different domains, like you have manufacturing use cases, you have BFSI, you have supply chain, you have chemistry. Now, having said that, the concepts that we have deployed in most of these use cases could be cross-functional as well. Something that we have done for manufacturing, that could be used for banking as well. That could be used for the medical imaging as well. Right? I'll get into the details in a little while. But the core idea behind developing all of these use cases was, first, our own skill building. We as TCSB realize that having a quantum in-depth knowledge is very difficult to find outside. So we embarked on this journey 1.5 years back, where we got our own folks getting trained onto this technology and then start developing POCs. The second objective was experiment with different quantum techniques and classical techniques, and then do a benchmarking of the results that were obtained. So we have tried with many classical techniques, we have tried with gate-based models, we have tried with annulers as well. Now I'll get into the little bit of details of each of the use cases. Give me 1 second. Okay, so the first use case that I like to talk about is the quantum enhanced quality inspection. In other words, I call it image processing based anomaly detection. So last year, towards the second half of last year, BMW had put forward a quantum challenge where they had put up 4 different use cases. This was one of them, and we participated in that. And I'm happy to say that we finished as one of the top 3 finalists in this. Now, the use case talks about identifying anomalies on different parts of a vehicle, but through image processing. So you have this conveyor belt and different parts of the vehicles go through it, images are captured, and those images are given to us for further processing. So we took those images, we first implemented a classical unit technique on this, and then we tried to create some quantum enhancements on those. So that was one technique that we used. Second, we created a completely new pipeline of classical implementation, which included segmentation and classification as well. And then finally, we converted those segmentation and classification layers to quantum. And the results that we obtained, we could easily say that we were on par with the existing classical techniques. I won't say we were better, but we were on par with the classical ones. The results were very much in line. Now, the concepts, the techniques that we have used here in this particular use case, as I said, they could be cross-domain as well. So similar techniques could also be used in the medical imaging section as well. We as an organization are working on some new algorithms which deals with breast cancer prediction, kidney tumor segmentation, right? And that is classically that is being done. We are trying to see if we can bring some part of it to quantum as well. That's right now in the evaluation phase, but we should start implementing that in the next 2 months or so. Similarly, you talk about the insurance use case where you have to do a survey of a building structure which needs to be insured, right? The ideal technique, usually what happens is you fly a drone or somebody goes and clicks pictures and then you bring that to your office, go through them and then identify like what kind of an insurance or what kind of cover that would require, right? So those things can also be done using these techniques in some way. Well, there are other use cases also that I can keep talking about, but I don't think I'll have that much time today for that, but we can have a chat about it later as well. Then these are some use cases in the banking domain that we have done. The best use case that everybody likes to speak, the portfolio optimization. And then we have time series forecasting also, where depending on the past performance of a certain stock and some other parameters, you try to predict the future value of it. Now this time series forecasting, though we have done it for the BFSI domain, it could be relevant to other areas also, like retail, like manufacturing, where you need to predict the demand and supply, pricing of products, and all of those things. Now here, we have done it for a certain stock within the Indian stock market, try to predict the price of it, the upcoming price of it. And its dependency could be some other stocks. It could be the international market, right? Some other assets. So all of those were considered. The next set of use case here that is mostly related to supply chain. The first one is cargo loading optimization. This again was a challenge that was put forward by Airbus. We did not participate in that, but we tried to take this up later. As I said, this use case, this challenge was done 2 years back, and we started working 1.5 years back. So this is kind of an offline activity that we did. The goal here was you have a plane, a freight aircraft, and you have all of these different containers. Now the goal is to place them onto the aircraft in such a way that you honor all of the constraints of the aircraft, and you also make sure that most of the containers are serviced. So we tried doing this. We have implemented this on gate-based machines. Then we have also done it on annealers as well, and a few classical techniques as well. So what we have ideally seen at this point of time that any optimization use case that you take up, quantum annealers have been known to give good results compared to the gate-based models. And it's also natural because for gate-based machines, there is today a lot of restriction, most prominent of them being error correction. The capacity is less today, right? So today, if you want to compare, you might not see it winning compared to the annealers. But that story could change in the coming years, and you have a wide range of domains that you can service using gate-based machines. The next use case over here is agro-produce supply optimization. In simple terms, route optimization. And a little bit more additions to the route optimization. Now here the idea was, we were working for a partner who is into the agro-produce shipment activity. The current way of doing this activity is manual with a little bit of automation. The goal here was transporting agro-produce goods from the farmers to the storage facilities, and from the storage facilities to the end locations. It could be stores, it could be direct to homes, anyway. So we tried to tackle the first part of it, that is transportation of goods from the farmers to the store locations, to the storage locations rather. And there are certain observations that we have seen. Again, this observation that you see here is for the annealers. We saw approximately 43% less vehicles being used. This is compared to the semi-automated mechanism that they are currently using. We have seen better vehicle loading. So here we are also using this concepts that is being used in cargo loading optimization to fill in the trucks. And then the distance being traveled by the vehicles is also reduced. So some of the readings here that we have seen. Now finally, I go to cybersecurity scenarios. So from the TCS perspective, as I said, we have one dedicated team that is just focusing on cybersecurity in general. And now they have set up a team that is looking at quantum security as well. And as part of that, the first activity that we have taken up is evaluation of the NIST algorithms to work in the area of PQC. So that is the first thing that we are doing. The second is we are trying to work with one of our partners. I'm sorry I cannot name them, but we are trying to work with one of our partners here to set up 2 test beds within TCS premises. And we want to showcase or demonstrate data transfer between the two, considering the quantum security features are in place. So QKD is what we are going to use over there. And finally, quantum accelerators. This is the toolkit that I was talking about earlier, where we are trying to speed up experimentations by developing a toolkit that anybody within our organizations can use. If you look at it, I've listed out some of the features that this particular tool has today. We are able to accelerate the application development, that's on quantum. You get a centralized data store. You can do experimentation tracking. This is a feature that we are inheriting from our classical implementation, which is already there. We will also allow you to benchmark the algorithms, different algorithms. And we will also allow you to prioritize your experiments. In addition to that, there is one more thing that we are working on to incorporate in this tool, and that is resource estimation. That's something that is very useful. Coming from a service industry, that is what many of our customers also ask for. So we are working on a tool to satisfy this. One final thing about what we have done. So recently, last week I was in Australia. There was this Azure Quantum Week that was organized by the government of South Australia, and Microsoft, KPMG and TCS together participated and conducted this. As part of this event, which was a week-long event, we had a few sessions, a few talks the way I'm doing it today. We had a couple of talks on the use cases, individual use cases there. We had a hackathon that was conducted and a few ideation workshops with some of the prospective customers there. So entire day sitting with a group of people, say 10 or 15, and we try to figure out use cases that could work for quantum and in what way they could be useful. And the 4 topics that are listed here at the top, these are the use cases on which our team has given talks, and this came directly from the people who are developing this within our team. So after listening to all of this, what do we propose to our customers? Now, put yourself into the shoes of your customer. What do you want? The first thing you would want is an instant ROI. What is the returns that I get when I invest in something, right? And if you're doing something for me, how fast can you do that? Now, considering quantum, the state that it is in today, you can think about what classical was 30 years back. That is where we are with quantum today, right? Even the hardwares, when you look around, they are not ready for commercial use. Most of the hardwares that are available, whether it is IBM, whether it is D-Wave, whether it is somebody else, they mention that this is for exploration and experimentation purpose. You cannot go ahead and do commercialization. So then what do we tell the customer? And will customer listen to us? Okay, that is another important thing. So This is a journey that we tell the customer to follow. We have already told you that the time to start on quantum is now, and Dr. Anupama already said why it is so important to start today. You don't want to be caught off guard 4 years down the line or 5 years down the line. So today is when you want to do it. So as part of that, this is the journey we propose. We tell them we can start with evangelize. That is, we can give you quantum awareness, we can help build your skills on quantum, and if you want to set up a COE, we can do that for you. Now, this is useful for the customers, for organizations who are very new to quantum, who do not know much about it, and they want to upscale themselves. And we do have customers who come to us with this particular proposition as well. The next stage is analyze. In this stage, we sit with the customer and we scan their portfolio of use cases. We try to identify the use cases that could be relevant on quantum, and we tell them in what priority they could implement those or they could start working on those. The third phase, which is very important, is implementation of POCs of those use cases. Now, listen to this, the POC of the use cases, not the commercial version. Today, when we are implementing, we start with POCs to show them, to prove to them that this could be done on quantum, and also to see if there is some kind of quantum benefit that you can see today. And if you do that, believe me, tomorrow when you have better hardware available, you would also be able to see the quantum advantage there. Now, how soon? That will depend. Finally, we talk about showcase and scaling, where we say you can scale the POCs that we are doing with you. We can execute these on the hardware. Now, the hardware implementation comes now because, the real cost of implementing quantum comes when you bring in hardware into the picture. The initial first 3 stages could be done on simulators to get a feel of it, to come out with a POC. But the final stage, if you want to do it on hardware, showcase and scale is the way to go. So now, depending on what the customer, where the customer is, at what level he or she is in quantum, they could be in any of these stages. And there could be a timeline that can be demonstrated here, like you can have 4 to 8 weeks for the first 2 stages, and then you have 8 weeks for the next, that is co-innovate stage. That could depend or differ depending on what kind of use case you are tackling, what kind of a customer you are getting. Like one of the customers who came to us for evangelize, they wanted us to do this evangelization for them for 6 months. So not 4 or 8 weeks, but much more than that. Right? So it also depends on what they want. So finally, we need you. We need bright minds to come and work with us. If you have to do some internship projects that you are interested in, and believe me, till today we have been working with a few organizations and we have been getting students who do their internship with us. There have been some who have done it on in the area of cryptography, in the area of chemistry. And if you are interested to do that for machine learning and optimization use cases, specifically finance is something that we are looking for, then you are most welcome. And these are some of the contacts that I have mentioned over here, the third one being me, Godfrey Matthias. And Paridhi Rahabar is the one who deals with all the student-related activities from our side. So you can contact us on any of these emails and we'll get back to you. We can have a discussion on that and we can say where you fit and you'll be most welcome. So thank you. Thanks for giving me a chance here. So I can take up a few questions now if there are any.
If there are no questions, I have a question.
Sure.
You showed about something about the segmentation of that kidney. So what was the method and what was the finding, if something can be
So yeah, so this.
Everything cannot be disclosed or can be disclosed.
Right. So this kidney tumor segmentation is actually something that is recently started. I might not be the right person to talk about it, but what I can say is, so what we have started working on is the classical part of it. And we are now working with that team, the research team, to see if we can bring in some quantum techniques within it. What we have seen is there is some segmentation related activity being done there. We do not yet know what technique the research team is applying for now, but that is something that we are focusing on because we come with a strong background on that part for quantum as well.
Thank you. I had a question. Sir, you were mentioning constantly the difference between gate-based quantum computing and quantum annealing. So can you briefly explain us the differences on a hardware and a software level that you face while using them?
Okay. So when we talk about gate-based machines, we are talking in terms of circuits. So you have to design circuits that can solve your purpose. When we talk of the annealers, quantum annealers, that depends on the minimization technique of the energy levels. So it's not really the circuit development that you need to do, but rather work on a different concept of minimizing the energy state of that system. Right? And that is how you tackle those problems there. So the way you do it for gate-based is you have to create your new circuits to solve one of your purpose, but in this case, it's different. And what we have seen is annealing techniques are usually good for optimization kind of problems only. That is what we have seen till now. So if you really want to do something like a machine learning or cybersecurity or chemistry, where you do not have, where you have to do something other than optimization, gate-based machines are your best bets. And if it is optimization, then the annealers.
Thank you, sir.
Oh, and as far as software is concerned, your second part, if you know Python, you know everything. Not that simple, but you need to understand the concepts behind the two. I mean, you do know Python, but then concepts is also something important. Now, one example that I can give you, you already know about Qiskit, right? That is for gate-based machines. Then you have D-Wave, who have their own SDKs that they provide for annealing. That is also Python-based, but the way you write the code, the way you conceptualize a solution, that is different over there.
Good afternoon, sir. As I am a student of MBA, I am very much interested in finance. So I want to ask what would be the quantum's role in the future of finance industry and what skills should I have for the coming quantum age?
So what we have seen is in the area of finance,
Yes, sir.
quantum is going to play a very big role. Now, why I say that is, I don't have the slide over here, but we do have one slide, not here, where we actually did a study about the different finance organizations that are working in the area of quantum, and we were shocked or rather surprised to see that there's a huge list over there. Now, as Anupama madam already mentioned, I'm not sure if you're there for that, but JP Morgan Chase is already there. Then we have Deutsche Bank also coming in. There's a huge list of organizations already working. And if you see the use cases also, I think here, though this is not an exhaustive list, the first one over here, which talks about BFSI cases, you see when you do these use cases in classical with very high complexity, it becomes difficult to solve them or they take a long time to solve, right? So that is where we feel quantum can bring in some kind of a benefit there today. Benefits, very minor, but maybe you'll not be able to justify that today because the cost is very high. 3 or 4 years down the line, or maybe a little more as well, you could see that there is a lot of development happening already in the area of hardware. There is a lot of work going on in the area of error correction as well. So today what you see, tomorrow will be really different than what it is today, right? You can expect better machines, better software, and you'll be able to tackle even complex solutions is what I feel. And what was your last question there?
So what should be the skills that we should be developing for this?
Skills, domain knowledge is very important. If you want to tackle something like, say, finance, that's the first thing. And probably I believe your quantum formulations, right? The way you formulate problems, that is something you need to develop. I mean, finally, once you know that technique, you can program it in whichever language, whether it is Python or something else. But that formulation thing is very important, is what I feel.
Thank you, sir.
Hello, good afternoon. Hello, good afternoon. I am a student of BTech, Jamia West Jamia. As you said earlier, QKD is not so much development. We have to take a great work around it. So QKD is basically working on encryption and decryption technique. That means QKD have been proven to be perfectly secure, but no such proof is available for PQC. But PQC relies on assumptions that for mathematical models. So how QKD do not rely with PQC? Because PQC, as we use PQC, it does not really secure. But for QKD, we need to secure it. Because if we transmit the equations for encryption and decryption, it must be secure. So how we can prove it in future aspects?
Very good question. And that is something that many of the research organizations are already working on. I believe I do not have an answer for that part today, especially because I do not come from the cybersecurity background. But what I know is I don't think anybody has an answer for that today other than me. I mean, even I don't have it, so nobody else also might be having it. So this is a big topic of research today, right? And it's not just the techniques that you're using, but even the hardwares. Like today, whatever mechanisms you use, whatever infrastructure you have, what we believe is QKD cannot be supported on that. So you need to have a completely different setup is what we believe. Right? As far as your answer is concerned, really sorry, I'll not be able to answer that.
Good evening, sir. So, in the previous slide where you showed about the breast cancer image, so one of the basic problems that we would face in a machine learning is like we have many diagnostic centers, many companies manufacturing X-ray machines, for example, and we would be having different version differences and even the maintenance. So image distortion or noise could be it could be affected in the images. So how could we generalize this quantum machine learning for on a larger scale because of the set differences with a machine in here and a machine just 1 kilometer away, some other diagnostic, they would be producing different quality of images.
Correct.
So how can we over tackle it with quantum machine learning?
Well, this is not really a quantum problem, but data in general. So now you are talking about this use case. I'll tell you about this use case, time series forecasting. Now here also, when we are talking in terms of stocks, different providers of data give you data in different form, correct? If you're looking at the Indian stock market, we might get data in some form. If you're looking at the US stock market, there is another thing. Now, in this case, what happens is, for one of the stocks that we considered, say ONGC's dependent variables are few of the Indian stocks, and there are certain stocks outside as well, like the USD to INR conversion rate. Then you have the Brent crude price, right? They are not really Indian values. You need to pick them up from somewhere else. Now, when we pick all of this data together, you see there is a big difference. Some might have some data missing because Saturday, Sunday might not be holiday for them. You might see there are certain public holidays coming in for our stocks, not for them. So then you have to do that data management, right? So we perform a step before we do anything else, and that is data sanitization. And that really depends on what kind of data you are trying to tackle here. Now, in this case, we know what could be the problems. So we sanitize the data accordingly, like front filling or back filling, something like that. In case of images also, there are certain things that we need to do, which again could differ based on what kind of a use case you are tackling, right? So I might not be able to give a general answer to that, specific to the images, but there would be techniques to do that as well. If there are no more, oh, there is one, okay.
So can I ask you a question generalized to your company TCS? What kind of brilliant mind you are looking for? Means if you are wondering for a student, what qualities it might they might have to be the part of TCS?
You mean you're talking about internship or you're talking about full-time?
Both.
Both, okay. So the general answer to this would be, if you're passionate about what you're doing, we are ready to hire you. Now, if you're talking about quantum, any specific field that you want to work, if you come up with some idea, you don't need to implement. If you have some idea about what you want to do, you can come talk to us, because we are open to any kind of domain. As you have seen, it's not just one or two domains that we are tackling. We work with different organizations, we work with different customers, starting from banking to security to manufacturing, any domain and any kind of problem. If you have some idea, you can come talk to us and we can work out something. If no more questions, then
I think we can conclude there is a
sure.
Yeah. So thanks a lot. I would like to thank both the speakers, Dr. Anupamari and Dr. Godfrey. So we had an excellent insight into what the industry is doing and how our academic knowledge can be applied there. And also, on the behalf of whatever I know, we are part of both the IIT Jodhpur has signed an MOU with both IBM as an academic partner, and also we are also a partner with TCS. So the collaboration we can do both of them, so the access to open to all the IIT JA students who are present here, so you can make use of this like internship or attending any workshop or whatever the interaction you want to take it forward. I would like to request Anupam was mentioning something about IBM for especially for the other researchers from the, you can.
So I'm sorry guys, I didn't mention anything about internship, and when you mentioned, I realized that students are here, so we should have mentioned that. So I'm from IBM Research, and IBM also hires interns and IBM Research also. So IBM Research, typically we have a summer internship, which is a paid internship for 3 months. And the applications actually start in the month of September. So we have already submitted all proposals for next summer, and you're typically asked to apply now. So just go on to the IBM Research webpage. If any of the internship proposal excite you, feel free to apply. And it's not restricted to just IIT Jodhpur student. I mean, any student can apply as long as you feel the research problem is interesting. And barring the paid internship of this 3 months, we also do a lot of these remote mentoring, wherein the student doesn't have to travel and come and work with us in our locations, Delhi and Bangalore, but you can actually work with us, and all you get is a papers or the certificate is there, but we can work together for a paper collaboration and things like that. We can't do patents, and there's no payment or finance things involved in that, but that's round the year. It's more about the mentor and the mentee and how they work and how long they wish to work. Also for jobs, it's open, so feel free to look at the portal and apply. So that's all I can say. Yeah, but thank you.
Yeah, I would like to request Professor Subhashish Banerjee to present the memento to the speaker. Subhashish Banerjee, please. Yeah. You can bring the memento.
Thank you, everyone.
So, so we conclude this session on the quantum technology, and in continuation of this, tomorrow at 11 o'clock at the physics seminar room, there is two talks and followed by a technical session. So there are about 12 technical sessions plus some poster presentation on quantum technology. The talk will be delivered by professor from IISER Kolkata, Professor Panigragi, some of you might know already. So he will give you a talk at 11 o'clock. So kindly those who want to get into more into the physics or the basic aspects of this and look at what are the applications. One of the things he will speak about tomorrow is how the QKD network is being implemented in some of the cities like in Austrian capital, etc. All that he will speak about. So those who are interested, kindly join in the physics seminar room 11 o'clock. Okay. So thank you very much for your attention, and we thank organizers on giving the opportunity. I also thank both the speakers, both on the behalf of my behalf as well as on the institute behalf, on the behalf of INE, spending their valuable time with us and giving an insight. Thank you very much. So we conclude this session. I believe there is a tea is available outside, I believe. You can join. Thank you.
So, dear students, so dear students, so next session we have about smart infrastructure. So Dr. Alok Nath De, President of Samsung India, they will discuss about the 6G system over India. Okay, so we will start from 4:15.
Hello, check.
Good evening, everyone. I kindly request to come forward. Everyone who is sitting at the back, you can come forward. Yeah. So great, welcome back for our next session. So this is first session on smart infrastructure. I would like to invite Professor Neeraj Jain on the dais. He works in the area of brain research. He was ex-director of NBRC National Brain Research Center. He has around 80 publications in his name and few patents. And currently is heading the School of AI and Data Science at IIT Jodhpur. So Professor Neeraj, I would like to request you to introduce Dr. Day.
Thank you, Subir. So this morning I was chairing a session where our own Dr. Rajendra Nagar talked about metaverse. And among many things that he talked in metaverse was we need high-speed, reliable connectivity. And in the evening, I happened to chair a session where we are going to talk of 6G-enabled world. And it's very clear that we can't have a realistic metaverse unless we have a high-speed connectivity. So we are very fortunate to have Dr. Alok Nath Dey here this afternoon to tell all about future of connectivity in India as well as in the world. He is an extremely distinguished person, and I'll tell you only in brief about his accomplishment and his background. He is Executive Consulting Director and has been Chief Technology Officer at Samsung India for over a decade. And as you can see, he is also an adjunct professor at ISC and IIT Jodhpur. He has also served as a visiting and adjunct professor at IIT Roorkee and IIT Delhi. He has over 30 years of industry experience, including in BEL, Nortel, Ericsson, where he was a country director, and Samsung Electronics, of course, where he is corporate vice president as well. He is BTech from IIT Kharagpur, ME from Indian Institute of Science, Bangalore, and then PhD from McGill in Montreal, Canada. He has received a number of awards. Few of them is one I'll mention. He received Alexander Graham Bell Prize in Canada, IET Memorial Award for Distinguished Contribution in Electronics and Communication, IDC Inside Award for Innovation in Telecoms, Inno Award for Entrepreneurship, SOCAM Award, and many, many more. I don't want to take too much time because this session is already delayed. He's been advising Government of India for various technology that are being introduced, how to do that, what to do, what not to do. So he is the expert who is making things happen in the country, working through the government, in addition to being a technologist. He is a senior member of IEEE. He is chair-elect 2022 of IEEE Bangalore section. He is a fellow of IEI and in the National Council, which represents Electronics and Telecom Division. He promotes science and technology linkage very actively. That's very important. Traditionally, we think science is different, technology is very different. And as you have been hearing since yesterday, it's a continuum. You don't know where science starts, where technology starts, where science ends, where technology ends. It's a continuum. They all have to feed into each other, preferably without any thought going into whether you're doing science or you're doing technology. They are one and the same thing, two aspects. We just divide them for the sake of convenience, which I think is an artificial boundary. And the more we get rid of it, the better it is. And he is the person who believes in that. He's been spearheading Samsung's investment in Indian startups through Samsung Venture, and he's also himself an angel investor. His main research interest is in cyber physical systems with underlying technologies of AI, augmented intelligence, and secure IoT. I invite Dr. Dey on the stage to deliver his talk. Thank you, Dr. Dey, for coming here. And before he starts his talk, I'd like to invite our Deputy Director, Professor Vadera, to give him a bouquet. Welcome him.
Okay, so good afternoon, good evening, almost. We're going to talk about envisioning 6G enabled world. And I just want to have 3 questions asked. One is, how many of you are in the undergraduate? Okay. And how many of you are from outside IIT Jodhpur? Okay. And how many of you are non-IT, ECS, outside that, other backgrounds? Okay. Thank you. Now, I think I just wanted to make sure. So those who know the subject, I'm a little bit adjusting. So those who know the subject, I request them to listen and also see. You can see the slides. Slides are in bit details. So you can benefit from both media. And those who are not from the background, you just listen to me. You don't need to bother too much on the slides. Just the skeleton and then listen. Okay, so I'll adjust it that way. Thank you. And last time when I visited, after joining this adjunct positions in July visit, there was this flooding and a lot of water. On one hand, there was a lot of water on the road, but you didn't have the water inside the campus, so it is a difficult moment. But nonetheless, I saw the spirit, and I could still achieve what I wanted to have, those dialogues and have interactions with many professors, 25 of them, in the midst of all of this. So I really appreciate and applaud your spirit that is there. And we were talking to Deputy Director. I know our Director, Professor Santanu Chaudhary, for quite long period. He's been senior in IIT Kharagpur. And I could see that process, is very simple, smooth, and progressing very well as an institute, even if it's in Jodhpur. We've seen the flight while coming. A lot of people here are coming for pleasure trip, right? And so in the middle of it, a couple of us are trying to talk about 6G or metallurgical coming to IIT. So it's a good experience. So with that, I hope you are kind of switched over to this new topic that I'm going to talk. So just for the others to talk about it, and before even going to 6G, a little bit of brushing up. I started working in the 2nd generation. Before that itself, 1st generation, I was in Nortel Networks, and that time we were doing 2nd generation of activities of the Nortel, Northern Telecom, Bell Northern Research. They were also building equipments for this, which today Ericsson, Nokia, Samsung, Huawei, many others are building. We were doing that then. And the 1st generation is all about analog communications, which most of us have forgotten how it works, except few people who does the circuitry of analog. The power of analog is still there, but most of it with these digital transformations, mostly we are moving to the digital world. So 2G started with that, and 2G was all about voice communications. Everything 2 people are talking, and it's people to people, and it's only voice. That was the 2G. Then we started bringing in data that we call 2.5G, GPRS, Edge. These are the kind of 2.75G, because to move from one G to the other, you have to have something very significant. So when you had small data here and there, we didn't even call 3G, but between 2G and 3G, you kind of started moving gradually into it, and then finally 3G gave a lot of data. In the 4G world, then we started bringing in not just the data, but multimedia data. The broad concepts got defined, and in 5G, we started moving in even some of the things that are there, Internet of Things, but that is wireline connected, but also want to do some of these things we started bringing. Not fully, 6G will take it, but we have started doing it. So today we are talking about 5G, and this 5G itself in India is going to be deployed this year end, few cities, and by January I think major cities we will be having. We had reasons why it got a little bit delayed. for standardization, things that we wanted to do, the spectrums and many other reasons. But nonetheless, as Samsung, we launched it 2019. 2019 March, we launched in Korea, and 3 operators together with a common infrastructure. That is a kind of competition but also collaboration. You hear that, but that was a great example that how simultaneously with government support we can launch but still compete between LG, Samsung or other operators among themselves. Today, this January, there is already 10 million subscribers that are there in 5G in South Korea. Then US and other places, and we'll start to see the benefit of it in this year. Now, in this 5G world, there were 3 things that were very, very important. Because every time you design a system, and when I'm talking, you as a student can think it of in your system, these concepts, right? You don't have to, even if you're not a 5G person or communications, you can still think it of. How to define a bigger systems. So you have to have few impacts that will drive. So 3 things, there are many things. If you see the right side, you will see like an octagon or decagon kind of it, in which there are many points. You want to measure spectrum efficiency. Same spectrum, how many users you can accommodate. How much can you be mobile? Can you cover pedestrians at the same time, very high speed vehicles? How much area traffic capacity in a particular area, how much capacity that you can handle when everybody talks together, can you handle, right? How much are you doing energy consumptions? Network energy, if I have these many users, how efficient it is. So all these, from one generation to the other generation, there is an improvement. On top of all those voice data that I talked about, there is this improvement in those. So when 5G came, 3 things we said. That enhanced mobile broadband, whatever bandwidth that we are getting in wireless. Now you may not get fully, but fine, fraction of it, but 1/5 of it, 1/10 of it, say so and do it that way. That was one of them. Second is ultra reliable and low latency. These are contradictory, because if I can take a lot of processing time, I can make it reliable because I'm checking many things, right? So I can make it reliable. But the trade-off, and that is an engineering things, right? We always live with the trade-off. So how can I make low latency but also still reliable? So can you find techniques for that? And third thing is the massive machine type communication. Massive did not happen, but machine type communications happened. And below you can see that, it is a timeline. We started in 2016. Now I wanted to highlight this point again. If you see this generation, each one takes almost a decade. Like I'm talking 1993, that when I was talking 2G, and if you take each one, 8 to 10 years to take a generation. So there's a lot of research that goes, validations, deployment, trial, to make system happen. And I started working when I joined Samsung in 2011 as CTO, and we started, my first assignment was 5G research. And we formed a team and started looking into MAC layers and other things, right? So 11 to 15 almost went into research. And same thing we are now doing for the 6G. This is a research phase, not standardization. After a lot of people doing research, then we decide, now let's form a standard body and see who has best kind of solution. But in the beginning, we don't know. We talk, we publish, we kind of chit-chat, have conferences, but no standards. So 16 it started, and this 21, the 5G got closed. So it took 5-6 years for standardization to happen, release 16, 17. It started from 14, 15, 16, 17. These releases, each one taking 1.5-2 years time, these are standard body who does that. So with that, this happened. And now we are talking about going into the next phase of it. And just from Samsung, I wanted to also explain that there was this Winter Olympics happening in 2018 in Pyeongchang. Our whole goal was Japan Summer Olympics would be final product launched, and Winter Olympics 2 years before, as you know, 4 years, but it is interspersed 2 years. So Pyeongchang Olympics, in the stadium, we had launched it, and then people could do this video, right? Even though you are sitting somewhere in the stadium, but if you want to see how to, this particular player's view or the athlete's view, you could actually get it from your seat. Or even if you are not in an advantageous positions, you can get another view. So we started having many cameras, 100 different views, and you can choose your view irrespective of where you have sat. So this is a kind of one game, and with a bigger devices to try it out in the beginning. But over time we did it in the form factor, and now in India, I was just telling that even from Samsung we have almost 20 plus 5G enabled devices are available in India. They're just there. Once the system, the equipment is up, people can get the benefit of it. So I think you got the hang of the 5G. Just to give you a little bit of few dots here and there, when we test it out in that 5 years or even during the standards, you have to do a lot of trials. So first we did, how does it perform throughput with a particular frequency? That is less noisy, less atmospheric condition, does it work? Then we say, okay, actually move to the right spectrum. Then he said, no fixed, but when people move around, when they walk, am I getting similar throughput? And what do I need to improve upon? Then we made bicycle or scooters and motors. Then we made it to the trains, base stations and CP, they are communicating. Then we did it under tunnels. So it's not that you can solve the whole problem in one go. You just have to take it in pieces, perfect it, and then move to the next step. So this is what we did. And obviously there is benefit for passengers, there is benefit for train operators that you can see already from there. So first we did in UK a 5G, fixed home for high-speed internet and video on demand. Then the train, you can see that. And these are little futuristic when 5G vehicle to everything, because 6G is getting designed, but 5G will be there for a while. So what are the other applications that you can bring? So today when we launched 5G globally, we were talking about how to download. Most of the use cases is fast download of a movie. That a 2 hours, 3 hours movie used to take, let's say, 10 minutes to download, but now you can do it in a minute or a few seconds to download. So that was the first kind of it. Then some interactive gaming in the malls. That was the second. But they cannot be sustained applications. So people are thinking, and obviously connected traffic light, high definition map update, because as you are moving faster, can the map be refreshed quickly so that you are not stale and you can get the updated information as you are driving faster. So these are some applications that are being talked about. So just to conclude on this part before I start this 6G, is in the system, the traffic lights are becoming very important even in smart city context. So there is a 5G core. You should know this, how the whole system works. There are 3-4 parts of it. One is a 5G core. Core network is the farthest one from the device, and they are master control, and they have wide coverage across cities even necessary. Then you have the access units that are closer to let's say IIT Jodhpur could have closer to one. And then you have street lights and things which are carrying information for the last mile and then going to your home. So for example, if it's a smart city, even though you may not do a gigabit traffic yourself, but you can have an LTE 4G small cell, some public Wi-Fi, some IoT sensors, CCTV camera, digital signage. When you add all these up, it becomes a gigabit traffic. And then backhaul becomes your 5G. So it's not just the phone and what you do, but sometimes smaller traffic you can aggregate and use 5G as a backhaul. So we are going to do in India for both the backhauls as well as 5G to the end to do that. So I hope you got fairly good idea quickly on what the 5G's thing and how this got evolved over time between 2011, and now we are in 21, 22. It got launched and getting deployed in many countries. So with that, let me move to the futuristic part of it. Obviously, we will not get there in one day. We are planning 2030 because it's already 21, 2. And the standards just this year started happening. We don't call it 6G yet. We call it B5G, beyond 5G. So 3 years will go into beyond 5G mode. There might be some software upgrades of 5G with that, but true 6G will come. So the harder technologies that will make a big breakthrough, that will take longer. But there are some small hanging fruits. There are some immediate needs that can be covered in between. So that's your B5G story that will come. So 3 things, the macro scenarios changing, users experiencing rich media service. So multimedia is going to be integral part of our communication. It's not going to be some small special cases. Everything that video or even bigger, I'll talk about them in future, but the holistic multimedia would be part of it. Second, humans becoming more and more connected. It's a hyper-connected world. And with realizations of Internet of Things, it is not going to be people to people, people to machines, and even machine to machine communication. Today, 5G provides some people to machine communication, but machine to machine is much lesser. And I think in the 6G time, we are expecting things to things communications to grow. And it's a cyber physical systems, or what we call phygital, physical and digital. So 6G systems is a backbone for these infrastructure where lots of things of logistics or agriculture, these are physical things, home, buildings, but you are connecting to cyber world and you need an infra to connect it. And therefore, this should serve as that. So I hope you got that. I had a chance to co-edit this book. This is the world's first book on 6G mobile wireless networks. We published it last year, March timeframe from the Springer. And a couple of us from Samsung as well as other professors we connected. And this has been, I think you can have a look into that and reference. So I'm going to take some of the points from there to highlight envisioning the 6G part. So it looks, those who know, you can read details, but those who are from other fields, junior, yet to learn, then you can listen to me. So I'll tell you very simply. So currently it's a gigahertz communications. Earlier we talked about megahertz, you understand that, and gigahertz, and it's a terahertz. So it's another 10 cube differences always, mega to giga to this. Why are we moving? Have we used all of these? No, because different utility services are there, like satellite is using, maritime is using, and we have chosen few frequency bands in which we can operate nicely. But as you move up, what is the challenge? If we can do it in lower, why can't I do it in higher? The challenge is, the atmospheric propagation and the losses, do you know how oxygen and water works, and the absorption lines, if you study there, they match those frequencies wavelength. And therefore, you will have a high absorptions. If you communicate here, In 4G, it can go out, but in 6G, with the walls and materials, it might just stay inside and not go outside unless you have a mechanism to deal with it. So therefore, that's even inside, but even outside, atmospheric part is quite heavy. So that is a challenge. But then if so much challenge, why are you going? Because we want broadband. We want to have a lot of things, multimedia services. Now, a fundamental principle of electronics communication is, when you have a frequency, how much you can get around it. If you have a lower frequency, only that much bandwidth you can get around. This is called fractional bandwidth around that. So if you don't move up, your fractional bandwidth, 1% of 100 gigahertz versus 1% of 1000 gigahertz would be at a different level, right? So you need that. Now, obviously, techniques, but fundamentally you need this higher bandwidth to do it. So that is one reason to do it. Now people are saying there are orthogonal frequency division multiplexing or many other techniques. Question is, which kind of waveform will be stable under that? That's a question. And then people are also looking into what kind of semiconductor, because this is in the physical layer, right? When you create the waveforms and this processing. So is silicon good enough? The semiconductor people are looking from there. Because I'm going to consume a lot of power, can it be good? Because today we are talking, and this is sustainability things that we are talking, your generation has to even look much more onto sustainable. We have already built many solutions, but is it energy efficient? Is it sustainable? Is it harmful for radiations? These are fundamental questions that previous generation did try to solve, but didn't focus. And also it was not a big issue because lesser people were using these equipments. But now more and more people, more high bandwidth, more data all the time, and therefore we need to be much more concerned about this. So whether you do indium phosphide or gallium arsenide or silicon germanium mixture, these are things that the semiconductor people are looking into it. And the last point in this is, since you cannot do, because the absorptions are there, typically in communication there is a transmitter and a receiver. And one receiver could accept. But now that is not sufficient. You need multipath and multiple antennas, and we call antenna arrays. And there is a concept called MIMO, multiple input, multiple output. So now we are going to talk about ultra MIMO in the 6G and have many receivers, and can it even look from different directions. So all these variations are the topic under this terahertz communication. I hope you got a little bit of gist of it. Why we move it up, what are the challenges, what are the waveforms that people have to research to get it, semiconductor support, and then antenna arrays that are absolutely necessary. So if you have got this, then let me go to the other part of it. So I have 7 such pillars, and that is the crux of my talk. So the second point is network configuration for precision. Now again, you don't have to understand fully, but what is important is in the current configuration, we have connected few points and it works. So more or less it is a stable configuration. It is a static configurations in the current network. But we want to bring dynamic configurations. We call it mesh network or ad hoc network. Can I form quickly ad hoc? For example, if I have a drones and there is a disaster, the time that you need communication, those poles, that's the time it goes down, right? Because that is when you want to communicate. But they are down. So what's the utility? So from disaster management standpoint, it is a disaster, right? So if I bring in drones from some place and fly over, and can it quickly form a network quickly, an ad hoc network to be able to give those supports and supply. This will be studied very deeply in this 6G. ad hoc and the mesh network, and the dynamic connections, configurations, optimizations, automatic deleting of nodes, connecting nodes. This would be a big piece of it. The second important point is, when you do this, another thing in the world, they're coming from different angles. You know, in the past, even Samsung and Ericsson and Nokia, Huawei, I mentioned, you know, there are only few players in the world that are playing these network equipments, and they are big, and it has to be managed. So there is this whole movement of open source. Can I build each layers very nicely? Because if we have to make it dynamic, it helps in both. But also, you know, it can be vendor agnostic. I can buy one layer from one vendor, but the second layer from another. Even if somebody goes out of business, I can plug it in and it will work. Otherwise, it's a big headache, right? How will you change this whole system and the investment that an operator has made? So open source is becoming a very, very important thing. And we have open RAN, open network configurations management, ONAP. These are the kind of open source that are coming. As a movement already started, but I think in 6G time we will have many such modules. So this is a second point. And the third point in this is this current communications is all two-dimensional, meaning all on the earth, right? Like we all are doing that. So two challenges. One is, you know, there is a lot of radiations, and people are becoming concerned about this, that earlier it used to be few big towers here and there, and they used to radiate. But more you go 5G, 6G, you have to have many such towers, but smaller in size. But you have to get those places, and people get concerned when it's next to their home. Therefore, can I elevate them up, right? Not on the ground, these networks. And therefore, the UAVs and things like that, they can be my HAPs. So it is becoming a 3D world in the communications. So you go up, and maybe base stations, part of it, some of the radiations elements could be from there, and we configure. Not just that, the satellite communications are coming. They were mainly for defense and other purposes, but now it's becoming mainstream. You want to do maritime. So all of these are getting combined, and in 6G, non-terrestrial network is an important component. Beyond terrestrial network, how can you do to connect with them? If somebody has gone to the seas and fishermen and you want to send an alert, how do you do that? Today it's a different system. They're not part of the main system. They are operated by a separate network around the maritime. So can we make it mainstream? And also, you know, the radiations and other things. So I think you got network configurations, how we can make it dynamic, ad hoc network, open source modules, and also taking it non-terrestrial beyond that. Got it? Okay. So then I come to the third point. This is machine type communications. So, as I told, in 5G itself there is certain machine connected, but the standards do not go very far. And that's perfectly fine because we're connecting and there is a separate network. But 5G, in 5G you will hear two kinds of things. One is called 5G new radio, NR. So that is supporting already. But what we are trying to look, two things. One is very low power sensors and energy harvesters, right? These kinds of things where less battery would be required, and how do I integrate them? Low power energy kind of consumption. So this is one thread. This is there already in Bluetooth and many others separately, but as part of the mainstream. But more than that, I think the 6G is starting to define this MTC, machine type communication. In that, there are two categories. One is critical, one is massive. See, sometimes you want to massively connect, for example, a big city that you want to connect. So it's a massively connected, but delays are okay, little bit here and there. So it's not critical. But for example, if you are driving a car and you are talking autonomous car, then it's a critical, so it's a CMTC. So we are making a table of CMTC, MMTC, and then very many combination of this. For example, if it's a factory monitoring, it may be one time. If it's a robotic aided surgery, it may be another type. If it's an autonomous driving, it's another type. If it's a precision agriculture, it's another type. Which category it is and what provisions, what elements have we been able to define so that the system will be built. I hope you got the machine type communications. Today it's very small, but I think this fundamental categorizations of these and a solution being present for each of them. What will you shut down? How will you make it ultra reliable? If it's critical, can you detect automatically what it is, switch over to other? That's another part of it, detection. But once you have detected, what is the mechanism to do that? And that takes it to the next automatic. How do you get it? That is an AI part of it. And can you switch over from one to the other in an applications? That's one part of it. But once you got it, that is your communication. Again, it's very crowded, so don't worry for this. This is for another talk some other time with the specialists. But augmented intelligence, I just want to highlight again what will be different from today to 6G's AI. Now, these are not frozen completely, but there is concurrence coming out already from discussions and people that people want to achieve. Can they achieve? Not everybody is knowing. So here, one of the things, as I said, this dynamism is an important thing. So for example, many a times we see the spectrum that are there are many times unused and nobody is able to use it. So unutilized spectrum, how do you give it an AI to choose this? Now, between two operators, let's assume that they have free and people don't mind. Because if I'm not using, in any case I'm not using, if I'm giving it to somebody, I can earn some money, right? Even as an operator, because in any case he has a customer at this point, so why not to give it? And even government and regulators would not like somebody to just book it and not use it, because that's, other could have used it. So one is the allocations in the beginning. I'm not talking that. I'm saying after allocations, people have spent. But how do they share with each other in a structured way and make money out of it, right? One is going to give it. Now, you can send lots of information, but that people don't want. First of all, it's heavy on the system. Second, one operator would not like to give everything. So they want to define minimum information that needs to be passed to be able to do this dynamic spectrum and switch back. So this is where the AI, I think there is a lot of papers you will see research that is going on in dynamic spectrum allocations using AI. One other AI as a big goal, big hairy goal, I doubt whether we'll be able to get there by 2030, but there will be some movement that is happening, which is a big desire, which is called explainable AI. And this in the communication is being set as a target. So first of all, AI has to be at all layers. Today, when I see 5G, there are also some AI. But this is posteriori, not a priori thought that we have put. And therefore, you can only do here and there some tweaking. But if you have to do it, fundamentally we design. But one of the challenges, we are saying we will be responsible. And AI has to play that. If AI has to go up the level, it has to become responsible AI. And which means I should be able to explain why it is. Now today when we make 23 layers, those who are doing AI and convolutional neural nets, you can optimize and get the output from here. But if I say an 11th layer, what's going on, you may not be able to tell. You get the end results. It's all fuzzy in between, and we don't have an answer. And therefore, I'm not saying at all layers it has to be there, but can I even slice at 3 more layers and say, yes, this is what is happening. This is what is dropping. So this is XAI, and I think this is, research is about to start in a good way, but we would be loving to have it in the 6G. And the last part of this AI is about this digital twin. In IoT world, we have this, something that is physical, sensors, but I can map it at the digital level, and 6G will operate with many machines that I said, so therefore digital twin, and there is an AI associated with that. So digital twin and your dynamic spectrum allocations type of applications, these are bound to happen, and at all layers. But more than that, if we can make it explainable in various points, then in the legal cases or other things, it will stand. Otherwise, it may not have that weight in the legal framework. You might do inside, but it will be seen non-transparent, non-explainable. Therefore, I think the focus would shift quite a lot towards that. So that was my 4th point. If you are tired, I will stop here. If you want me to go, then 3 more. 3 more? Sure? Okay. With your consent. So the 5th point is edge computing. Now this is already there. Today, IoT, you have your, you cannot do everything on your device. We were starting to send things in the cloud, but cloud maybe delay factor, privacy is going out a little bit, cost is there, month after month you have to pay the servicing fees. And then we bring this edge in between, the device and the cloud, this edge layer. So that's already coming in the IoT world. We have fridge and TVs that are acting as hubs or this edge device in home, which can coordinate few of the other devices. But what will come in the 6G's time is effectively, you want to look into the split compute, that an algorithmic complexity, can I divide between in hardware and in software? What will run in my device? What will go in this edge device? And what will happen? Today's smartphones are still having a lot of processing powers and things, but you don't know future how it will unfold. And don't catch me, this is not, I'm talking from Samsung standpoint or futuristic thing, but we don't know. Because what may happen is it can become a thin client kind of it, right? And everything else is an edge or going to the cloud. Or it may still have processing power, or you may have one with a big processing power, two with a thin clients that you can access. So more if it becomes thin client, more the edge dominance would be there because you don't understand everything to the cloud. And so that kind of role and how do you divide your hardware and software, that partitioning of it, of an algorithm, is something that's being studied very separately and in details. So preserving privacy, high algorithmic complexity, low latency, these are some drivers for this work. And it is true for intelligent transportation systems, intelligent Internet of Things, that's where it is going. So that's taking me to the 6th one. This is a big challenge. As such, in the present world, I think the world's biggest challenge beyond those geopolitical and other things is this security aspect, because I think the people that are developing security solutions versus those who are breaking it, probably there is a mismatch there. And obviously the odds are higher because 99% people, you block 99 doors, but one door is open and the person knows how to enter that door, or by random generation with the computing power. So the odds are not same also, right? So this is a big thing, and we have designed in Samsung, for example, Knox as a very basic from device to root, and then firewalls and other things. We have a Knox 10 layers of security solutions, and that's why this is getting used, or devices, in even US Department of Defense and many other places because of the security that is there. But it's single device. Now I'm talking connected devices, and you know one reason for IoT not flourishing that much that we want to do is the security. Interoperability and security are the two primary. Interoperability, a lot of solutions have come recently. There's a lot of interoperable things, but security is still not fully solved. So this is a complex one. But more than that, in 6G, we are not just talking security. That has to be in any case fixed. And people are also talking privacy, which is your own data shouldn't go out and things like that. So that's the second part. These two are being talked and certain solutions are there. But what we are talking is trustworthiness. We will talk 6G as not secure and private or privacy preserving. We'll talk about is it trustable, trusted. And that means not only your solutions, whoever are your partners and everybody, are they forming the norms? Because otherwise, many apps, you have seen, through the other apps that you can penetrate, and it's still vulnerable. So one way to change this problem, when you wanted to solve how to bring security and trustworthy, the world has defined differently, and this is a revolution. Assume that's the best way to build a trusted system. Because if you think it's a trusted and you add patches, it may be broken. But assume that there is no trust with anybody. And I can work in everybody as long as there is this smart contract and a distributed ledger technology that you could sign it up. So this is where blockchain underneath and distributed ledger, and IoT is a distributed systems, that is going, and you meet these requirements, you are part of it. Whoever meets it, you are part of it. So this is becoming a big thing. It's not just for the 6G systems, but even in a smart contract for procurement, for banking systems. You invest in somebody you don't know, but you put a criteria, only when all those conditions are met, the other person can take the money. You cannot take it before that, right? Whatever you have defined. Even if the money is there, but you can't use it. The gates are not opened. So this trusted system will be built based on that zero trust. And this topic is not a technology topic alone. There is a lot of regulatory and economics and techno-commercials reasons that will be there to build this. But this is the sixth pillar that I wanted to talk. I hope you got the hang of it, and the difference between privacy, that's your own data, who all should see it, how much do they see, when I say delete, is it deleted? That's privacy. Secure, you have a system, you go end-to-end, your WhatsApp and end-to-end secure, encrypted, decrypted, that's your basis for security. Trust is a contract, what you said versus what you are doing, when you are doing. Can I do automatically? Because I cannot look into it manually to do it, therefore the digital platform would accelerate. So with these thoughts, I think 6G is getting designed, particularly the trustworthiness. And the last part I wanted to talk is the rich media service. That's my last slide. The rich media service, at the end of it, you get 6G, but for what? I think, enough of selfies and, video download, movies, this is done. And we wanted to see if all this digital twin and avatar and metaverse, this is an element. And one of the things is hologram, and the holographic displays that need to come, probably to render. And this is non-existent. Many of the other things from 5G, you can incrementally go, even if it's not to the full extent. But we have done the maths for this hologram, and this is not possible in the present because the amount of, let's say, 5G's peak data rate is 20 gigs per second, but a minimum hologram would take 500 gigs per second. Therefore, it's not possible by 5G. This is an unique things that 6G can bring. I hope you understand that some are incremental improvement, some you can do it here, but can do better with some surrounding features, but some you cannot do in today's system, and this is one such thing. And high fidelity hologram and interactive things, and when the machines communications, for example, typically we are going to talk about 10 to the power 7 connections in a square kilometer area. That is the kind of things that we are expecting. Now, okay, that's a theoretical, practical could be a bit less. Then UAV-based swarms that could be formed. So these are going to be having a lot of data. So group communications, these swarm type of communications, hologram, these are some things that will be requiring our 6G. And I talked about digital replica. So all this immersive experience where metaversical things will come, that would definitely require 6G from the application standpoint. So thank you for listening so rapt attentions with that. So I hope you got the 1G, 2G, 3G, 4G's evolutions a bit, the 5G, and the 3 pillars that I talked about, mobile, broadband, throughput, the low latency, ultra reliability, and the machine type communication. And in 6G, going back again, the rich media service, the security and trustworthiness, the edge computing with the split compute, the augmented intelligence, the explainable AI, the machine type communication, the critical and massive MTC and the hybrid of that, the network configuration, the mesh kind of networks, open networks, and then terahertz communication where you can get a lot of bandwidth, spectrum efficiency, less radiations, good receptions to support. This is the foundation, and the last one is the applications to be able to support. This is an end result of it, but obviously each one has its own technology to do that. With that, if you have any questions, I'll be very happy to, or comments. Please. I'm assuming Sumit will not ask difficult questions, but rather give suggestions.
Sir, you mentioned that there are concerns about the health. So we are taking the antennas maybe at the higher level.
This is one possibility, yes.
So in that scenario, will not impact on the, there won't be any impact on the health, or it will be reduced, or what?
No, I think there are multiple ways that it has to be done. It's a good question. One of the ways is to take the base stations, part of it in the drones, or some kind of UAV, maybe a bit bigger than the smaller drones, to float. There is this HAPS, high altitude platforms. So in those kinds of things, then if you can take it up, it may not be happening all the places. It will add one of the elements. See, where there is a concern in dense places, maybe it will be done. But it may have additional delays and other factors that need to be there. So I'm not suggesting, don't get that wrong impression that in 6G it's not going to be in the ground and base stations. It will be still predominantly on the ground. But today we are stuck there. We are releasing ourselves, bringing an additional flexibility to take up as an alternative to an higher altitude or to a remote places. So that is just an augmentations of it. It's not to solve. You have to solve by other means of encasings and even the devices encasings that people are working. By the way, I mean, not to give again a wrong impression, even 5G is well tested, all the specs that are there, the radiation amounts is way lesser. So I don't think there is any concern of it. from the devices standpoint, if there are happen to be next door of your neighbors or your houses, it's just a psychological concern. Many a times it may not have basis, but you will be human being, and so you read somewhere and say, I wish it would not have been next to my door.
Yes, sir. Thank you. Sir, I got inspired from your 7 pillars. So I started thinking for 7G and the 8th pillar.
Okay.
So what could be the 8th pillar in 7G?
That would be, I'm not sure, whether we will go out of the earth and fully there in 7G or in 8G, but definitely satellite will be a very integral part through 6G, and inter-satellite communications would become in the 7G for sure. But whether going to Moon and Mars is part of it, maybe a touching of it, but can be an 8G. Yeah. That's just my explanation. Thank you for thought-provoking question.
Any other question?
Did you get it? If you got it, just give a shout out.
Yeah, there
Thank
is a
you.
question there.
Yeah. Yes, please. If you can just take the mic.
Sir, you are speaking about drones that will float. So there can be some battery problems also. But can we use low altitude satellite that Starlinks are using currently for the 6G version?
Yes, yes. So I didn't mention about these. There would be many kind of devices. The drones is one. There are these LEO satellites, the low Earth orbit satellites that are already being talked about. Even, our Bharti Airtel is already part of it, OneWeb. And there are different constellations that are coming up. It was there way back, but these were medium Earth orbit or geosynchronous Earth orbit. But now we are talking about low Earth orbit because we need low latency. We cannot go very much up, and we have understood how to moderate this. But in low Earth orbit, you need to have many satellites. Like 3 satellites in geo can cover the globe. Like if you have 4 or 5, you have redundancy. Okay? Whereas in this LEO, probably to cover, you may need 500s of them. Okay? And maybe more to have the right coverage. But there are companies that are working, and they will be an integral part of it. Now, it may come from a LEO satellite communications integrated to this, or it may be a 6G driver, but it will intersect someplace, definitely.
Thank you, sir.
So can you tell about Starlink, that's Elon Musk project?
Yes. So you can read, and I'm sure you know more than me. But, I think these are, the whole space is a whole different game. And, if you look into not just Elon Musk, but there are many such programs that are going. One is to go interstellar and, space stations and hotels and be there. And even I see this new field that is coming up, astrobiology, which is, in those spaces, in those floating, how the biology would work, the human beings and animals. And so that's one kind of studies. And then second is obviously, what we talked about, satellite and more sophisticated satellite and the debris management and the space, how would you do that? And third is, at our plane extensions from Earth going up to this. So that's a bigger program. We can talk more separately, but I don't think 6G will connect directly to that. That's much bigger vision on a separate cut, and possibly 7G is the right one. That will not be part of the 6G as it is seen now. I mean, who knows 7-10 years in that. But we can talk more separately. Any other 1 or 2 questions? If you have comments, suggestions, crazy thoughts.
Okay, no other questions? In that, there is one more there. Yeah.
So these all are the new technology, 6G, and so how you can handle these all things, because you have to work on new things. So how you can handle these all things?
No, no, one person doesn't need to solve all the problem. We have like 7 billion people in the world, and many researchers are coming up in different countries. So they are specializing. Even just to give, it's a nice question, but just to give an example, even within Samsung, for example, the physical layer we are doing in, let's say, US, and Mac layer we are doing in India, and the network part of it in Korea. So as a team, each team is focusing on one. So the important thing for success, because these are very deep, these are not shallow research. Can you change a waveform from one to the other, and in high speed, what technology would work in the pedestrian, but how can I scale it up as the same person is speeding up? What do I do it in the other extremes for coding, modulation? These are quite detailed work. So network people focuses on network, the security people focuses on security, but then as in standard body, there is this standard body called 3GPP. That's ETSI in Europe, this standard body is. They have many work groups, and each of these work groups talk about these different aspects, machine type communications, the satellite communications, the security part. And then there are very senior people who is kind of gluing and understanding and giving a ramification from one deficiency to the other group. So they exchange questions between different groups if it is affecting. And through those coordinations, so deeper work, at the same time you do some broader connections across that. So that's the best way. And different work groups are there. For example, University of Oulu in Finland has started the 6G work almost like 3 years back. So they are progressing. Europe has many such funding. And even in India, we have started now. There is path loss communication that IIT Kharagpur is doing. So different institutes are doing different kind of research, and then you aggregate through the standard body.
Thank you, sir.
Okay, I guess, it's time for another talk possibly, and so if there is anything else, you can talk to me separately. Thank you again for listening with rapt attention, and it's my pleasure. Thank you.
Okay. Thank you very much for this very informative talk. Before you leave the stage, we have a little something so that you will remember us by.
Thank you.
Okay, thank you very much. And now we'll have the next session. And Dr. Dipanjan will be chairing this session. Yeah.
Yeah, we will be having next session by Dr. Avinash Sharma from IIIT Hyderabad. Please be seated here. Yeah, it will be a very interesting session on learning-based 3D digitization of humans and terrains. Please be seated here. We will be having next session by Dr. Avinash Sharma. Okay. Okay, we will be starting in 10 minutes. You can come back having a break of 10 minutes, please. We will start in 10 minutes. Okay, thank you.
I was completely surprised to see you. Huh? Podium use करो इस पर I would prefer this. I can walk around this side.
I think they should come back, right? So, dear students, I think the next session is almost about to begin, okay? So, I would request you, all of you, take seats so that we can get started and, keep it on time. So, you can have a small break outside, but please do come back very fast so that we can get started with the next talk. Thank you very much.
well. So I have some affiliation, I mean, and of course Professor Antanu is there, who is the director here and is leading a project where I am also a PI, and a lot of exposure. So some of it also I'll show here what we are doing as part of that project. So first of all, really sorry for scheduling the talk so late. I can understand all of you are exhausted, but I wanted to keep it short. So in that case, maybe we'll see an hour, depending on how, if you're really enjoying, then yes. If not, then maybe you can clap, and I understand that. Right? I used to do that in my school. I studied in a government school. So if somebody is going really long in a talk, clap. Clap once means okay, two means you might have seen in a home also, right? Whenever somebody come and not leaving, then mother will come and ask, you want one more tea? That means over. Okay, I'll try to keep it little bit. So the good thing is there's not much math and not much, what you can say, complicated thing. I'll try to speak very lightweight stuff. Of course, everything requires math. So the caveat is without that nothing works. But for now, I'll keep it light. And I can afford to do that because we are talking about something visual, something graphics, right? Something in computer vision, that's the advantage. That's what I tell my students. You can show a lot of nice figures in your papers and images apart from minimal equations and all. But some other domains like physics and all, they do require a lot of rigorous math or mechanics and all. So basically the talk that I was asked to make a topic of experiential realm of how do we really design some scientific solutions which helps people experience, right? And this is one area which is going very hot right now. And I don't know how many of you have seen WALL-E movie. Anybody has seen Pixar's WALL-E movie? Just raise your hand. Yeah. We recommend see movies. I recommend a lot of my students see selected movies. Right? So WALL-E is a very good movie. Although it's a movie which captures what is a future possibility. Right? In negative way also. How much automation can overpower us and how much virtual reality can overpower us, right? And then Inception is another movie all of you might have seen, I believe, right? So these movies are telling us about a future which could be dangerous, detrimental. But as a scientist, as a researcher, we need to keep working towards that and then bring fairness, ethics and all sort of things, that whatever we can, hoping that a new world, because we can't stop the automation. The way which technology is growing in the last 100 years or 50 years, the pace is really great, and sometimes we believe it's hard to keep up, how to really read so many papers and understand so many systems and product coming. Okay, so I'll not bore you too much about it, but I thought I'll give you very basic context about why we are doing human 3D digitization. So I'll try to talk about it, and then I will mainly focus on how we do it. Okay, so essentially, yeah, I hope it works. It's working a minute before. Okay, so this is my affiliation apart from IIIT, where I did my master's and my PhD at INRIA. I was briefly at Max Planck for my postdoc. Xerox Research I worked, and my PhD was from University of Grenoble, and INRIA is basically a research organization of French government. So jointly they give degree. And interestingly, the place is very beautiful, and Joseph Fourier was born there. I hope all of you know Fourier, right? Fourier series everybody studied, so it's a very nice town. So anyway, so this is my group. So I just want to acknowledge all the current students, and there are also a lot of graduated students who are sitting all there. So we go every year at least twice for an outing, except the lockdown time, of course. So now the focus of this talk is more on how do we really experience the virtual world, or in a way we bridge the gap between a real object, the way we perceive with our all five senses, and the way we can actually digitize it, and then it can be perceived via an technology centric, whatever is the device, at an HMD, let's say, along equipped with haptic, maybe in the way things are moving. So you can really sense the object, you can touch the object, you can smell the object, right? All sort of, your senses, we want to digitize it eventually, right? I'll mainly focus on the vision part of it from my background, okay? So essentially these are the three critical things that are needed in any AR VR system. First thing is you need a good head mounted display which can fool your brain. So ultimately we are trying to fool the brain for telepresence, for immersive experience. right? So although I am standing here, I should feel like I am in another environment, another room, another city, another country, another planet, right? So I need to fool the brain. That's the whole crux of the AR, VR and mixed MR and all, mixed reality. Everything is about how do you fool the brain. And fooling the brain means fool the senses primarily, through which brain perceives the world. Okay? So you need a head mounted device which can really render very fast, which requires very less power to run. So a lot of desired properties are needed. Latency should be very low, power consumption should be very low, quality should be very high. And one more thing which I think a lot of research is going on now is how to reduce load on the eyes. Right? You can see I am wearing this device, passive sensing device. It's helping me since I was in 4th class. Right? So you don't want to really stress your eyes too much. Okay? So that's another thing, and my belief is the way we are doing it is completely wrong. Okay? We need to really go to the way of what Inception was presented. Right? There should be a way directly to connect with the brain with electromagnetic sensing and then fool it, rather than doing this way. But currently this is how it is. So to do this, we need this device. Then we need a very good estimate of the 6th of position of the head, or essentially this device. Right? And nowadays we are also doing eye tracking. So where is the gaze while I am wearing this? So where I am looking. So if I am looking there, then I should render something in the front part of the virtual world. If I am looking like this, I should render this part of it. And there are a lot of details about it. The way human vision works, that also people have to study to be able to replicate or design hardware and softwares which can really support this. Then the third part that I am going to focus more and primarily is on rendering the 3D content. So I am not going to teach you computer graphics, but how many of you have done computer graphics if I ask you to raise your hand in your undergrad courses? Just raise properly, right? I am not asking your grade, so I am just okay. So some of you have done it. So the idea is you represent an object with I will talk about it in detail, as a triangulated mesh in this example, and there are attributes to the triangle vertices, to triangle facets, and then we render that 3D object, and the rendering should be very fast. There should be minimal latency. This is largely when I am talking about augmented reality, by the way. Okay? When the world is actually having a virtual object that we have inserted, augmented reality, that we might even interact with. So basically these are 3 parts, and I am going to largely focus on this part, but for the completeness I will just show you the head tracking solutions. There are a lot of variety of solutions available. Primarily it can be classified into outside in tracking and inside out tracking. So the idea of outside in tracking is there are some you can think of as sensors which are monitoring the scene, and I can only move within that area where the sensor has visibility. So these are like beacons. They are lighting, illuminating the environment, typically with an IR or any such modality which is not visible to our eyes. Okay, and then the headset has some kind of markers, and then they are being basically watched, and how the headset is moving, the one which I am wearing, where it is moving, it can actually estimate the relative transformation, the 3 degree of freedom of rotation, yaw, pitch and roll, and 3 degree of translation, x, y and z displacement. Okay, so because we need to exactly know how head is moving, and accordingly I will change the graphics so that I get an immersiveness feeling, right? And the inside out tracking is on the other hand does not require a beacon or something, but it uses computer vision, it uses features in the environment, and then using that it tries to track and estimate where I am. This is what as a human we do, right? We try to localize feature points, key points in the environment, and if we go to environment like a maze, then we are lost, right? In a maze what happens? Bhul bhulaiya, we don't know, everything looks same, and we are kind of stuck in an infinite loop. Okay, so our localization fails there. So the idea is this is more related to localization and VSLAM, visual SLAM, which we call in robotics. Just a nice video I will show you. So how does this HTC Vive is a solution? We have that in IIIT we are running a course there, and we have that system. So idea is there are 2 beacons which are actually flashing the scene, one vertically, one horizontally. Okay, and then with that, assume that these are the markers, then I can estimate their exact position based on the phase difference that I have or time lag that I have between illumination by the vertical and horizontal swap. that is happening by the two beacons. Okay. This is an example of inside out tracking where the person is basically reconstructing the environment on the fly, sparse reconstruction of 3D point cloud, and then using that they are trying to trace a trajectory of the headset. So you see the person is moving, of course headset is moving along with it, but the orientation of the headset is also being tracked, right? And then with this we can even generate a map of the environment, which typically is the aim in robotics. Here the aim is to really try to localize yourself where you are looking right now in the environment. And this is how it's being rendered for the person live. So one of the eye, you can see this is how what is being rendered. So the person is this room, but is actually experiencing this reality. Okay? Okay, so till now what I talked about was the need of such technology, the need of, or how do you really implement such technology at very high level, really mega level, right? Now, if you want to do that and you want to generate a virtual world, the biggest problem is virtual world should look real. How many of you play video games? I mean graphics games. All of you enjoy it, right? Well, at some level. But when you compare between two games, how do you compare? Apart from how many killings you can do. What is the key part? Graphics. But then why graphics? What is the right word for that? How much realism it has in the environment that is being rendered. Right? So it's all about realism. It's all about can they fool your brain to perceive a virtual environment real. Right? And I have seen people doing that, even Age of Empire and those times when there was no good graphics also. So it has, there are other aspects of getting engagement in game. Okay, I'm not saying graphics is everything, but that's very important. And do you enjoy playing game, a high quality game and low quality hardware? Why? Because there is no immersiveness, it's just lag. You do something and then rendering happens slower than that. So it has to be real time also, but we are not going in that aspect. So the key aspect is how do I generate real world, which is how do I generate virtual world which is highly realistic. Okay, so gaming, animated movies, so you want plants, you want trees, you want mountains, terrain, everything need to be look nice for outdoor. For indoor, of course, a lot of work also happens, but the problem is indoor digitization is easy. If I want to replicate this room in a virtual, I need to only scan this chair once or reconstruct the chair once, which I can manually do and replicate it. It's easy task, right? Not everything is easy, but you have controlled lighting and all, right? Outdoor is much harder. So we'll focus on outdoor part of it in today's talk, okay? And then how do I really learn from real data? Like can I use satellite images or satellite imagery like DEM is a digital elevation map or digital elevation model, which are actually perceiving from satellite the terrain's height. And how do I really use that level of real world information and then generate realistic terrains for virtual world? So learning based solutions is what we are going to explore. So in this use case, this is one of the solution that we proposed in ACCV 2020. It's a vision conference, Asian Conference on Computer Vision. The idea is this is a DEM. So it looks like a 2D image, a grayscale image. Essentially at every pixel I am storing what is the height of that point. And this is being scanned by the satellite. So I know exact GPS coordinates of which area I am sensing from satellite. And if I render it in 3D, this is how it looks in different views based on the shadow I add there with L-shade modeling. So the idea is, I don't know if the slide is not so great, but can you switch off one of these lights if anybody knows how to do that? So the idea is, what you are seeing here is a user drawn sketch. So an artist want to design a new terrain. So all they need to draw is this green strokes you can see here, right? So these green, yeah, that's really great. So these greens are basically strokes of different height levels that user can draw, and this red, blue is the river and the red is the ridges. So I want to basically use this and generate a DEM which can then render as a 3D terrain. But what I need to do, I want to generate it something which looks very realistic, right? So the idea is, can I learn from real data and then basically propose a solution that given this I can generate a very realistic DM. So I can learn a model for Alps mountains, I can learn a model for Aravalli mountains, I can learn a model for Nilgiri mountains. They all have a very different profile in terms of terrain, right? Or I can learn a combination of them. So all those tasks I can do with this. So we propose this terrain authoring paper, which is an IGRAS 2020-22. This year itself. It's an IGRAS is a conference in the domain of GIS. So Professor Rajan, Dr. Rajan is another collaborator from another center in GIS, a domain expert. So the idea is user can draw a map, a sketch. Yeah. Digital elevation model. It's a height map. This is what I have shown here. So from satellite, an image is taken of an environment, right, area, and then it measures what is the height of that point, right, and I can render it as a 3D. So it's a terrain I am talking about. Like if you go in a virtual game and I want to say I want to do a hiking of Gangotri, right, how do I do that? First I need to scan that area with satellite, and then I need to generate real flora and fauna. I need to add more details which are sometimes, because satellite cannot capture everything. If there is a dense forest, it will only capture the canopy of the forest, not the underlying surface. Okay, so the idea is, can I generate novel terrains and then use them for whatever application, gaming, animation, whatever, entertainment. Okay, so the idea is we learned that space using a VAE, a generative space. So variational autoencoder we employed, and we learned, so we extracted this ground truth from real DEMs, right, and then we quantized it with this, and then we trained this model that given this quantized level set and the strokes of river and ridges, valley and ridges, I want to really generate this. And we learned this generative space so that every terrain patch can be represented as a point in this low dimensional space. And then after learning this, the second stage is, given this we learned how do I given this generate a terrain, a DEM, sorry. Okay, so here this is a realistic DEM. With every pixel I am predicting a depth value relative to some fixed depth, sorry, height value relative to some height. You can look at either way. Right, depth from top and height from ground. Okay, so this is a two-stage process, and with this we can generate highly realistic terrain that we can put a texture on it which looks very real terrain. Okay, and now I can take two terrains that I generate in the latent space, I can do an interpolation of them. So this is a 3D modeling. Yeah. We are learning a latent space which is in sketch only, but continuous sketches. So given input a discrete sketch which has the level sets in green color, and then ridges line, ridge and valley lines, and we train that model to generate more continuous maps, sketches. And then second stage we take the sketch and then learn to map to, which is a pix to pix architecture. We map it to learn DEMs, which is a digital elevation maps.
Basically, if we don't incorporate this
Yeah. Yes. You lose a flexibility. Now I can interpolate in G space. We tried doing directly also. This outperforms that. We have shown, you can read the paper. Okay. Plus I can now sample any random point, will give me a new terrain in that space. Okay, with Gaussian mean and variance that I choose in variational autoencoder, I can generate a new realistic terrain. Okay, and then I can also pick a terrain, draw a terrain and generate variations of that I have shown in this video. Okay, so now one problem with this approach is it can only deal with patch levels. I can generate one patch, another patch, and artist has to put lot of effort, right? And the biggest problem is in gaming environments, I need an infinite terrain. I can go in any direction. The moment I go, a new terrain is generated and rendered, right? You might have seen such games, right? So on the fly I want to do, but problem with on the fly is people typically use a noise model called Perlin noise. So this is how it looks. So it looks something, but it's not actually real world. It's some random noise that is being generated. So how do we learn from real data and do that? So this is an under review paper right now. So the idea that we propose is, in the first training phase, what do? You learn two things. You learn a way. So we propose a frequency spectral as a frequency separation. So here what I am showing, terrain can have different spatial frequency. So this is the low frequency, this is the high frequency and medium frequency, and combination of them looks like a real terrain. But this is again a synthetic one that we generate with Perlin noise. So idea is, can I take the real world patches, DMs, right, and then I can do a frequency separation, and for different frequency I learn a diffusion model. So this is a model that was proposed in 2015. It's another kind of, it's just like variational autoencoder is a generative model, diffusion model is a generative model which uses Markov process, and then it learns to diffuse. It's a deep learning solution actually for generative modeling, and we use this to generate frequency specific terrains which we then fuse again, and then we train another thing which is a terrain super resolution, just like image super resolution you might have seen. I'll show an example later. How do I, given a noisy image, I can get a high quality image. So we want to use that to enhance the terrain itself, which is an image, nothing but an image, and then I am able to generate random patches which I can combine with the kernel blending that we propose using a Perlin noise as a base model, and then we can render a infinite terrain with that. So I'll just show you what example of a terrain that we have rendered, right. So this is actually learned from a real data, but has minimal component of synthetic and then a combination of them. Just different visualization of the terrain that we are able to generate with low frequency. This is how it looks. It has structure, basic structure, but not details. High frequency has details, but not the basic structure. And then we learn diffusion model in this space with the forward diffusion process. It's a different T value. As the diffusion evolves, it becomes more and more detailed. So low T is low frequency, as T increases, high frequency. So I am not going in detail of diffusion models here, but we just wanted to show for completeness of it. And then a Gaussian kernel blending that we do with Perlin, fractal Perlin noise that we use there. So if you do it without blending, this is how it will look. Independent patches if you put together for infinite generation. When you do it blending, this is how it looks. So for that we use a fusion there. So I won't go in much detail, then I'll skip this part. Then let's assume I have a terrain. Now what do? It's just a bare land. I was just today seeing from the flight window when Jodhpur came, it's all more or less barren land, right, with some trees and some farms also I was happy to see. So how do I really make it like this? Unfortunately, our goal should, as a human being, should to make this land as with real trees. I hope some of you are contributing, because I am seeing that in IIIT when I joined, I did own a plant kind of movement, and I am very active in plantation drives and all there. So I am sure all of you should plant one tree and you should survive 2-3 years by the time you are here. You should be a goal as a human being, contributing to the place you are extracting so much water and energy with this AC and everything. Okay, so coming back to graphics. So we proposed in 2021 ICCV a tree generation. It's a grammar based tree generation, right? And then we actually generated a library of tree for Indian species, mango, tulsi, plant and trees that we generated, banyan tree, and then you can see this is how a rendering look like. So we made it available, you can download it, it's a Blender plugin that we have developed, and now you can design your own games with Indian species of tree. So there was a novelty in the grammar itself also, and then you can also look at how do we really, this can really deform with the blowing air. You can also model the tree growth actually. So this is a wind effect, by the way. So this is how the stem will deform as the air is blowing. Then you can also have a control on, okay, I'll probably skip this part, but there's a Blender toolkit that students have developed, is also available. If you're using Blender in computer graphics, you can just add this plugin and you can develop your own species of tree that you want to do that. I'll just little bit fast forward things in the interest of time, because I know everybody is tired now. And then the tree growth simulation we can do here. We can also, this is a forest rendition that we have done. Okay. So the next part that I will come to is a human. So till now we looked at urban, rural environment, or you can say the forest and all. Indoor also a lot of work exists. But the key thing that we are interested as a human is another human who want to live in a virtual world where there are no realistic humans. Right? Of course, I do not endorse setup where tomorrow you have a PUBG version where you can put avatars of people you hate and then you start killing them virtually. This will be the nadir of human being a human being. We don't want to do that, never. I never recommend going to PUBG kind of games or any such games which take away your sanity. Okay? But anyway, once I was discussing with my friend that any moral policing will not work. A civilization has to realize its mistake and evolve, but you don't want to be part of that generation which is lost, so be careful. Gaming and all is good, right? But it comes with a caveat. So unfortunately, don't tell me that you are like that smoking company, whatever, the cigarette company who is telling that it's hazardous but still selling it. So you are designing virtual world, comes with a caveat. You have to be careful that in future your generation, next generation should not lose the touch with the real world. That's what is happening. Mobile is a practical example of that. Right? Family structures are disintegrated because of that. You just go to any restaurant. Husband is seeing mobile, wife is seeing another mobile, and if children are also grown up after age, they are also stick to their mobile. What's the point of going there? Anyway, but ultimately I want a virtual presence so that I don't have to travel all the way from Hyderabad to Jodhpur changing 2 flights. Can I just stand here and talk? And people have done that. In elections also there are ways in which people are telepresenting, but it's not fully immersive. I can see that a projector is there and it's generating something. Right? Can I simply wear something and I am in, let's say I am standing here but I am standing in Hyderabad and I am moving around on the stage. Okay? For that the first thing you want is a good avatar. So this is you can try, there is a company online that you can just upload your photograph and you can generate model. Unfortunately it does not look real, does it? Right? Hairline maybe they try to match, the nose they try to match, but not beyond that. And most important part, clothing. Right? So how do I really digitize all this? If I can do that, then I can achieve in AR, VR very effective telepresence for humans. And I can make virtual worlds which are highly realistic. So this will be the large part of the remaining talk. I hope there's no need to clap now. Right? Okay. So how do I do that? Scalable 3D digitization of real world garments and scalable digitization of human beings just with monocular or a few view images. Right? So this is a classical setup. I put a person in the middle and I put so many cameras around it. I take an image of the person, and then I generate a 3D model of the person in that pose. And you can see it's basically, and another variant of it is I take this image, single image, and I generate a 3D model of the person, same person. And there is a 3D geometry underlying it, which is represented by a mesh actually, triangulated mesh, and then I put clothes on it, a texture on it, which make it real. Okay. Now here, this is okay. I can understand that you are seeing an object from different point of view and then generating a 3D of the object. So it is plausible, doable, right? Scientifically also. But this is a very ambitious attempt, which is ill-posed problem. Because when I do a imaging of a 3D object, of a human or any other object, I am seeing a 2D image eventually. What is formed on your eyesight is a retina, is a 2D image. Luckily we have a stereo setup, 2 cameras, so we can perceive depth with triangulation. But then also a lot of priors happens in the mind. Anybody has ever thought so many movies came on Alien, all of them show it as a 2 hands, 2 legs and 1 head. Because this is how our perception of life is, intelligent life is. Anybody has seen a donkey being depicted as an alien? No. Our biases are there. So you want to really absorb those biases here. And can I do this in monocular then? Can you just give me one image of mine and I can give you a 3D plausible model? Of course, what is not seen, it will be always plausible. And if you can give you slightly more images, few more images, I can do much better, of course. Okay, so we attempted this. So those who do not have computer vision, in 3D computer vision background, although I conduct a summer school and I can see many faces who are there this year also. So you are welcome to join that in Hyderabad. So you take a point cloud representation of a 3D or mesh or volumetric or a mathematical representation which is learning the decision function or the intrinsic function itself, which defines the boundary. So I learn a function f which is parameterized by parameter theta, and given any 3D point in R3, it tells whether it is inside the surface or outside the surface. So in a way I am learning this underlying function which is defining the surface of the body. So the idea is 3D is all about capturing the surface and representing it either with point cloud or mesh or volumetric, like Lego game, all of you might have played or heard, and then intrinsic function learning, which now with deep learning is possible. Excuse me. So, and this is a texture mesh I was talking about. So this is literally like flattening the mesh in 2D, right? Anybody has seen how they make globe? Globe all of you have seen, right? In your schooling time, right? How do you make it? Or how Google Earth is able to show you the 2D map of the world or the 2D map that you have filled in your childhood? It's a flattening of the Earth surface, right? And there is some deformation does happen. Okay, so this is a 2D texture map of the 3D human body. You cut the throat and then you cut it from backside and you flatten the face. Same with the hands, torso and everything. Okay, so we use that. Lot of applications of 3D human digitization. So you can see this is something that is now very popular but not up to the mark, and our group is making a contribution towards it. I'll show some results on 3D digitization of clothes and rendering. Then sports analytics, dance, animation, yoga training, many applications. In fact, biomedical and in cognitive science people need that for gait correction for stroke patients. So it seems by looking at how somebody is walking, you can predict whether the person will have a stroke or not, or already has a stroke or not, or any other deformation in the body, spinal deformations. Okay, so a lot of things can be done. Okay, apart from entertainment. So what are the challenges in human body modeling? Okay, the first and biggest thing is non-rigid complex body poses that is exhibit. Right, so our body can actually exhibit infinite or very large space of articulated body poses. So if I have to reconstruct or represent a human body, this and this should be same person. Right, so modeling these poses and then reconstructing while learning to or dealing with multiple huge variation in poses is very hard problem. On top of it, self-occlusion. So if I give you an image of mine like this, then this area is not visible because it is occluded by the hand. Right? Then if typically I have one monocular means single image or only few images and non-calibrated, I don't know exact camera positions. Then topological noise. So when I reconstruct a 3D object, either I am wearing a lungi or camera is not seeing my leg. It's two different separate parts. So it basically reconstruct this. And then when I reconstruct, I can have non-uniform discretization of surface. And then very thin surfaces like a rope here that girl is playing is very hard to capture. So all this data was captured when in India where I did my PhD. I know her name, Lucy. Anyway, so on top of it, another big challenge that comes is clothing. And especially Oriental clothing, Indian clothing, loose clothing. If you are really wearing a dhoti or sari or even a suit kind of this, right? It's very hard to model the dynamics of the cloth and where it will move as the body pose will change. It's an active area of research, we are working on it. Okay? And then, so recovering body and clothes surface separately, modeling clothing deformations as the body move, recovering exact surface geometry like wrinkles and all, how do you model? Okay, the same shirt will not have these wrinkles if I am really a fat person, right? If there is a tummy, it will have a very different kind of deformation. Then Then I sense a person who is moving, like say dancer is dancing, right? Anybody has seen Bharatanatyam dance? Nobody raise hand, right? This is a very dangerous thing in Indian expression, right? It's both yes and no. So 2 days back, in fact yesterday only there was a talk by European researchers in Canada, and he asked, you are guys understanding? Everybody said this. He was unaware of this expression. He says, oh, everybody is understanding. So then reconstructing hairs, even much tougher, right? I am little bit lucky that I am losing hair fast, but if there are long hairs, people with long hairs, very hard. Why? Because it's a thin structure, very thin structure, and its texture also, it absorbs the IR and other kind of things. Very hard to model. Then hand details and exact face details also hard. So it's a very hard problem, guys, what I am trying to tell you. And what we did in 2018 itself with deep learning method, that given a single view we were able to generate this 3D kind of geometry, which has both the body and the cloth deformations planned. It was a volumetric regression that we did. We learnt those, if you remember the volume voxels that I was showing here, these voxels here, sorry. So we learned which is on and off. It's like a 3D image where every pixel is on and off. So we learned this building on a top of a 3D N2 R2 network, R2N2 network that was proposed by Stanford, and then we were able to, and then we also recovered some low quality texture of this. 2019 then we worked on a paper where given the monocular images we tried to predict the underlying parametric mesh. So it's a naked body model, it's a parametric model called SMPL from Max Planck in Tübingen in Germany, and then this is the underlying skeleton. So we put loss on the joint location, we put loss on the mesh, and we use a semantic segmentation coming from a dense pose paper, and then we use some deep learning pipeline, encoder, concatenation of feature and decoder, and we were able to reconstruct I'll show you some videos, per frame reconstructions. So we predict this point cloud which has underlying fixed topology mesh, and we deform these meshes and their position to fit to the body pose. So this is on a real world data set that we show results. Again, we are not using any markers or anything here, it's just an image the way we are treating it, and we can see how, what kind of deformations and poses, extreme poses that we were able to model. Till now we are not talking about clothing at all, it's a naked body model. Because pose itself solving that, and you can see there is a jerk here and the head is inconsistent, that's because we are doing it for every frame independently, there is no temporal coherence, it's also an active area of research. We just were starting a project with TCS on sports and all that they want to fit. This naked body model itself, first of all, look at how a footballer is playing and kicking and all. So these are really complicated poses for a network to learn. Okay. Now we came to another contribution in this area where we realized that 3D is hard. For learning also on 3D is hard. Because if you represent on point cloud, you lose information. If you represent on a volume voxel, there's a lot of redundancies there. So voxel inside my body are also filled and I need to learn and model them. Implicit came little late. So we are also using that now. So in this work in 2020 3DV conference, what we propose? We propose a novel representation, which is a peeled representation, which is motivated by computer graphics. So idea is if I have a 3D model of a human being, let's say an oracle gave it to me, or I have a scanner high quality that can generate, I put a virtual camera, I think time wise we are good, right? If you are not enjoying, let me know, you can cut short it. So what we proposed is, I'll show the video, but we said we put a virtual camera from any alternate views, many views I can put, and I shoot a ray for every pixel. Everybody know how imaging happens, right? 3D object is illuminated by a source, the surface reflect the light, hit the camera pixels CCD, and they are illuminated with that color, and we assign that color and digital image is formed. It's the other way around. Think of it, the rays are starting from camera center hitting the object surface, and they are hitting, they are not even optical ray that hits only the surface is visible. They are like laser ray which goes X-ray kind of thing which goes inside the body, and model what is the depth of this point, this point, this point and this point. As many as intersection it has, it's try to model a depth, which we represent as peel depth here. So first depth, second depth, third depth, fourth depth. Okay, and then so this is basically this right leg of the person, front side, back side, then left leg front side, which is this side, and then last back side. And similarly, an RGB image can also be formed for a 3D model. And we propose to learn using them. So this is how it happens. Ray shoot, and for every RGB image I know that there is a corresponding depth and RGB, peel depth and peel RGB we called it. And then we said, now I will use deep learning CNNs on this representation, which is much better than actually dealing with 3D itself, faster and scalable. So you pass it through a ResNet encoder, and then we have two decoder branches in the GAN setup where we are predicting the peel depth and peeled RGB, and there's a discriminator which says whether they are realistic or not. And then I also have a 3D loss called chamfer loss, which gives me the finally peeled representations that I have reconstructed, regress with the ground truth. And now I can get from a single monocular input image, I can get the peeled depth and peeled RGB, which I can back project to get the 3D point cloud of the shape. And then I can meshify it. So from this kind of image, you are able to get this kind of reconstruction. Of course, quality is bad here if you see the hand and all, right? But the idea is it's completely model free. This was 2020. Then 21 we said, okay, I want to use semantic prior. If I know this is a human head, this is a human hands and legs, and every view and image I can generate. So I basically learn cascade of model. I said, first I will generate from single image some peel depth plausible. Then I will also use the same image and this peel depth as a prior and generate segmentation map. And this segmentation map along with the initial depth map and RGB image, I will feed to generate more refined depth and RGB images. Okay, so I am not going in much detail of this, but paper is available. And then this work came, which is actually under review final phase in IJCV, which is a top journal in computer vision, next to the PAMI, lower than that little bit. So International Journal of Computer Vision. And the idea is we propose that given an input image, we will also make use of this naked body model. And then we want to separately learn deformation of the body model to look at the geometrical difference in the hand structure. But for loose clothing, we want to learn separately, complementary part of that. And then combine both of them to get this final point cloud, which can model loose clothing. So how it works, given an input image, we learned an SMPL body estimation, which is a naked body model, we peel it, and those peel map along with RGB is fed to a common encoder with 4 branches of decoder. One for RGB, one for RGB, one for deformation of the SMPL, which will come as bottom, and one is a complementary modeling a loose clothing, which a naked body model cannot model. And then we fuse all these two to basically get a loose clothing modeled in peeled representation. And then I can basically back project in 3D point cloud and recover a 3D model of the person from monocular image, single image. And now I can train a model on synthetic data and then just take some internet images and generate 3D models of celebrities or people in different varying clothing. You can see a hole there, right? Can you see, all of you? A cut is there. That's where the rays are hitting the tangential to the surface. They can't model this part if you are seeing from that viewpoint. So we fill those holes. So it's a per frame that we reconstructed in internet video. Then we propose another variant, which is, well, it was actually, it was shot down in the first round of WECV because of another work that we didn't compare well. So we have resubmitted to ICVJIP, but the idea is, I want better face and I also want to improve the surface geometry. So there is one inherent problem in the reconstruction of monocular. For example, instead of this very thin strips, if I have big strips, right? So these are intensity change. But since I am learning from an image, Model has no idea that is it the cloth which has texture or it is actually the human body is like this. It has no idea. Right? You might have seen old people with skin which has wrinkles. Right? So those wrinkles, they might come actually from skin, or I might wear a cloth which gives an impression that I have wrinkled skin. So network has no idea learning unless I make it aware. So how do we propose to suppress that noise. Okay, and then basically from a monocular image generate this kind of 3D. Now you can see the back side is not very accurate, only plausible it is generating, because there is only one view available. So we even try to address that with multi-view, which is under review paper right now. And for the face, what we propose to use, we say, okay, since face is a very small as compared to the full body, we crop only the face, super resolve it and reconstruct it per pixel depth, and then we put as a prior in our peeled model. So we are able to generate very good, reasonably good quality in terms of actual geometry of the face as compared to the fixed naked body model which has only fixed face. Okay, so you can even the beard kind of thing, and then the way hairs come out can be modeled, but again the back side is not modeled properly because it's a ill posed problem. I don't know how the back side look. Then what we did is we bought the scanner thanks to a government funding, and we reconstructed human body models for Indian population in high resolution. So it's a structured light setup, and we got this kind of reconstruction. So anybody working in this domain, this data is making available from 1st October. It's a Diwali gift from our side. It's a very expensive data. If you want to buy outside, it's very expensive. One mesh costs $50, and we are releasing 250 meshes with very high quality and also diverse clothing. So it has salwar suit, lungi, sari, all possible ways that we can deal with loose clothing. And this all was done by this guy. Sagar was leading a PhD student, a master student, Astitwa, just to acknowledge them, Chandradeep. Only they agreed to put their face up there. And lot of our staff, because COVID time, hostels were under quarantine. So we had to make use of a staff, security, cleaning people to come and admin people. You can see the quality, kind of quality, and the key thing is the Indian clothing is what we tried to capture here. So apart from this, we have a multi-sensor lab also with multiple cameras. So these are lights and these are cameras which are Azure Kinect 1 megapixel depth. We had 4 initially, now I have a 7. So this is how we are trying to capture now Indian classical dance forms. Of course, without tight, loose clothing right now, because we want to set up a benchmark for the world to use that. Why? Because it has complicated poses, and it has beyond that. It has a vocabulary of different poses, enacted in certain way, narration behind it. There's an ontology of dance. A lot of things are there that we can be done on top of this data, apart from just 3D. And you can see the challenge. So if I have 4 cameras, one is looking from here, one from here, and 4 from back, if my hand is in front, this area is occlusion, so it's not visible. So I want to really fill those holes and get high quality, right? So if you fill it whole with a TSDF is a method, truncated sine distance field, we get this kind of reconstruction which is very noisy, and then we basically use an off-the-shelf neural deformation graph paper from CVPR to fuse across multiple view. There's one more famous work from Microsoft called Fusion 4D that we have successfully replicated, and we'll release that code also. So you can see the smoothness that we achieve versus the red one that we got from TSDF. And then I can make anyone dance. So he's one of our staff member. His 3D scan, we can basically, via this SMPL that we have fitted to 2D video, we can make him dance a classical dance. Of course, it's noisy per frame, and then you can see the deformations around legs and all, but this is one use case, right? So if anybody want to become Michael Jackson, you can just take his video, get the skeleton extracted, put your 3D scan model, and then you can dance like him. What was that famous? Moonwalk, what was that? I'm never able to do it. Then we are also modeling now hands, because in Indian classical dance, Hasta Mudra is a very important part of expression. right? And it requires very complicated, an ongoing collaboration with Brown University also, where we are looking at reconstructing hands of multiple views and learning-based framework, learnable parameterization. Now, we'll come to the final phase of this talk. What's the time check? I'm poor at it. 6:30. Can I take 5 to 10 more minutes? Okay, got a missed call also from somebody. So, virtual try-on, like virtual mirror. I want to wear a cloth. So now, during COVID time, all of us were stuck. First 6 months were really poor, bad, lot of fear, but after that things were better. But still, people were not going for window shopping for retail. So online has picked up a lot anyway. Before that also it's happening. After that it become even more. But the biggest problem is the return rate, guys. So I worked with Myntra, and they say that people order and they return genuinely also. Not those who just want to try new clothes and then return. Okay. Why? Because one thing is the fitting is a problem. Second, how it looks is a problem. They want to see it in 3D on them. Okay. So then, that's a very good use case. The problem is it's not scalable to loose clothing. You can maybe have a fixed template of t-shirt and pant, and you can just change the slides slightly and there are textures differently. But how do you do really, because basically garment design is an act of artists, right? It requires an art form, a creative activity is there. And you don't want to lose the underlying geometry and texture because of that. Right? And there are high frequency details that are out there that you want to retain. So you don't want a mesh reconstructed with colors, low quality. Right? And it has a lot of application in nowadays. Clothes are also, there are softwares with which people design clothes. Right? And then you can do a virtual try-on a mobile or on a laptop. I don't know what happened. So I think laptop is also tired, it wants a break. So basically there are a lot of use cases of this. Then you want gaming and animation movie, you want realistic clothing. You don't want something that's synthetically generated. Right? And then you can also want to learn how the cloth deforms and physical simulations of clothing and all. Right? So to be able to do that, you need digital clothes, and the fast fashion is the biggest challenge there. I can't say I'll scan all clothes with a scanner, right? Because every month there are more and more designs coming. Every season there are a lot of clothes that are being designed. For specific to summer there's a different design, winter there's a different design, right? And this also leads to a lot of environmental impact, because these companies produce in masses and they just throw them out if they are not being sold. Okay? And then 3D printing of clothes is also now the future that is being happened. I want to have my own 3D printer, design my 3D cloth, print it and wear it. That could reduce this little bit. Okay? So 3D printing dress is one example. There are references, you can have a look at it. Okay, I think I am pressing the wrong button that is causing it, but I will. Okay, now, yeah, I'll just move quickly away from this. So what we did, given this image, we generated this 3D geometry and this textured map, which we then put on this looks like this. So monocular reconstruction of Indian clothing, loose clothing, not just Indian. Okay, with no parametric shape. And this texture map that I was talking about for the human body flattened, just a more detailed explanation of that. So if a 3D sphere is there, you can flatten it as a UV 2D map, just like a globe we do. And to be able to do that, I need to cut it somewhere. That cutting is called finding seams, and then cut along them. What is the advantage of texture map? If you see, this is a mesh, which if I am correct, with 100,000 vertices or at least 50,000 vertices, you can see with textured meshes, I can see high quality details very well. These thin lines are coming out very well. Of course, there is some pixelated artifact, but if you zoom out, it doesn't look so bad. As compared to here, which is actually very bad and dependent on mesh topology, mesh number of edges and vertices. And if you even go to low quality mesh, which is what we expect when we go to mobile phone based rendering, you see the quality degradation here as compared to what we see with the same mesh topology but texture. So texture is very important, that's the underlying idea. And if you go with fixed garment, so this is our work that we did with Mintra and Vakvi, and the idea is you have a fixed texture map and you can simply manipulate. So I can remove Puma and put some other brand also on the same cloth. I can do all that. But it's only on a fixed topology mesh. Only on t-shirt it will work. Is there any disturbance there? I can wait if you want to finish something. It's disturbing me at least. Either you sit down, you go out, I don't mind. Please. I never like to offend people, but try to neglect it. Okay? So some template based solutions are there. These are really state of the art papers, but they have their own limitation. The deformations are not realistic. It can't model complicated clothing at all. So if a template based will model this as a separate piece, this as a separate piece. But I want to learn this. So what we propose is, which is a paper being published this October next month, I am going there from Portugal for ACM Multimedia. Given a monocular image, our Xcloth method can basically generate textured meshes on which I can render now high quality texture 3D for loose clothing. And it can deal with any arbitrary kind of clothing topology also, not just t-shirt and pant. Okay, so it can deal with diverse clothing, it can very complex clothing, occlusions also partly. So this is a SOTA that I will skip this slide, but this is a CVPR 2021 work which says that nothing exists closer to what we did. Okay, so these are the other method that we compared, including the CVPR 21 work, and this is ours, which has all the desired property: monocular, texture map prediction, geometrical details, cloth body template free, generalization to arbitrary clothing, occlusion handling. So how we do it? Given an input image, we have a 3-stage pipeline. The first one is implicit geometry estimation, which has inherent inside itself 3 more modules: geometry estimation of the whole body, deep semantic field estimation, which says which is the head, which is a t-shirt, which is a hand, and then garment extraction from 3D human reconstructed model. Okay, so you learn this first from monocular image, that we use our own model, and then we learn the semantic field on 3D, and then we extracted the garment. Now second phase is with this geometry I need to flatten it. For that I do automatic seam estimation. I predict where to cut the cloth, and then I flatten it with UV parameterization. In this work we did it deterministic methods that are already existing. So I take this mesh, cut it, and then flatten it like this. And the third thing is texture mapping and inpainting. In fact, since I am doing monocular, I am seeing only partial cloth. Backside, how do? I simply inpaint it with learning based method. So given this, we generate this by first module. Second module, estimate the seam. Right? The generation happens with this peeling that I already explained. This is a parameterization output, and this is a textured parameterization that we see, texture maps, which are inpainted. So this is without inpainting, this we do with inpainting. So we take this part visible, we take the back side, we just invert using symmetry, and then remaining part with black area we texture, we inpaint it with deterministic or learning based method. So now with this kind of in the wild images we are able to reconstruct, and these are other methods: BCNet, Pix2Surf, MGN, and ours. And you can see in 3D what kind of reconstruction we are doing from single image. Right? Then we can do texture manipulation. So from this image I generated geometry and I change the texture. So now you can just plug and play, put whatever pattern you want on your clothes and you can see them. Preferably on your own 3D model if privacy is not an issue. And I can write anything now on a t-shirt, I wrote something. So this could be very useful for 3D printing. How does it look in 3D on particular body? Then this is super resolution example that I was mentioning. If the input image is low quality, right? This is if you zoom in you will see this low quality. I want to super resolve it. There are applications available which super resolve. We use them, but we can now do it on texture map, and now I can get high quality rendering of the cloth from low quality image. I can basically take a 3D mesh which is reconstructed from a regular body and then take it on some wrestler and then put it, and I can basically deform it appropriately for the body shape. And I can then also render it in 3D in motion, also in loose clothing. So that monocular image is rendered like this. You can see some noise is there in this area. but otherwise looks very realistic. Of course, the sequence looks zombie. Student did it last minute during the deadline, and once it is submitted, who cares? But now they will care. There's a startup that we are registering this month end. So hopefully you will see some product coming out of it in next 3 to 6 months via one of this big retailer. If it works. Sometimes your technology is advanced enough that community don't adopt it. Because they don't have means, right? But India in general is very good at adopting technology. You can see UPI, what happened. People thought people will never use. I'm not biased towards one government or another, but when government pushed it, people say, oh, they are illiterate people, how they will use UPI? And now everybody is using that. Every card, thela owner has that. We are good at technology, adopting technology and new ideas. So I'm hopeful about this startup. Then this now we extended it to multi-view also. So we said, okay, one view is only plausible. What if I have 3 views available, 2 views available? So we change certain modules, and we also make this parameterization now learnable. So part of this work is published in ACM SIGGRAPH Asia 2022. Yesterday itself it is accepted as a brief. And then it's under review. The whole pipeline is under review at WACV, where we say we can do even text mapping learnable. We can do this multi-view using an off-the-shelf implicit function learning technique. And then I have the learnable texture mapping and then texture filling. And it does not use a prior also, that's the advantage. So when I had a human naked body model prior, for that image you can see there's a curve here in the body, which is actually now removed, because the bad prior is not there. So we just compare with some parameterization, the flattening, the deterministic methods, how does it work, and the blender based method opt-cut, least square LSCM, and our solution, how does it work, where it is. Okay, this image is missing. Okay, then we show just some results on low quality mesh, how does it will deform in a blender, the loose clothing basically. I'll stop here. There's one more work we are doing related to AR, VR, or I'll just quickly go through it in 2 slides. The idea is since I'm wearing this, if I want to telepresence, if you are sitting in one state and I am wearing in another state or even another room, and we both want to be telepresent, how do we do that? So we can have a 3D avatar of the person, but it does not reflect the actual appearance. What if I can unmask the face region, the eyes region, if I know the exact trajectory of the eyes also? That is another work that we are under submission right now. So we propose this way of in-painting the facial region, especially the eye region, and then we can basically, even I am wearing headset, the other person who is joining from other side of the e-meeting will not see me as wearing headset. And it will try to retain as much as details possible, like hairs and all you see here. In 2D right now, you can use it per pixel depth. I don't have that video here, but we have generated that, and we compared with other SOTA methods and we outperformed with them using our method. Still not temporally consistent. So we had a ECCV work paper on that, and then we have one more submission we are under progress. So I'll stop with this here. I hope I didn't bore you too much. Still have energy for the rest of the evening. Any questions?
Yeah, so thank you, Avinash, for very exciting and interesting development from your lab, and in general covering an array of areas and application domains in which you are currently venturing. So I would take some questions from the students, so please go ahead. If somebody has any questions for Avinash based on some of the areas he discussed.
Good. So there are some questions. I'm happy. People are not sleeping at least.
Sir, actually I want to ask about motion sickness. That in virtual world, motion sickness is a major problem. So how can we rectify? Is there a solution right now?
So I did not focus at all here on that, right? But it's a very good question, and that's where I tried to already put an answer for that. See, why motion sickness happens?
Because our brain framework works on virtual reality and it goes outline.
No, it's not just brain. There is a way in which we estimate our head position.
Yeah.
In the ear canal, there's a liquid, right? So you might have known, some people they can't really deal with roller coaster rides or even bus rides. Their sensitivity is much higher than other person right? So their brain can sense their position is changing. And in vaction what happens, it's getting a false, it's not matching. So what other senses are telling and what eyes are telling is very different. So in eyes I had this experience. Recently I was in Delhi. So all of you should go. There's a nice demo of Ajanta caves in Delhi National Museum. IIT Bombay startup did that. So the one moment the tracking went off and it's like, oh, the whole, I am like in the space moving while I am standing on the stand. So vaction happened. So this is a mismatch. And that is because we are just trying to focus on one sense. Right? We are not fooling the brain completely. So is there any way I can just put something we are maybe Dipanjan might be very interested on that idea, but everybody has this idea, nobody has solution. I wear something on top of it which fuse all the modalities it can fool simultaneously. So the nerves that sending message about the localization of head, I am fooling that signal for the brain. Then vaction will not happen. So that is the way. This is not the right way that we are doing. But technology devolves like this only. We are actually looking into those aspects also, but not at that level. We are starting a collaboration with SVASA on meditation, how it helps affect the brain plasticity and all. Yeah.
Anybody in the back or in the middle or in the front, whoever interested from that side, this side? Anybody who has a question?
They all are exhausted.
I think so.
So
it was a long session, but it was very, very intriguing.
late evening also, so almost dinner time for some of them.
Yeah. Well, I think like somebody may be still thinking actually.
Anyone?
Maybe we'll catch up with you later.
Yes,
Yeah.
you're welcome, and we do a summer school also, and we'll have for startup also, and we'll do a lot of other things. There are always vacancies, those who are graduating from here. I don't want to hunt from here. Anybody who's motivated, and so all of you are welcome to IIIT to participate, and otherwise also we can work remotely. Thank you.
So thanks again.
Thanks a lot.
Yeah, I would now request Dr. Rajendra to give a memento to our speaker, Avinash. Thank you for your suggestion. Yeah, thank you everyone. I think we are done with this session practically. And thanks for all of your presence here to witness this interesting talk. And if you have any other questions for our speaker, you can take it outside. Yeah, thank you very much.